Dear colleagues, sorry for technical problems. Now we start the second day of conference, and let me invite Peter Davidov from Lashkaryov Institute of Semiconductor of Physics, National Academy of Science of Ukraine. It will be the first presentation, and I wish you a fruitful day today. We will have approximately 40 oral presentation from different scientists from different countries.
Сейчас включу трансляцию.
Hello, my name is Peter, and today I want to present the topic spiral nanoparticle arrays as a sensitive layer in a MIP-based chip for explosive detection. So, what is nanochip? Well, in simple words, it's just a piece of glass covered with a thin layer of atom nanoparticles. But these nanoparticles are very small and they separate. Usually, it's like they got spherical shape. And the average size of these nanoparticles is around 12 nanometers. So what it gives to us? There is such known phenomena as local surface plasmon resonance phenomena, or shortly LSPR phenomena. In simple words, is the ability of nanoparticles to absorb the light of some specific frequency, almost all light energy absorbing with some specific frequency. How we can use this in sensorics? For example, we can use, here you can see spectors of absorption. So these spectors highly depends on size, shape, material, distance between nanoparticles, and also on surrounding environment. So it's like a feature of this effect, which we can use for sensorics. But when we're changing the environment around the nanoparticle, we can shift our LSPR position. And this peak will move left or right depending on the environment. How we can use this, how we can control the environment. So each time we repeat the sensoric actions on our chip, we got each time the same environment. So we can like use it as a sensor. One of the most fun approaches is MIP, molecularly imprinted polymer. If speaking simple, you just create a couple layers. First layer is your glass slide, second layer is our nanoparticles, third layer is polymer with holes, specific holes for specific molecule. So for each individual molecule, you should create your own template, as you can see here. And then you remove this template and you got structure with polymer and holes for this template. So you can use this chip further for sensorics. And when this template molecule gets in these holes, empty holes, the spectrum shifts right, because environment around the nanoparticle changes. Empty hole and filled hole. In our research, we use such templates as 4NP, 4NT, 5NI, and 1NF. Why we use these templates? Our goal was to create chip that got specific sensoric abilities to TNT, but due to the security problems, and we also not allowed to use TNT in labs, I guess. We use like similar molecules to TNT structure. You can see TNT got benzyl ring and 3 amino groups, yeah, and our templates got benzyl ring and 1 amino group, which located in different places, yeah. So we used these molecules as a template in our MIP structure. We start with surface modification with inverter. It's material to start polymerization reaction. So we put our chip in inverter for 1 day, and then we took specters, and our inverter influenced it in the chip and give us some small shift. Then we add some monomers to this solution and start polymerization reaction. So in general, we got our chip, our nanoparticles, inverter, monomers, and our template. And we put all this under the UV lamp for polymerization reaction, and we received a MIP chip for our gold nanostructures. Then we test our chip on 4NP. It was a template that we used in MIP structure, and we got small shift for spectrum. As you can see on this inset. This shift over time can be described with such exponential curve. On this spectrum, you can see like state of this chip before we put explosive. It's like this lane from this lane, yeah. And then we put some explosive, and exponential curve start goes and goes to saturation. That was reaction of our chip on milligrams of explosive for NP. Of course, then we took a couple more experiments with different molecules for NP, 5NI, and 1NN. Yeah, and we create such table. As you can see, the average time response for NP, like the time that our curves goes to saturation, our shift like move, and then stop to move. Yeah, is around 40 minutes. And the shift of our position in the wavelength is near 0.9 nanometers. Also, what interesting for NT shows much more quicker response. It goes to saturation in 2 minutes. And, I guess it's very interesting result, which we will research in future. And we compare these shifts in such histogram, yeah. So we get a shift without molecular imprinted polymer, and we got chips with different reaction of this chip on different gases, 4NP, 4NT, and 1NN, E5, and NI. As you can see, we imprinted it our chip for NP, and it gives us the best response. So our chip is more sensitive to this specific molecule, but it also sensitive to other molecules that are similar in structure. So as a conclusion, during our research, we create the chip that can be used as a sensor element for explosive molecules, such as 4NP, 4NT, 5NN, and 5NI, and 1NN. Average time for saturation is near 40 minutes, and average peak shift is around 0.7, 0.9 nanometers. That's all. Thank you for your attention. Maybe you have some questions.
Thank you for your talk. It was very interesting. Please, if we have ever questions from our conference hall. Oh, okay, just a moment. Please come also, because it could be problems with connection.
I have two short questions. For result about sensitivity of such molecular imprinted polymer to vapor of different compounds.
Yeah.
From the line, yes. But there are many explosive compounds, different chemical composition. In each case, you must previously imprinted this molecule for sensitivity to such type of structure.
Yes.
It's not universal because it's not easy to.
I didn't tell that this is universal. Yeah.
And next point, you tested sensitivity to vapor of with some concentration. But in real condition, this concentration can be lower.
Of course, it can be, but we tested it like 2 milligrams, I guess, or micrograms.
So guess it's vapor.
No, we took like solid state material, put it on to the cuvette, where was our chip, and it started vapor, like solid matter, solid state crystals got some vapor.
Yeah, but not gases.
Huh?
But not gases. It's vapor.
Yeah. But in real life, it's like similar because, for example, if someone interacts with explosive and it can be somewhere on his clothes, some small particle. It's like very like sand pieces here. We took two such particles, and if such particle somewhere on a clothes, it's also evaporating something, some small molecules, and you can detect these small molecules.
Okay, hey, thank you for your talk. It was very interesting.
And you can see it in YouTube any time.
Thank you.
Yesterday we will see that our first day translated in YouTube, and it was approximately 1,000
Views.
Yes. So you can see that a lot of people use our online link and connected to our conference. Thank you very much, Piotr Demido.
Oh, I have to invite the next speaker, whose name Anastasia Marushenko, who is a student of National University of Kyiv Mohyla Academy. Hello, Anastasia, please turn on the sound. We can't hear you.
I'm going to share the screen.
Okay.
Just 1 second.
Can
you hear me now?
Something wrong with your microphone. We couldn't understand you clearly.
Maybe microphone put for bigger distance from you, because it is very close, I think.
It's like.
Is it better right now?
It's ripping.
Okay. Is it better right now?
Yes, it's much better. It's great.
Okay.
Perfect.
Probably because of headphones. Sorry about that.
Oh, it's okay.
Sharing the screen.
Yeah.
Yes, I'm ready.
Okay, thank you. Thank you. You're free to start your talk.
Yes. Good morning. My name is Anastasia Marushenko. I'm from Kyiv-Mohyla Academy, master student, and my topic is effect of chemical composition and thickness of magnesium zinc oxide films on a plasmon-phonon interaction in magnesium zinc oxide silicon carbide structures. Oh, just 1 second. Yeah. The goal of the work is twofold, is to investigate the plasmon-phonon interaction in optically anisotropic magnesium tin oxide silicon carbide structures by means of infrared reflection spectroscopy in the range of residual rays, and to demonstrate the application of this method for determination of physical parameters of the materials. Let's start off a little theory about the materials we will observe. Magnesium tin oxide has great features as a high photosensitivity, high photo and cathodoluminescence yield, pyro and piezoelectric effect. And the formation of magnesium tin oxide solid solution allows us to wider the band gap compared to zinc oxide, which allows us to shear the working range of lasers and photodetectors towards deeper ultraviolet. And in this work, we will review the magnesium ratio of 20%, which allows us to observe hexagonal structure of lattice and optical anisotropy in the infrared spectral range. Now, a little information about silicon carbide substrate. It has unique properties such as radiation and chemical resistance due to a strong ionic covalent bond. Also, this compound shows a strong anisotropy in the properties of plasmon subsystem. Sorry. So let's talk about the methods we use to calculate our spectra. As you know, polaritron is a quasi-particle that arises due to interaction of electromagnetic waves with electric or magnetic dipole incidation of a crystal lattice. And in our work, we will review surface plasmon polaritrons interaction, which arises due to coupling of surface plasmons and photons. So the calculation was performed using the model for dielectric permittivity with additive contribution of optical phonons and plasmons. And here we can review parameters we have used for longitudinal and transverse optical phonons and its damping coefficient, and for plasmons and its sorry, 1 second, for plasmons, yes, and its damping coefficient respectively. Here are the formula that we use for calculation of attenuated total reflection spectra. Here the formula for reflection coefficient, and indexes 1, 2, 3, 4 correspond to areas of prism, air, film, and substrate respectively here. Also, here are presented the parameters we used for calculation of infrared reflection spectra. The spectra was modeled according to the film thickness, airspace distance, angle. Here we presented the parameters for x equals 0.2 and for thickness of film equals to 500 nanometers. According to the studies made by my colleagues, other authors of this work, we found that with a thickness of film less than 100 nanometers, the effect of the film on specular infrared reflection spectra is negligible, and for the thickness more than 10 micrometers, the effect of substrate is negligible. And when the airspace is more than 5 micrometers, we cannot get any signal at all. Hereafter, we will review the results for x equals 0.2 in order to investigate the hexagonal structure and optical anisotropy, and with a thickness equals to 500 nanometers. Here are the first results. Frequency dependence of real part of dielectric constant. Here are, for the first curve, this is the curve for the film and for the substrate respectively. And here are the areas where polaritrons can be arising. This is important to know that the areas for the film and for the substrate almost do not overlap except for this little section. Here are the results presented for free carrier concentration difference in a substrate. We reviewed two cases with undoped and doped silicon carbide structure. So in doped case, we got more free carrier, higher free carrier concentration. Here we can observe that for doped substrate, we got a shift in extremums, only in a substrate, while for the film, the extremums remain the same, except for the frequencies, just the value was changed because of the angle 30 and 33 degrees, respectively. And in the next result, we review a slightly different case. We reviewed undoped and doped film. Here, results are slightly different because we got a shift in the film as it was in the substrate in undoped and doped case, but we also got a shift in one of the peaks for the substrate because of a plasmon interaction from the film with phonon interaction of a substrate. Here are presented the results that differ from the angles for the film and for the substrate. Here we can review that the less angle is, the more extremums we have. Here, for instance, there are areas where our surface is a little smoothed out just because the angle, just because of the value of the angle here. And for the substrate here is the area where this extremum almost disappears and the surface is almost smoothed out. And the last result we got is dispersion relation for our substrate and for the film. For the film, results are presented here, and for the substrate here. Now let's move to the conclusions. The surface polaritrons can be predicted in semiconductor magnesium zinc oxide structures using the model with additive oscillator contribution and cell-consistent parameters determined for magnesium oxide, zinc oxide, and silicon carbide single crystals for orientation E perpendicular to C. The excitation and propagation of surface polaritrons of phonon and phonon plasmon types are possible. The spectral ranges of the existence of surface polaritrons in ATR spectra registered as a function of angle of the IR excitation incidence at fixed light frequency and vice versa were obtained. Thank you for your attention.
Thank you for your talk. It was very interesting, and we are waiting for the questions. So maybe from the conference hall, any questions? Okay. I can see any questions from the conference hall and from online. So sorry, we don't have a question. Thank you for your talk. It was very interesting. It was very nice to see you on our conference. And so we're moving on.
Okay.
So our next speaker is Dr. Anton Litvinenko. And here he is. He will be offline.
I will be online.
Or he will be online, but we will broadcast you. Okay, just a moment. Okay, we can see you. Yeah, okay. What's your presentation? You have. Yes, it's on the computer. Yeah, just a moment.
Next session.
Yeah. And what session?
Composites and nanomaterials.
Composites and nanomaterials. Okay. Okay. Select your presentation. Okay, just a moment. We start broadcasting and to make all our participants see your presentation. This is it. Yeah.
Yeah.
Okay, so Thank you. You're free. You're free to give a talk.
Mouse.
A mouse only.
Okay, thank you very much. Good morning, dear colleagues. First of all, I would like to thank the organizing committee for the possibility to participate in this conference and to present here our work devoted to metal nanoforms.
Oh, it's okay. Sorry.
Okay, can I proceed?
Yeah, you.
If you are going to create a nanostructured metal, you essentially have two strategies to consider. First is to create discrete metal nanoparticles separated, and another option is to keep your sample of metal as a unitary whole, but to introduce some nanostructured peculiarities, some nanostructured nano-sized structure elements into it. It may be cavities, holes, or other elements. The latter approach could be using the latter approach. You can benefit both from from the properties of the nanostructured metal, and to enjoy some properties of bulk metals. Namely, it can be high electroconductivity, thermoconductivity, and so on. It is especially beneficial if you consider this your material for application where in which your nanostructure should be connected to something microscopic. It can be electrode, of course. It can be a heat sink when you need to drain extra heat from something, and it can be a catalyst which you want to immobilize on some surface, maybe to perform your desired process in flow mode, for example. The aim of this work was to elucidate the factors influence the structure and properties. Primarily, we consider electrocatalytic activity, of course, of metal nanoforms, so such porous metals, and their composites, and to evaluate possible prospect of application of such materials and then modification by porous substance. By other types of porous substances. Essentially, in order to create such materials, you need, anyway, technically, you need to create nanoparticles and of some kind and to fuse them to the structure. Fortunately, there are a number of processes in which such materials are built in one pot, in one process. It can be, for example, a decomposition of nitrogen-rich complexes of metals. Here, the forming metal is formed by excessive in nitrogen. It can be chemical or electrochemical dealloying of various alloys when you leach more active component from the alloy, and another component forms as a sponge. Sometimes it can be chemical, trivial chemical deposition from solutions, for example, for noble metals. And last approach, which we consider the most, is hydrogen bubble templated electrochemical deposition of metals at high current density. One should be aware of one significant peculiarity of such structures, of any nanoporous structure, is that when we deal with separated particles, its surface is always accessible. If we deal with long and narrow nanopores, the majority of their surfaces can be inaccessible due to diffusion limitations, for example, in solutions. So it can be beneficial to not just to create the minimal pores we can create by some means. It's beneficial to create hierarchical structure when the narrowest nanopores will be short and formed maybe in on the surface of larger nanopores to avoid these diffusion complications. It will be especially important for heterogeneous catalysts, for electrodes, and actually for a number of applications. One of the benefits of electrochemical deposition of nanoform is that this method generates such structures intrinsically. Here we present a number of samples generated deposited for various metals. You can see that the structure of the deposit is heavily influenced by the nature of the metal. But anyway, the general idea of the structure of such materials is the same. You have two levels of structure hierarchy. First is macro-sized. Modern reports tell that the primary factor governing this level of hierarchy is bubble sizes of the evolving hydrogen, and the second level is actually nanoscale, sometimes sub-micro scale level of hierarchy, governed primarily by the growth of the metal deposit itself. It can be dendrites, it can be just crystallites. Anyway, it should be admitted that you cannot fully decouple these processes. I mean, formation of micro-sized level and nano-sized level. For example, hydrogen evolution actually creates a local layer of alkaline electrolyte in the vicinity of the electrode. Is that does deplete hydrogen ions, which obviously influence the deposition of metal. And there are a number of such factors that where one process influences another process. So the theory of formation of this deposit, full theory explaining every peculiarity is yet to be proposed at the moment. We considered such materials formed from silver. Actual silver nanoforms for as electrocatalysts in reductive dehalogenation of a number of organic halogen-containing organic molecules. Why silver? Because silver is well known as an iconic electrocatalyst of these processes, and our findings showed that nanostructuring by this way helps to even improve the electrocatalytic activity of silver. The results, I mean, the potential shifts, if we compare nanostructured silver and smooth silver, vary from negligible to actually impressive, depending on the structure of the organic halide. And it should be especially noted that application of silver nanoform as electrocatalytically active electrode coating help to minimize the amount of silver necessary for creation of the electrode. Actually, it's 2 or 3 degrees of magnitude of the silver mass used in for creation of the working electrode, the working cap. If we try to vary to condition of depositing of silver nanoform, we can obtain we can influence the structure peculiarities, the sizes of elements, of the structural elements of the resulting form, the surface roughness, and to the less extent its electrocatalytic activity. Our findings show that varying of silver primarily the variance of the silver concentration in the electrolyte help to impact the diameter of craters, the thickness of the nanodendrites of silver within the structure, and surface roughness. However, peak potentials of reduction of organic halides, primarily we studied that from bromobenzene, is barely influenced by the deposition conditions, but currents within a cyclic voltammetry experiment vary significantly, and it changed in line with the surface roughness. So we can optimize the parameters to create the structure with the most developed surface with the highest specific surface area, and thus to create the most efficient electrode for performance of our process. It's not clear why nanostructuring influences the activity, the electrocatalytic activity of silver. To be honest, it's not completely clear why silver electrode, silver coating is one of the most efficient electrocatalysts of electrochemical dehalogenation. We tried to address these issues a bit, at least, and by the means of DFT modeling. And our very preliminary results suggest the importance of formation of silver carbon bonds with the of the intermediates forming in this process. Contrary to that hypothesis, which were proposed in literature, and which is also important for explanation of the nanostructuring impact. We didn't find significant differences of the process on various crystallographic facets of silver. So we should search further and to try other hypotheses. Maybe it's maybe some kinds of defects on the surface are responsible for the high electrocatalytic activity of the nanostructure. Our further efforts were targeted, were aimed to creation of nanocomposites based on the metal nanoform. Primarily by modification of metal nanoforms by various porous substances, mostly by particles of metal organic frameworks. The first approach which we used was actually trivial. We tried to drop cast suspension of MOF particle onto the surface of metal nanoforms and to dry it. Such materials can be considered to some extent as an inverted and alternative of common approach in which one takes metal nanoparticles and deposit it on the structure on porous carrier, or within pores, or on the surface of porous carrier. To be honest, we tried to further improve the electrocatalytic activity by pre-concentration of substrate by the particles of MOF on the surface. But we found out that it's probably not the case, allegedly due to above-mentioned problems with long, narrow nanopores. We found that MOF particle actually block the surface in the majority of cases. But as we found that the resulting nanocomposite was unexpectedly stable, the particles of MOF did not leach by solvents. Now we are trying to use it for another application, because MOF particles are catalysts themselves for a number of prospective processes, primarily for fine organic synthesis. And if we get such very stable composites, we can try it for flow chemistry, as a catalyst for flow chemistry processes. And it's ongoing investigation. Another approach which we can use in the case of tin nanoform for modification of its surface, but by another porous substance, is electrochemical oxidation of the surface. Tin surface being electrochemically oxidized in the appropriate electrolyte in the appropriate condition, result in formation of anodic nanoporous anodic tin oxide on the surface. This process is well described for tin foil, and we tried it for tin nanoform, and resulting in formation of another level of hierarchy on such structures. Preliminary results suggest that such materials are promising for photoelectrochemical applications. It should be especially emphasized that this tin oxide, anodic tin oxide, is semiconducting. It's not a blockade of the surface of electrode. We can still use it for electrochemistry. And interesting is that such oxidized surface showed various wetting behavior depending on the way of oxidation. If we compare annealed tin nanoforms, it was super hydrophobic. If we anodized tin nanoforms were super hydrophilic, which can found another maybe very unexpected but interesting applications. Just to conclude, creation of porous materials is important alternative to splitting materials into nanoparticles, but one should be aware of the problem of long narrow pores and to consider creation of hierarchical structure. We found and shown superior electrocatalytic activity of silver nanoform in reductive dehalogenation of organic halides compared to smooth silver, and found means of optimizing the structure for the best performance. And we showed the possibilities of adding another levels of hierarchy by modification of the resulting nanoform structures with porous substances of various methods and various kinds. Which can find a number of applications, and it's ongoing investigation. I hope to show you more results when we get it. And last but not least, I would like to thank and acknowledge the work of a number of people, of our collaborators, who participated in these works, and to acknowledge our funders. Thank you very much for your attention.
Thank you very much for interesting talk. And please, if you have some question, I welcome you to ask something about Thank you again for your presentation. So the next speaker will be Dr. Evgeny Gavrilyuk from the Lashkaryov Institute of Semiconductor Physics, NAS of Ukraine, with report entitled Raman Characterization of Coupon-Pure Synchronous C5 type nanocrystals obtained at different parameters of colloidal synthesis.
Давайте перезапустим, да.
Да.
Сейчас. Трансляция экрана. Не идет, смотрите. Сначала не идет.
Ладно. Maybe I can say when we have some small delay, a couple of words about Evgeny. He was a winner to, we can say, prizes. The first one was President's Scholarship for Young Scientists, and the second Humboldt Scholarship, for which he will work in Germany for 2.5 years. And he also shared with us some interesting facts from his biography, that he's interested not only in science, but also playing musical instrument and martial art.
The topic of my work is the Raman characterization of copper zinc clean sulfide type nanocrystals obtained at different parameters of colloidal synthesis. At first, I want to briefly introduce you this topic, make a short introduction. So, what is this compounds? Also, they know as CZTS, and for what they need. As we know, for the last few years, it's very increasing demand of the electricity power, and due to some ecological problems, it's lead to searching for new ways of obtaining electricity. One of the promising way is the photovoltaics, and as you can see from this graph, for the last few decades, it's exponential growth of the photovoltaics over the world. For today, more than 80% of solar cells are used the silicon as the absorbing layer, but it's need to understand that it's not so very good and promising as for the first look, because increasing of the amount of solar cells leads to increasing of the amount of material need for them. And due to the silicon is have a not direct band gap, it's very complete to obtain a really thin layer of silicon with good absorbing in the solar range. So also need to understand that producing of the silicon solar cells are not so environmentally friendly as we wish. That's why it's searching for new materials, and one of them are quaternary semiconductors. When we're talking about the quaternary semiconductors, need to understand that it's not something very complexity, but it's come from the really well-known binary semiconductors. So as you can see from this graph, from very known zinc sulfide, just replacing the element of the second group with elements of first and third group, and then replacing the element of the third group for second and fourth, we obtain a quaternary semiconductor. So why exactly CZTS compounds? Because they had a lot of advantages, for example, say low cost, earth abundant, and as a result, they are really cheap. So non-toxic, they had a very high absorption coefficient due to the direct band gap. and also their band gap are near ideal for photovoltaic. And just for a few years of researching of these compounds, the conversion coefficients already reached 12.7%. They had also a lot of perspectives because they can be obtained by the low temperature colloidal synthesis and in form of colloidal nanoparticle solution, and it's a way to use it in the third generation of the photovoltaics. But of course, as all of materials, they had not only advantages but some issues need to reach. It's multiple structural modifications, secondary phases, and a lot of intrinsic defects. Briefly about these issues, when we're talking about possible structural modifications, we need to understand that this material can be formed in 5 different structural modifications. Yeah. Okay, very briefly, first slides. Exponential growth of photovoltaics, what I'm talking about, as you can see from this graph, way from binary to quaternary semiconductors, and advantages, disadvantages. And I stop on this slide about the possible structural modifications. So as you can see, it could be formed on 5 different structural modifications. It's casterite, stanite, disordered casterite, PMCA, and sphalerite. But the most common for these materials is casterite, stanite, but exactly the casterite, but in 2 different forms. It's called ordered casterite and disordered casterite. But you need to understand that it's not disordering in the meaning of absence of crystal structure. When we call talking about the disordered casterite, we mean that in a specific crystallographic position, the atoms of copper and zinc not on their specifically places, but could randomly distributed over this position. So, of course, it's obvious that ordered and disordered casterite are very hard to distinguish with traditional X-ray spectroscopy. Also, the other issue is presence of binary and ternary secondary phases, and also it's very hard to distinguish with this X-ray diffraction due to the very close position of peaks. But these 2 issues can be reached with the Raman spectroscopy because there are 2 different positions for ordered and disordered casterite, as you can see on the left picture, and also all of the secondary phases have their characterization specific peaks positions. So that's why the Raman spectroscopy was chosen as a main method for characterization of these structures. And of course, we need to talk about in ways of obtaining these materials. So for today, it's very lot of different ways, Zolgale, spray pyrolysis, and others. But why we stop on the low temperature colloidal synthesis? Because at first, it's gives possibility to obtain a really nanostructure with a very low cost. Is very environmentally friendly method because we obtain the colloidal structures in water solution. We can obtain any volume of material. We can vary size. We can obtain nanocrystals with different size, just varying some synthesis conditions. And of course, the solution is already ink for the solar cells printing or printing other devices. Of course, it's again has some issues. It's influenced a lot of parameters on a resulting quality of nanocrystals, and that's why we decide to investigate some influence of some specific parameters on the structures. So our method are slightly different from that you can find in literature, and main difference is that most method described in literature means that on the last stage of your synthesis, you need to heat your solution something near 98 degrees for 10 minutes. But our modification give us possibility not to heat, because as you can see on this graph, the red curve is for the heated sample. There are no side of CZTS sample, but also some presence of secondary phase copper sulfide. Not heated sample show very good feature for the which correspond to the crystalline CZTS material, and no presence of secondary phases, and the sample are very stable in time. So we think it's a very good because when we exclude the heating, it's give possibility and gain to make this method more cheaper. So the other parameter is stoichiometry, because as I say, the very big problem is ordering and ordered and disordered esteride. And why it's happened? Because copper and zinc has very similar ionic radium, and they can very easily replace each other. With substitution copper with silver, which have a very different ionic radium, you can maybe something nivellates this effect. So as we can see, with a replacement of copper to silver, there are only a slight shift of the main characterization peak. It's due to they really have a very close position, but we think that we really replace these atoms due to the very different intensity of this characterization peaks. And the other parameter we investigate was adding some additional nanocrystal in synthesis process. And as you can see from this graph, adding of some nanoparticles do not lead to any significant effect. For example, nanoparticles of gold are very harmful for these materials, but adding, for example, nanoparticles of cadmium telluride leads not only to the better crystallinity of resultant sample, but also to the better stability of solution in time. So conclusions that the parameter of low temperature colloidal synthesis established, it's make possibility to obtain structural stable in time nanocrystals without the presence of secondary phases, and the adding of some additional nanoparticles leads to increasing of crystallinity and stability of materials. Thank you for your attention.
Thank you very much for interesting report, and I would like to ask our auditorium ask some questions. Maybe if there are no questions, I have a small not comment, but some remark or remark some detailized thing, maybe about how were obtained your nanoparticles. I mean, if you think about some shell on the nanoparticles, or it just were pure, I mean, to prevent agglomeration, if you will use for something.
As a stabilization, was use thioglycolic acid.
Okay.
It's we think it's form ligands on the surface of our particles.
So, okay, thank you again.
Thank you
for interesting talk. Okay, thank you. The next speaker will be Dr. Olena Fasenko from Institute of Physics, NAN of Ukraine, with report entitled Volume Wainwright Nanostructures for Surface Enhanced Spectroscopy of DNA Constitutives.
Dear colleagues, now I open my presentation and we'll start from one moment. Dear colleagues, my name is Rasenko Olena, and I'm representing Institute of Physics, National Academy of Science of Ukraine. And I will present today the topic which was made in our institute by a team of scientists from 2 departments. To begin more detail discuss the topic of my presentation, let me remind a few facts about surface enhancement spectroscopy in general, because it's one of the main topic of my presentation. The enhancement of optical process near the rough metal surface is known for about last 10-20 years. And this process are such as surface enhancement Raman scattering, namely SERS methods, surface enhancement infrared absorption, namely SEIRA methods, and metal enhancement fluorescence, and such methods as second harmonic generation. In my report, I will stop more detail on the surface enhancement Raman spectroscopy. Now, surface enhancement spectroscopy mainly due to the very limit of molecules that could be detected, and its some advantages, such as non-destructive and high signal noise ratio, wide to use for different biomedical applications. SEIRA and SERS effects cannot be explained very easy, and as a rule, it includes 2 main mechanisms, such as increase of electromagnetic field near rough metal surface or metal nanoparticles, and increase of a dipole transmission moment of adsorbed molecules on the metal nanostructured surface, if we speak about SEIRA methods, and increase of chemical process near rough metal surface, if we speak about SERS effect. As a rule, surface enhancement Raman spectroscopy is a surface sensitive technique that can help us to enhance signal from very small amount of molecules, cells, or different other biological objectives. And as a rule, it's realized near the metal surface. In our case, we propose absolute new type of substrates for realization these effects. In our work, we used an absolute new approach to realization of surface enhancement Raman spectroscopy. Namely, we suggested use volume waveguide nanostructures instead of metal surface. The goal of our work is to develop cheap but effective photonic crystals, structure formed by periodical distribution of nanoparticles in polymer matrix for highly sensitive detection of chemical and biological agents. The volume photonic crystal structures are fabricated using the holographic methods in original nanocomposite. And this methods was updated and developed by a team of Professor Smirnova, Tatiana Smirnova from our institute. Our work had several steps, such as theoretical analysis and design, which was done by Professor Volodymyr Fityo from Lviv, from National Polytechnic. And the next step, it was fabrication and characterization of label-free sensors. And after this, we testing the substrates for realization SERS effect. In the future, we plan to test it for realization SEIRA effect too. To reach this goal, it was needed to do the following tasks. The first, it was needed to provide computer design of such type photonic crystal sensors based on the resonance phenomena in the waveguide structure with braiding using real parameters of photonic waveguide structure in theoretical calculations. The next goal, it was improvement of polymer nanocomposites for the fabrication of such photonic crystal structure. Then we develop a refined one-step optical technology for formation of such photonic crystal structure in nanocomposites waveguide. Then was manufacturing of the photonic crystal waveguide structure prototypes with optimal grating waveguide parameters such as period of gratings, amplitude of refractive index modulation, thickness, and type of metal nanoparticles, which was in this polymer matrix. After this, we use test molecule. At this moment, we used only one type of molecules, timine, for realization Serre's effect on such type of nanostructure. On this slide, you have seen the distribution of field near the such type of photonic crystal waveguide nanostructure. As you can see, we have two substrates, its profile of substrate and the theoretical calculation of the field near this periodical substrate. If follows from the theory of planar waveguide for localization modes that the strongest field is concentrated in the layer with the higher refractive index. In our case, it's in the grating. In the homeostatic media, the research media with refractive index A, and the substrate with refractive index NS, the field decreases faster in the medium with lower refractive index. This increase can be explained by fact that when NS decreases the field in the substrate, decreases, but in our case, if you see on the figure 2, you will see that when NS decreases in the field in the substrate, decreases but increases in the research medium under the resonance. So for us, it's needed to do such substrate that the distribution of the field will be more moved in the field where absorbed our molecules, which we observed. It was established that the sensitive on both the wavelengths and angle increases when the refractive index of substrate decreases. The sensitive increases by factor about 2.8 times when the refractive index of substrate decreases from 1 point, as you can see from figure, 1.515 to 1.45. This situation is illustrated on this figure, which shows the distribution of the field in waveguide under the different type of refractive index. It's also theoretical modulation of distribution of the field near such type of periodical structure. And here, as you can see, the distribution of the field in this structure with normal incident is given on these figures 3A and 3B. And if you look on this figure, we combine the different amount of NS and A, and we can move the field. And our task was move this field, local field, in the place where our adsorbed molecules is located. There is a standing way in the grating due to the wave modes. Due to the two wave modes moving in opposite direction in the waveguide under the resonance. Here you can see holographic fabrication procedure. You can see experimental scheme which we used for realization this photonic crystal system with nanoparticle distribution. As I said in my previous slides, it was done by the team of scientists from our institute, from another department, which is this group is led by of scientists who was involved in this process by Professor Tatiana Smirnova. And as you can see from this slide, a conventional two-beam interference scheme based on the diode pumped solid-state laser with emitted wavelengths approximately 345 nanometers was used for holographic fabrication of such photonic crystal volume substrates. Two mutual pattern expanded coherent beams, which was diameter approximately 15 nanometers of equal intensity produced in interference pattern in the intersection plane, and it was samples was located in this place. And you can see from figure that the periodical of gratings can be adjusted to the angle between the recording laser beams. For example, for fabrication of grating with period of the gratings approximately 395 nanometers, the recording angle was, we use approximately 27 degrees. Because of symmetric beam configuration, the fringes of the grating, as you can see from the figures, is perpendicular to the surface of substrate. I will return back because I'm not finished with this slide. Due to the photopolymerization features of nanocomposite, the grating formation can be was monitored in real time by the diffraction of a helium-neon laser. As you can see from this slide, we used two lasers. One of them, helium-neon laser, was used for testing process. And the wavelength of this laser was 333 nanometers. The samples were exposed until the state value of the diffraction efficiency was achieved by approximately 80 to 150 seconds. Here you can see the schematic process of formation such type of photonic crystal nanostructures with nanoparticles. The volume periodic structure are formed as a result of diffuse redistribution of nanoparticles with polymer matrix upon exposure of the initial nanocomposite group to the UV interference pattern. The homogeneous photopolymerization of monomers and local moving of the nanoparticles from the region of high recording intensity to the region to the low recording intensity until the full consumption of the monomers are two base process occurring upon holographic explosion. As you can see from figure, nanoparticles using photopolymerization moved to the places with minimum, and in such way we received volume waveguides with different periods. It depends from angle, and it depends from lengths which we used in the holographic process. The next slide, we used, as I said, for realization Serres effect, we used testing molecule. In our case, it was thymine. At the first, it was interesting for us to try if this Serres effects will be realized in this volume waveguides structure. And it was interesting that we received enhancement of Raman spectroscopy of thymine on these substrates. And it was depends from refractive index. And it was shown that when the refractive amplitude of this refractive amplitude of modulation of this refractive index was higher, we received higher signal from Raman spectra of thymine, which was absorbed on such type of substrate. It's interesting because previously for realization of surface enhancement spectroscopy, Serres effects of Serre as a rule was using a different type of metal surface of different type of metal nanoparticles. We propose absolute another type of substrate. It is volume substrate. It's gratings waveguides. And as you can see from this slide, different bands of Raman spectra of thymine have different enhancement factor. So we can see that different molecular groups enhance by a different way. The next slide. Here, for us, it was interesting to check minimum amount of thymine which we can register on such type of substrates. And we made an experiment where we used different type of photonic crystals with distributed nanoparticles, as I call them volume waveguides gratings, and we used also we comparison this experiment only with polymer. Sorry, we have technical issue. Now I return back and I will move to the slide where I stopped. It was the last, not last, but I will continue from this slide. So I continue that I explain experiment of realization Serres effect on our volume photonic crystal system. For when we use the big amount of thymine absorbed on polymer and polymer with holographic with gratings and the distribution of nanoparticles in the polymer matrix, you can see enhancement, but not very big. But then we decrease this amount of thymine. You can see on the second figure, the red one, it is thymine on polymer without any gratings, and the black one, it's thymine on polymer with our gratings with distribution of nanoparticles in polymer matrix. You can see when we decrease the concentration of thymine, the enhancement factor increase. And the last slide on the bottom, you can see that different concentration of thymine on polymer and on gratings, because such amount of thymine on polymer we cannot, it was not possible to register. So here you can see that we receive very big enhancement factor of Raman spectroscopy for such type of system. The highest enhancement factor of Raman spectra of thymine molecules in our case was approximately 560 times, and it was realized for concentration of thymine approximately 0.5 in 10 in minus 9 gram. So it's less than nanograms of thymine. The dependence of enhancement factor from thymine concentration is shown on the this slide. As you can see, that it is very strong depends from concentration. When concentration is very small, we have biggest enhancement, and it's very decrease with increase of concentration. Now we plan to try use this photonic crystal system with nanoparticle distribution for analysis and detection of different type of viruses. It is very actual now, and we start this work. Here you can see conclusions. I will not read all these conclusions due to the time, because we lost a little bit time, but I can set the main results. That in our case, we propose a new type of substrate for realization surface enhancement spectroscopy, and we plan to continue realization this effect and to try to use the substrate for different type of applications. Thank you for your attention. If you have question, please ask me. If not, please send me by mail, and I will be glad to cooperate with you. Also, I invite you for cooperation. We have good international connection with different scientific group from different countries of the world. Also, we are specialists in infrared and Raman spectroscopy, and we have equipment for measurement these features of different type of molecules. So we are open for cooperation, and we are glad to cooperate with you. Thank you for attention.
Thank you very much for interesting report. And now we turn to the question. Are there some questions? Please.
I would like to ask such kind maybe of more general question regarding self. As far as I see conferences and other materials, it's primarily suggested, this method is primarily suggested for analytics, for determination, for
detection, yes.
But as far as I understand, that Raman spectrometer is a kind of expensive equipment, not so general. Could you please outline which maybe kinds, maybe cases for such determination of something? As far as I understand, you need to have large, expensive equipment, and somebody will transfer samples for detection.
Yes, but if we speak about equipment, as in any sphere of industry, equipment have different type. So now in the market you can find micro Raman, no, not micro Raman spectrometer, which is not very expensive, but it is not. It's more for industrial purpose. It is not for scientific purpose. But now I have seen that it is possible to buy very small equipment. Yes, it have some limitation in features and some limitation of sphere of application, but it is not very expensive. If we speak about equipment for research purpose with different modes, it depends. You have microscope or not connected. It is micro Raman spectrometer or it is Raman spectrometer. It's connected to confocal microscope or optical microscope or FM. Even that now you can find such type of system. Yes, it all depends from configuration of system, how many laser you used, because the system allows to use different type of wavelengths and lasers, and depends of this all conditions, the price will be changed. But as for me, no, have its industrial application, yes, because even for my opinion, now spectroscopy, infrared and Raman, not very wide use for medical application, for example, even for detection different bacterials and viruses. Now used another type of diagnostic methods, not spectroscopic methods. And for my feeling, these methods have very wide medical application. Why it is not used now in medical so wide? How I think it's needed. Maybe yes, it depends from price of equipment. From another case, maybe it depends that it needs specialists who can understand the spectra, who understand to have catalog of different spectra. But I hope, and it is my opinion, that in the future, maybe in several years, we will see altogether that spectroscopy, infrared, Raman will be very wide use for medical application too.
I understand you correct. That in principle, it's some kind of simplified next door medical laboratory and uses sample biological sample.
No, it's the same situation as playing of instrument, musical instrument. Yes, you need to have music instrument, but you need to study to have employers who can play on this instrument. Yes, who can to use this instrument for different purpose. So it's not need only to have equipment. It's a need to be able to have employers and medical employers who will learn this process, who will have adapted protocols of using this equipment from medical application. And it's need time. It's need not only money, but it need also time for learning of these people. But yes, I hope and I think that spectroscopy will be wide used for medical application now too. And Raman infrared spectroscopy used not only for medical application, it used also and for chemical application, because this methods, it's classical methods for analyze different type of composites, new materials which were synthesis, because you can understand what type of molecules groups are in this or other composite. You can analyze concentration dependence of different materials. You can identify different materials. So it's absolutely very wide application in different sphere of industry. And now also I know even in Ukraine, some big companies use this infrared spectroscopy, for example, for food industry, for control quality of production. So it's a very wide application. Thank you.
Thank you. And we also obtained a couple of questions from our chat. Please, Pavlo.
Thank you. First question is from Leonid Donkov.
Leonid, very active participants.
Yeah. He is asking, could you please comment about the mechanism of photon crystal surface and Hans-Raman spectroscopy?
As I show on my slide, near such type of substrate, volume substrate, we received enhancement of field, and adsorbed molecules is in the field which is higher. That's why we received enhanced Raman spectra. And how I explain this theoretical modulation of distribution of the field in the periodical structure. It was received by there is a standing wave in grating due to two wave modes moving in opposite direction in the waveguide and the resonance. That's why this distribution and this enhancement field, it's if you see, it is volume of our substrate. Here it is the interface with molecules, and if we will put here molecules, adsorbed molecules, they will receive the enhancement field, and in such a way they will have enhanced bigger and intensity of Raman spectroscopy.
Okay, thank you for your answer. And we have one more question from Professor Satimish Okulchansky. He's asking you, thank you for your presentation. Have you compared your data with the literature? The surface enhanced Raman spectra of timine are available. If yes, do you see any difference?
Yes, of course. We compare it with traditional Raman spectra of timine because it is not new molecules. It's traditional molecules. And why we use these molecules? Because we have experienced work with these molecules, and we use it for detection GERS, surface enhancement Raman spectroscopy on graphene, and due for the peace stacking between graphene and timine, it was very interesting results. That's why we this molecules very good have absorption on the surface, and that's why we use this molecule. And in the future, we plan to try to use this substrate for different type of molecules, and to see maybe some chemical process also will be present in this substrate. But in case of timine, we not see very significantly chemical process. It's more electromechanical enhancement, electromagnetical enhancement of our SERS realization of timine on this substrate, because timine is absorbed in interface where we have distribution of enhancement local field. In such way, this absorption of Raman spectra is bigger. But if you look even on the spectra of timine here, in our gratings, if timine is absorbed on gratings, we have small distribution of intensity and bigger enhancement of bands in the region of 500 until 1,500 centimeters minus 1, and very, very good recognition of very small bands. But as a rule, for such small concentration, it is smaller than nanograms of timine. It's impossible to receive such small amount of timine for traditional other substrates. But you can see that very good recognition for timine bands in a diapason from 1,300 to 1,500. Also here we have distribution of intensity in this region, which I show from 100 to 1,050. So we have enhanced intensity distribution between different bands of intensity, different molecules group enhanced by different way. But we didn't, I think, because it is new results, we only received it maybe 1 month ago, but in my case, I think that we not have here some chemical mechanism realization of enhancement. In this case, we have only realization of electrical field enhancement and absorbed our molecules in the interface where this enhancement of electrical field is present. So it's electrical, electromagnetic mechanism of enhancement of such effect. But in the future, maybe we functionalize these substrates and we will see what we receive. Thank you for your question.
Thank you very much for nice presentation and also for important contribution.
The next video?
Let's move forward to the next speaker. Yes, it will be Alexander Murmantsov from Taras Shevchenko National University of Kyiv. His report entitled as Spectroscopy of Underwater Electric Spark Discharge Between Metal Granules. Yeah. When we have a couple of minutes for some technical preparation, I can say some interesting words about our speaker. He is the holder of the third-degree diploma of the All-Ukrainian Competition of Student Works, and nowadays one of the executors of 2 international scientific projects.
Thank you for introduction. Thank you for introduction. Good morning, dear colleagues. Today I would like to tell you about my work topic. It is spectroscopy of underwater electric spark discharge between metal granules. This is outline of my presentation, and first of all, I would like to speak about motivation of our work. So, why is the investigation of underwater discharge between why the investigation of underwater discharge is of a great interest is to scientists and to in particular. First of all, this kind of discharge established himself as a good method for synthesis of metal nanoparticles. I mean, it was found that the colloidal solution with nanoparticles is the most suitable form for biological usage. For example, this substance are widely used in agriculture that as a high efficiency fertilizer that improves quality of seeds and accelerates the growth of household plants. On the other hand, its practical use in biology and electrochemistry. The underwater discharge established himself as a high-efficiency method for water treatment, surface treatment, and plasma sterilization. It is known that the solution of silver, it is known that the solution with nanoparticles, with metal nanoparticles, such as, for example, silver or copper, is have high bactericidal or antifungal or antibacterial effects. This can be seen by the presented pictures that shows effect of MNP of silver and copper
on survival of microscopy fungi such as alternate and penicillinum. So nowadays, the producing and generation of colloidal substance with nanoparticles is still need optimization process. It is still need to investigate the generation process and to improve, still need improve the characteristics of finished products. So about this work is focused on investigation of the main plasma parameters to investigate how nanoparticles are generated. So it's work focused on optical emission spectroscopy of plasma between discharge plasma between different granules such as copper, molybdenum, and iron or silver granule. About experimental setup. This is a setup for generation nanoparticles and colloidal substance by the underwater discharge. The voltage applied to the electrodes called the current flow along the chain of closely arranged metal granules in the stochastic switching mode. The typical parameters of voltage was from 40 to 200 volts. Current was about 150 amperes, and the pulse frequency was in the range of 0.22 kilohertz. As a result of erosion spark process, the generation of colloidal fraction can be observed. So this video shows the behavior of micro discharges into a discharge chamber. As one can see, and that must be noted, the micro discharges burning in the different point of discharge chamber. As a result, we must register the emission spectra from different points and must process this spectra and average to determine to accuracy determine the main plasma parameters such as electron temperatures that obtained by Boltzmann plot technique and the electron density that was obtained from full width of half maximum of some spectral lines. So about results of our work. The typical emission spectra of plasma between molybdenum and copper granules left and right graphs are present. It must be noted that aforementioned previously, the spectra were registered in different points of plasma due to its stochastic stage and non-stationary character of discharge. As one can see, that is naturally for underwater discharge, the H-alpha spectral line are presented in all spectra. All marked spectral lines for molybdenum and copper spectral lines were clearly selected and used in calculation of plasma parameter. This is typical emission spectra for plasma between silver and iron granules, and it must be noted that not only silver atomic spectral line, but also ionic spectral line of silver are presented in the spectra. So all the spectral line was were approximated by Floyd function. On the one hand, it is need to determine the radiation intensity of each spectral line to construct the Boltzmann plot. On the other hand, in such way we can determine the full width of half maximum of each spectral line, and taking into account the instrumental function of our optical device. So the obtaining values of electron densities in different plasma are presented in this slide. It must be noted that for the case with Cooper granules, we additionally obtaining the electron density from full width of half maximum of Cooper atomic spectral line 51, 53 angstrom, in assumption that the main broadening mechanism of this line is quadratic Stark effect. As one can see, the values obtained from for plasma between Cooper granules in both different weight are the same, and it validates the of the applied techniques and allows to assume that obtained values of electron density for other case, discharge between molybdenum and silver granules are determined correctly too. So the Boltzmann plots for construct on the base of molybdenum and Cooper granules are presented in this slide, and as one can see, the temperature is not significantly changed during the burning process of underwater discharge. It can be seen from the slope of the approximation line. So the temperature is 6,000 Kelvin for molybdenum for the case with molybdenum granules, and about 30,000 in plasma for discharge between Cooper granules. It must be noted that in the case of molybdenum granules, the temperature is lower, but it is it's sufficient to provide the necessary electric conductivity to possibility of burning of discharge. Due to insufficient of presence of necessary number of atomic silver spectral line in discharge between silver granules, it is impossible to construct a Boltzmann plot. But we use methods of intensity ratio between silver atomic and ionic spectral lines by presented equation. It must be noted that this equation is transcendental, and we must use the graphical solve method to determine the temperature, the excitation temperature in silver plasma. So the temperature is about 18,000 Kelvin. Let's conclude. So statistical data treatment was carried out to investigate the plasma of underwater discharge metal granules for different points of plasma emission due to the stochastic stage and non-stationary discharge. We use optical emission spectroscopy to determine the main plasma parameter such as electron density and excitation temperature. It must be noted that electron density obtained in two different ways for plasma in discharge between Cooper granules are the same, and it validates of the applied technique and allows to assume that values obtained for plasma between molybdenum and argentum granules are determined correctly. Also, it must be noted that the difference between electron densities in different plasma is correlated with ionization potential. The excitation temperature obtained by Boltzmann plots techniques on the base of molybdenum and Cooper atomic spectral line. For the case of silver plasma, we used the intensity ratio method between atom atomic and ionic spectral line to determine this temperature. It must be stressed that the temperature in the excitation temperature in plasma between molybdenum granules are lower than other, but at the same time it's sufficient to provide the necessary electric conductivity to discharge work. Oh, thank you.
Thank you very much also for your good talk. And please, are there some question for our speaker? Okay. There is one question from our chat. Please, Pavlo.
The author of this question is Victor Kisluk. Okay, thank you for your presentation. There are two questions. Concerning the metal granules, there are average size and shape of them, and do you initially treat them etching or sintering? Thank you.
What about sintering?
Okay, here you can read.
So, first of all, it's not important what the shape of these granules, but all of the presented granules, I mean, all four types, the ±1 have the same shape. About sintering, I really don't know. It is a question to provide to my colleagues who is provide this metal granules. Thank you.
Thank you again. If there are no questions, thank you. And I propose to postpone our coffee break till the end of the session and invite now our next speaker. It will be Dr. Yulia Bondar from the Institute of Environmental Geochemistry of the National Academy of Ukraine with a report entitled as Synthesis and Evaluation of Nano-manganese dioxide with layered structure as an adsorbent for selective removal of strontium ions from aqueous solutions.
Okay, just a moment.
Вот эти два пропустились.
Из-за так затянулось.
Не знаю, нет. Может, их не было.
Таких не было.
А может, потом будут выступать.
Почитал.
А время так затянулось?
Ну, затянулось, да. Но они все равно сбегают.
Кто-то включил. Да, это сейчас. Окей. Нет, ничего не надо.
I can, when we have a small delay, I can say some couple of words about scientific activity of Yulia Bondar. This activity connected with the development of absorbents for selective removal of heavy metals and radionuclides from aqueous solutions. And nanocomposite materials based on polymer materials and utilization of radiation technology for modification of polymer matrices are the essential part of the current scientific investigation of Dr. Bondar. So please start.
Well known that strontium radionuclides is one of the most hazardous radioactive fission products. All its long half-life period, about 30 years, high solubility and biological toxicity. Strontium and cesium radionuclides are among the most abundant radioactive pollutants in natural water and technological solutions. That is why the
selective removal of these radionuclides needs special attention to ensure radiation safety. Recent investigations demonstrated that nanosized inorganic compounds such as zero-valent metals, metal oxides, inorganic salts are very effective adsorbents for heavy metals and radionuclides due to their unique structure and surface characteristics. Among them, manganese dioxide species have been received significant interest because of their high adsorption capacity, low cost, and environmentally friendly characteristics. Normally, manganese dioxide is a complex and non-stoichiometric oxide with average manganese valence between 3 and 4. In scientific literature, term manganese dioxide refers to a number of mineral species, the main structure unit of which is the mangan O6 octahedron. These octahedral units can be linked by edge or kernel sharing in different ways to form crystals with layered or tunnel structure. On this slide, you can see that manganese dioxide species crystallize as nanoparticles or nanocrystals with various morphologies. There are many publications that show that manganese dioxide species are very effective adsorbents for strontium radionuclides. However, the correlation between mineral structure and adsorption efficiency is complicated by the fact that authors and researchers have not paid enough attention to the identification of the phase used. According to the literature, by bernicite manganese dioxide with layered structure and tryptamilan manganese dioxide with tunnel structure are the main candidates to be effective adsorbents for strontium radionuclides. The aim of the current work is the synthesis of manganese dioxide with a layered structure, bernicite type, its characterization and determination efficiency in removal of strontium ions from mono and multi-component water solution. For synthesis, we used very simple chemical method based on redox reaction between manganese ions in valence state 2+ and 7+ in alkaline medium. As a result of synthesis, we received fine dispersed black powder. Some images show that bernicite is formed as rounded 20-30 micrometer particles. However, at high magnification, one can see that these particles are agglomerates of more smaller rounded globules with a diameter of about 200 nanometer. And in the terms, these globules consist of plate-like units of 10 nanometer size. Bernicite is a common name for layered manganese dioxide formed by two-dimensional layers of edge-sharing octahedral units. An interlayer region is occupied by alkali and alkali earth ions and water molecules. Recent investigations allows to distinguish two types of bernicite minerals with triclinic symmetry and hexagonal symmetry. Hexagonal bernicite can be divided, can exist in ordered and disordered forms. These types of vernicid differ in architecture and chemical composition of the layers. That's why the activity will be different. On the slide, you can see the XRD diffractogram of the synthesized sample, which exhibits 4 broad asymmetric peaks. The position of these peaks and ratio of intensity coincide well with the disordered hexagonal vernicid named as turbostatic vernicid. All peaks, you can see that all peaks are broadened, indicated the formation of vernicide in nanostructured particles. Infrared spectrum confirms the formation of manganese dioxide with layered structure. Also, we investigated the surface properties of the vernicide using adsorption distortion isotherm of nitrogen. One can see that synthesized sample have a rather high surface area, more than 200 square meter per gram. And according to the average diameter, about 66 angstrom hysteresis loop isotherm type, the samples can be classified as the mesoporous material. Also, we investigate the adsorption properties of strontium ions. It should be noted that strontium adsorption did not reach equilibrium after 10 days, and the duration of the study was about 50 days. Strontium ions adsorption on the mesoporous synthesized vernicid can be described by a two-step process: rapid and reversible adsorption on the external surface, followed by much slower intraparticle diffusion and adsorption on interior sides. The second stage is very slowly processed and can be continued for several days or months before equilibrium is reached. Also, we investigate the effect of concentration of competitive ions on strontium ion adsorption. As a competitive ions, we choose sodium, potassium, and calcium ions because they are main component of natural water, tap water, and evaporated concentrate of the atomic power plants. We investigate the absorption using 5 model solutions. The first solution is monocomponent, and another 4 contains sodium, potassium, and calcium ions in huge excess compared to the strontium ions. One can see that synthesized sample can effectively remove strontium ions from monocomponent solution. Sodium and potassium ions have little effect on strontium ion adsorption. How the sample 2 and 3, how the presence of calcium ions leads to significant decrease of the adsorption capacity samples 4 and 5. However, considering the calcium ion concentration in the model solution the model solution is very high compared with tap water, typical seawater. That is why we can conclude that our synthesized bernicide have very high efficiency to remove strontium ions from multi-component solutions with high salt content. Also, we investigate the influence of solution pH on strontium ions absorption. One can see that increase of pH from 3 to 9 lead to increase of absorption capacity. And also investigate the desorption of strontium ion and repeated absorption. Desorption is a very important aspect of absorption process from practical and economical viewpoints, as it allows regenerating and reusing adsorbent for another absorption cycle. As adsorbing solution, we used acid solution and salt solutions. We investigated 3 samples with similar absorption capacity. The first sample, adsorption, desorption by acid, and the second cell adsorption. The second sample adsorption, desorption by acid solution, and soaking in calcium chloride solution, and then repeated adsorption. Third sample, adsorption, desorption by salt solution, and repeated adsorption. One can see that strontium-loaded bernicide could be successfully regenerated by acid and salt solutions. However, the later solution was preferable one from economic and practical viewpoints, as it not requires the additional stage soaking and calcium chloride solution. So bernicide can be used for repeated absorption after desorption experiments. So conclusions that we synthesize bernicide by redox chemical method, and bernicide synthesized as disordered hexagonal form, and it is very effective material for removal of strontium ions from multi-component solutions with high salt content.
Thank you very much for presentation. And now we are forward to questions. Are there some questions? So, and also in chat there is no question. So thank you very much for a clear presentation. And the next presenter will be Dr. Vitaly Cherny from the National University of Life and Environmental Sciences of Ukraine, with a report titled as Effects of VO3 and thorium doping on structure and optical properties of zirconium oxides.
Good afternoon, everyone. Are you hearing me?
Yes, we can hear you clearly and coherently. Yeah, thank you. Thank you. Just a moment, we stop our demonstration, screen demonstration, and you could broadcast your. Thank you. You're free to start. Thank you.
Thank you. Dear conference participant, let me to present for your considerations our work that was performed in collaboration of 3 universities, scientists from 3 universities, The work name is Effect of the Europium and Fluorine Doping on the Structure and Optical Properties of Zirconium Oxides. Our motivation for this work was had two goals. First one was practical application, and second one is scientific problem arise. About practical application, you know that zirconium dioxide, known as zirconia, was very popular about 2 or even 3 decades ago for dental application. And this zirconium oxide and also some complex zirconium oxide was proposed as gas sensors, also for nuclear waste confinement, also for light emitting diodes and plasma display panels, and for fluorescent markers for biological and medical application, and also for some other application. It's only part of the practical value of these materials. Scientific component of this work deal with the issue that substitution in cationic site in sublattice well elaborated for many oxide and not only oxide compounds. In the same time, substitution in anion lattice attracted less attention. So this issue we try to clarify in our work. So aim of the current work is to investigate effect of fluorine as anion substitution on the crystal structure, on the electronic bond structure, and on luminescence property as part of optical properties of the zirconium oxides. We applied experimental spectroscopic studies and also theoretical calculations. A few words about zirconium oxides. We can divide them on the complex oxides like phosphates, silicates, zirconates, et al. And simple oxide, well-known zirconium dioxide. Interesting that although different chemical composition of these materials, they possess similar physical properties, similar structure peculiarities, and have similar features in electronic structure. Some samples were synthesized on the chemical faculty of the Taras Shevchenko National University of Kyiv. There was phosphates of zirconium prepared by high temperature melt growth, and also zirconium dioxide was used as model object, and it was prepared in pure and doped form by solid state route. About methods, we used studies of spectroscopical properties with excitation from vacuum ultraviolet up to visible region using synchrotron radiation at Hazelab Daisy, Germany, and ultraviolet and visible excitation was performed in Kyiv. And third part of the methods is about DFT-based density functional theory-based calculation that was performed using VN2K package. Let's consider some features of the crystal structure of the object. As example, we have 3 phosphates with different composition, but they have similar peculiarities, like green polyhedra. It's a polyhedra of zirconium OX octahedron for these phosphates. X can be from 6 up to 9 in different compounds of zirconia. Also, we have here phosphate groups, but it typical only for phosphate. Obviously, for silicates, there are no phosphate groups. So we can say that presence of zirconium or X polyhedra is common feature of the zirconium oxide compounds. A result of calculation, here we present partial densities of electronic states for Z3 compounds of zirconium phosphate. We have also similarities in this density of states. Green curves on 3 figures represent zirconium D states, and these zirconium D states are at the bottom of conduction band. Also in light blue color, you can see oxygen P states that form top of the valence bands. We know that transition from the top of the valence bands to bottom of the conduction band determines the optical properties like absorption of light, like emission of light by these compounds. In case we have some luminescent active ion like bismuth or rare S ions, we have additional states inside of band gap.
I'm sorry, Dr. Chorny, can you stop for a while, because we got the translation to YouTube and to our conference hall all stopped. Just a moment, we will restart it and let you continue. Thank you.
Okay.
Sorry for interruption. You can continue.
Okay, thank you. I don't know when it stopped, so I just repeat that for all 3 compounds of this picture, we have common features that correspond to valence band top part that has oxygen peak character, also bottom of conduction band that has zirconium D character, and for compounds with luminescent active ions like bismuth, like rare S or transition metal ions, we have additional states inside of band gap or near band edges of conduction band or at valence band. These features of the electronic structure reflected in the photoluminescence spectroscopy measurements. On the base of analysis of the literature and analysis of the crystal structure and analysis electronic bond structure, we can attribute some bands in the excitation spectra to zirconium OX polyhedra or bismuth OX polyhedra. In case of zirconium OX polyhedra, we have deal with so-called charge transfer processes from zirconium to oxygen. In photoluminescence emission spectra, we also have bands that can be ascribed to either zirconium or X polyhedra, or if we have some additional luminescence ions, we have additional bands in visible region. This band for zirconium compounds also have charge transfer character. But in this case, zirconium X isn't zirconium O6 like in regular zirconium phosphates, but maybe with oxygen vacancies. In visible region. In order to deal with some simple compound, because phosphates isn't so simple, we decide to study zirconia dioxide. It is known that it has 3 polymorphs only monoclinic one is stable at room temperature, but tetragonal and cubic can be stabilized by creation of some oxygen vacancies by doping of compound with yttrium, scandium, or other 3 or 2 valent ions. Also, interesting effect have size of the particles in the of the compound. It is known that nanoparticles, when they have sizes below 24 nanometers, possess only tetragonal or cubic phase. So when we decrease size of the particles in compound, we can stabilize either tetragonal or cubic phase of zirconia. In this work, synthesized zirconia was doped with fluorine, and we see that in this part, near 30 degrees on powder X-ray diffraction patterns, we observe some additional peak that corresponds to cubic phase of zirconia. So adding of fluorine promotes stabilization of this cubic phase of zirconia. So this first effect on the structure of fluorine adding to zirconium oxide. The next one, when we have only doping with fluorine, on this scanning electron microscopy image, we have rounded particles about 1 micrometers. When we co-dope zirconia with fluorine and europium, we have much smaller particles that are about 100 nanometers. Also was performed a calculation of partial density of states for monoclinic zirconia with some defects. The top part of the figure, you can see partial density of states for pure ideal monoclinic zirconia, only zirconium states and oxygen states observed. When we introduced fluorine ions into the compound, we observe appearance of fluorine states, but at the bottom part of the conduction band. There are also two different co-doping situations with yttrium and fluorine and europium fluorine. We have some additional states corresponding to cationic substitution. In case of europium, we have states in forbidden band, inside band gap. What we can say about this result, that fluorine directly not involved in the optical transition. There are no states of fluorine, neither here, neither there. And luminescence spectroscopy, also result of electronic band structure calculation reflected in the luminescence spectroscopy. We have here 4 different samples with pure zirconia, zirconia with fluorine, zirconia only with europium, and co-doped zirconia with fluorine and europium. In excitation spectra, we observe that this band disappeared when doped with fluorine. This band corresponds to oxygen vacancy is in this compound. Also in europium doped compound, we observe some additional lines in excitation spectra and in emission spectra that correspond to rare S ion europium. And when co-doping was performed, that we can see that here some so-called charge transfer band from europium to oxygen observed, also emission lines of europium observed, and in photoluminescence emission spectra, decreasing of this band in blue spectral region observed, and increasing of intensity of European emission lines also observed. From the luminescence spectroscopy results, we have good result for practical application of our zirconium co-doped with European fluorine. The black curve here represents the dependence of European intensity, of European luminescence intensity on content of fluorine. So when we increasing fluorine in the structure up to 8 molar persons, we obtain a much higher, about 1 order higher intensity of the luminescence of Europium ions in the zirconium oxide. So it's the most interesting result of our studies. And also when we add in some fluorines at the starting points, the structure possess more symmetrical surrounding on the Europium, but with the increasing of the content of fluorine in the structure, decreasing of the symmetry observed because ratio of intensity increase with increasing of fluorine. This results indicates that fluorine acting on the Europium luminescence mainly by the structure changes, by the changes in the crystal structure of the zirconia. We think that such effects should be observed also for complex zirconium containing oxide. So we plan to continue our work in this field. And some conclusions were in talk, and some are on this slide. So we, from calculated partial density of states, see that bottom conduction band have zirconium D character, and top of the valence band have oxygen P character. That means that these two elements, zirconium and oxygen, take play active role in optical transitions. All the luminescence bands in the excitation spectra and the emission spectra can be ascribed to either zirconium OX polyhedra, or with regular or with defects like oxygen vacancy in zirconium OX polyhedra. And some bands can be attributed to ions like bismuth. And it is found that fluorine promotes structure transformation in zirconia oxides. Thank you for attention.
Can you please tell what is the main benefits of your luminophore? Because as I can see, you just showed that it's in UV spectra, and is it intensity benefits or quantity photons emission benefits or something like this?
In case of VUV excited luminescence, that materials can be used for plasma display panels because they are good absorbers when xenon discharge take place. Emission lines of xenon discharge take place. About benefits of the zirconium luminophores, when we added some small amount of fluorine into zirconia doped with europium, we obtain great increasing of luminescence intensity of europium, and in literature, zirconium doped with europium was numerously proposed to application in as luminescent materials. So main advantage is increasing of the emission intensity.
Did you compare it with some other luminophores, like which use in LEDs or something like this?
Not yet. Not yet. We didn't compare it with commercial luminophores. It's hard to perform. Advantage is increased. I'm sorry. Because our samples in powder form, it is hard to measure the absorption spectra. So it's hard to estimate the quantum efficiency.
Thank you for your answers.
Thank you very much. And we have one more question which we obtained from our chat. This question comes from Victor Kisluk, and he asks, zirconia is known to be widely used as oxygen sensor, lambda sensor. Do you consider any research in this direction? It would be promising. Thank you.
Thank you for the question. We know that group in Estonia or Latvia, I don't remember exactly, actively study this zirconia as oxygen sensor. But for our group, the luminescence of zirconia as luminophore more attractive at the current at the present. So maybe later we can consider to use our samples as oxygen sensor, but not in this year at least.
Mm-hmm. Thank you again.
Thank you.
Mm-hmm. And now we will go forward, and the next speaker will be Dr. Ruslan Sergeyenko from Physico-Technological Institute of Metal and Alloys of the National Academy of Science of Ukraine, with a report entitled as Zirconium-based amorphous and nanostructured ribbon.
Good day. Now, can you hear me?
Yes, yes, we can hear. And just a moment, just make some couple minutes. Let us make good video signal.
Hello, everyone. Welcome to our nanoscale physics section. Please welcome our first speaker, Dmitro Harbuz, who is a PhD student from Technical University Kharkiv Polytechnic Institute. He will present his work on cluster source of vacuum, ultraviolet, and ultrasoft X-ray radiation, from basic research to practical application. Dmitro Harbuz, please, you are welcome to start your report now.
Okay. So the topic of my report have been already announced. So how do I? Nice. Okay. My work is based on original source of vacuum ultraviolet and ultrasoft X-ray radiation. There are only 5 of this kind in the world. Its operation principle is based on the electron excitation of clustered supersonic gas jet expanding into a vacuum. The use of different gases and the variation of the cluster sizes or condensate in a jet, as well as the changes of parameters of electron beam, allow us to achieve the wide variation of intensity range and spectral distribution of the source. The area of application of vacuum ultraviolet and soft X-ray radiation is very wide. Some of the areas presented on the slide, it can be photolithography, physics of nanoplants, photochemistry and photobiology, photocatalytic layers, surface modification, and surface cleaning. On the basis of our source, the more than 200 scientific works have been published. Our sources have been designed to simulate the transatmospheric radiation of the sun. On the slide, you can see the transatmospheric radiation of the sun in a range from 1.24 nanometers to 115 nanometers as the red curve, and the spectrum of our source by using the indicated mixture of argon, helium, and krypton as the blue one. The parameters of electron beam is electron energy 1 kilo electron volt, electron emission current 25 milliamperes, and flow rate of gas jet is 1008 standard cubic centimeters per minute. If it's necessary, the irradiation of our soul can exceed the radiation of the sun on the Earth's orbit by 10-20 times. So it allows us to proceed the accelerated tests. The result of my work is separated into two parts. The first one is devoted to the research of Kapton H polemic film, and another part to the properties of composites in film gas nanosensors. Our samples were located in a test chamber in a pressure of 10⁻⁴ power Pascal in the distance from 70 centimeters from the jet axis. The spectral region goes from 1.24 nanometers to 110 nanometers, and the integrated flux of vacuum ultraviolet and soft radiation was 2 on the 10⁻⁴ power per square centimeter. The radiation was corresponded to the 100 hours and 500 hours and Earth orbit. Kapton films is material which is highly resistant to both the changes in the environment. It retains its mechanical and electrical insulating properties in the wide temperature range. It does not dissolve into oils or in the organic solvents. That's why Kapton H is used in the critical low temperatures conditions in space exploration and aircraft construction. One of the possible example of using of Kapton H is a space sail. It is very important to know how long the sail will retain its mechanical properties under action of outer space vectors. Therefore, we used the 75 micrometers thin film of Kapton H after the exposure to the vacuum ultraviolet, surface radiation, and EMRS radiation in the range from 215 nanometers at the temperature of 293 Kelvin after the radiation in the condition of anaxial tension, and we measure the changes of its mechanical properties. On the next slide, you can see the stress deformation curve for Kapton H and some parameters of this study. Our experiments have proved that Kapton H is highly resistant to the sun radiation. However, we found out that despite the small part of vacuum ultraviolet and soft X-ray radiation in the spectrum of the sun, its effect on mechanical properties of the film is most evident. While the increasing of limit of photoelasticity and the action of the EMRS radiation is only due to the heating, the changes of limit of photoelasticity and decreasing of highly elastic deformation of the film under the action of vacuum ultraviolet and soft X-ray radiation in a range from 1.24 to 117 nanometers is only due to the radiation itself. We suppose that two processes occurs in the film: the rupture of macro chains and intermolecular linking that provides such results. The next part is devoted to the features of TSNQ gas nanosensors. We use TSNQ based salts as sensor material because of the feature of its crystalline structure. TCNQ crystals grows as crystals or pellets formed by stacked packed TCNQ molecule, as you can see on the slide. Also, you can see the model sample obtained on the glass substrate. It's optical image. The important feature of TCNQ is that high conductivity entropy between the direction color and perpendicular to the stacked axis. It can reach the amount of 10 to the third power. It is very important for us since our sensors are electrical sensors. We obtain our sensor device by compiled chemical deposition from the saturated solution of TCNQ from acetate trial on the textile substrate followed by copper. The part of copper foil is removed from the substrate in the formed gap. The multistructure of nanocontacts, which obtained by collision of uniform crystal of Coulomb TCNQ, is created. In our deposition regimes, one of the two polymorphic phases of Coulomb TCNQ can be obtained. The main difference of these phases is the distance between the kinetochromes of these molecules. By this factor, the difference of the conductivity of such phases can reach the amount of around 10 to the second power. On the next slide, you can see the SRD pattern of our model samples. We have found out that with all deposition modes in our deposition regime, the only first phase of Coulomb TCNQ is obtained, as there was no any evidence of the second phase. On the upper image, you can see the surface morphology of the layer crystals of Coulomb TCNQ. As you can see, it's pretty uniform. You can see the thickness of each layer about different some nanometers, and also you can see the nanocontacts which obtained by collision of these crystals. Each such type of nanocontact can serve as sensor itself. The amount of such type of nanocontacts is around 10 to the fourth power on each sensor device. That provides a very high intensity of the response. We record the response as potential drop, which occurs on the resistor connected in series with the sensor itself. While the traditional semiconductor sensor shows the simple response at the action of the gas agents, our response is difficult, it is complex, and it contains two maximums of the exposure and relaxation phases. We have proved that our sensors are sensitive to the different strains of Helicobacter bacteria in the human body. On the image, you can see the typical response curve of the different patients.
Your screen broadcasting in front of. Sorry.
On the slide, you can see the typical response curve of the different patients with the typical state of metabolic system. The first one, the blue one, is for healthy person. The second one is the person with the presence of Helicobacter pylori non-cancerogenic strain, and the green one for the person with the presence of Helicobacter pylori cancerogenic strain and with ocular dyspepsia of the body. We wanted to know how exactly the ultraviolet radiation influence on the properties of our sensor devices. The reason is that ultraviolet radiation is widely used in medical application for the disinfection of the instruments. Another methods of disinfection, such as cleaning with some solvents or heating, is not applicable in our case, since our sensor devices are not resistant to such influence. We have located the object in the test chamber that I have talked before, in the distance from 70 centimeters from the axis, and rest him there for 4 hours. After the exposure, we measure the response of the sensor device and the action of rest gas, and we found out that the intensity of the on the slide you can see the blue curve as the initial one, and the green one and blue one, after the exposure of ultraviolet radiation and surface radiation in range from 1.24 to 170 nanometers. As you can see, the intensity of the sense device have decreased in 2-3 times. Also, you can see that the response curve became more sharper, but the shape smooths with the consequent tests. We suppose that the changes in intensity is caused by the recrystallization or changes of morphology of the sensor surface and the action of the ultraviolet radiation. The changes of the shape is most likely caused by the effect that ultraviolet radiation make to the absorbed gas molecules. And the action of the radiation, the absorbed gas dissolves from all the vacancies of nanocontacts, and then we can observe the process of recombination and absorption-dissociation mechanism and the action of the blast gas more clearly. So, to conclude, I want to say that during this work, we measured the mechanical properties of component film under the action of EMRS, vacuum ultraviolet source radiation. We have shown that despite the small contact of vacuum ultraviolet with source radiation in the spectrum of the sun, its effect on mechanical properties of polyimide film is most evident. We have studied the structure and morphology of currently sent using film gas sensors. And we show that vacuum ultraviolet source radiation influence on the response curves and the actions of blast gas of currently sent using film nanosensors. Thank you for your attention.
Mr. Harbut, thank you for so interesting report. Any questions? Okay. Thank you very much for your presentation, and we look forward to your future insightful pieces of work. Our next speaker will be Dr. Elena Zhitlukhina from Galkin Donetsk Institute for Physics and Engineering, NAS of Ukraine. Her report is about anomalously enhanced thermal noise in quantum rings. Please welcome Elena Zhitlukhina to share the latest results with us.
Нет, я вам прислала.
В какой тебе? Nanoscale сейчас?
Выше.
Это?
PowerPoint. Выше. Хорошо. Теперь не осталось.
Controllable charge flow in electronic conductance is central to many areas of science and technology. Nanoscale devices are good candidates for this role, since their energy spectrum can be easily designed by using low-dimensional quantum-confined structures as quantum dots, quantum wires, and quantum ring, the main subject of this talk. And their response to external fields can be well managed. Two main questions we concentrate on this research. First is generation of high-order harmonics in the currents flowing in the discussed quantum ring, coupled to one or two reservoirs with a voltage periodic in time. And the second issue, physical mechanism of unexpected thermal noise in a quantum ring observed last year experimentally. Why we are interested in high harmonic generation? This effect is mainly known as a non-linear optical process in which frequency of laser light is converted into its integer multipliers. Since the initial radiation is monochromatic, and after transferring an object with non-linear properties, we get an outgoing mixing of waves with different harmonics. The analysis of the outcome is usually based on the fast Fourier transform in the frequency domain shown here. Periodic microwave modulation technique applied to different mesoscopic systems of reduced dimension is a powerful experimental method for generating high harmonics and realizing novel quantum objects with exotic out of equilibrium properties. In the desk book for designers of practical microwave devices, we can find schemes of microwave harmonics generation circuits which are complicated. There is also another problem. The harmonic have a different phase angles, and due to their mixing, there occurs phase angle interference in each spectrum of harmonics. Hence, if we need a particular harmonic signal of a good quality, a good reliable filter should be used to reject undesired signal. In this work, we show that a simple nanoscale ring with a phase coherent transport, shown here, can serve for effective generation of high-order harmonics of a microwave signal. Fundamental quantum laws guarantee existence, identifications, and more stability under change of the system states. Standard mesoscopic transport approaches may be applied to the system formed by a nanoscale phase coherent quantum ring with one or two leads coupled to microscopic reservoirs. The most general theory valid in quasi-static and time-dependent situation is that based on non-equilibrium green functions. For the case when interaction effects can be treated on a mean field level, this methodology is reduced to the well-known Landauer-Buttiger formalism. We are following this approach. The wave function for an incoming quasi-particle wave function carrying unit flux look as the quasi-particle wave function in a quantum ring includes the magnetic flux, it's shown here. For a sinusoidal magnetic flux, look as it follows that an electron with energy E emitted from the left lead is transferred into the right lead, and its energy is changed to E sub n. What we are interested in is the Fourier analysis of persistent currents in the quantum ring and the lead current. The left figure demonstrates the presence of high harmonics for a quantum loop with a signal current lead. The inset shows difference in the two loop currents in the time domain. The current bias is constant, magnetic flux is sinusoidal, dashed lines correspond to a constant magnetic field. The right figure shows the presence of high harmonics for a quantum loop with two current leads. The inset shows the normalized differential conductance of the device in the time domain. The natural question is if quantum phase coherent rings can be fabricated at the actual nanoscale level. The answer is positive. In a preprint appeared at the end of the last year, such a ring was fabricated by contact of two semiconductors with a two-dimensional conducting plate at their interface. The temperature was 4 Ks. Using the gate voltages, the authors could switch the device from a conducting nanowire to an asymmetric nanoscale ring. They performed measurements of electrical fluctuations and found good agreement with the theory in the first case and a strong disagreement in the second case. It was unexpected, and our next task was to explain this finding. The authors compared their results with the well-known statement Johnson-Nyquist noise. It's proportional to the environmental temperature, namely. The power spectral density or voltage variance for a resistive component is given by a formula. The resistance was verified many times, and it does work. Why is it not valid in the case of a quantum ring? Our explanation uses to the presence of inductance in this case, and its lack in the case of a nanowire. The generalized formula for the power spectral density of the voltage noise for components having partly reactive response as capacitors or inductors look as, where Z is the frequency-dependent complex electrical impedance. We can show that in this case, the well-known Johnson-Nyquist formula for the noise is transformed to the relation, its origin of the difference between experiment and Johnson-Nyquist theory. Conclusions. In this work, we have shown that nanoscale quantum ring can generate high-order harmonics and explain why experimental results for thermal noise strongly differ from the Johnson-Nyquist theory. Thank you for the attention.
Elena Petrina, thank you for your very interesting report. Any questions? Okay, and thank you again and good luck. We continue our session, and the third speaker is Oksana Kaplak, senior researcher from Taras Shevchenko National University of Kyiv. The subject of her report is magnetic caloric effect in multi-layered gadolinium films with different substrate orientation. Oksana Kaplak, please, you are welcome. Start your report now.
Okay, thank you very much. Can you hear me?
Yes, we can hear you, and we see your presentation.
But we did you see my presentation? Okay.
Yes, we can see it.
Okay, let's start. First of all, I would like to thank the organizing committee. It's a big thanks for the great job. You can organize this virtual conference, and it's my first opinion to attend on the virtual conference. So thank you. Today, my talk will be devoted of magnetocaloric effect in multi-layered gadolinium film with different crystallography orientation of substrate. Okay, how I can move to the next page.
You have any problem, Oksana?
Yes, slightly, because I can move my presentation.
Click on your presentation, just it must
to activate the window with your presentation. Click on the
click just on the presentation somewhere in the center of the now.
Yes, I tried, but nothing. Okay, finally. Can you see now?
No. You stopped your screen broadcasting.
Please.
Oh, I'm sorry. I'm sorry. Try again.
Yes.
Try again, please.
Okay, now.
Yes, we see the outline. We see the first page, outline.
Okay, nice. Okay, let's continue. My presentation, in my presentation, I will show some introduction to magnetocaloric effect and our experimental results that containing possibility of tuning magnetic entropy and relative cooling power due to the changes of crystallography orientation of gadolinium film. So, the magnetocaloric effect can be defined as the absorption or emission of heat when magnetocaloric materials are subjected to a change of magnetic field. Refrigeration system exploit a material's entropy change due to the variation of external parameter. In our case, it's magnetization or magnetic moment to absorb and release energy. The so it means magnetocaloric effect, was first observed by Warburg more than 100 years ago. But this effect attracted great attention of scientists and industrial team just after discovery this effect at room temperature, because before this it can be observed just at very low temperatures at milli-K. A number of published papers per year on the magnetocaloric effect has grown at exponential rate in the past years because some giant magnetocaloric effect was observed in Heisler alloys. Magnetic caloric technology can be used in both in cooling application, such as refrigeration, and air conditioning in the heating application, like water heaters and clothes dryers, as you can see on this slide. It depends in which part of this cycle you can use. So experimentally observed, this effect can be observed as reversible change in temperature delta T, or in changes of magnetic entropy delta S in adiabatic or isothermal process. In basically some alignment of magnetic spin system can be observed in some temperature range of in entropy depending scale at phase temperature of phase transition. For magnetic materials, for ferromagnetic, it's Curie temperature. For antiferromagnetic, it's Néel temperature. The maxima of magnetic caloric effect can be seen. A lot of materials, so basically, again, all materials demonstrate magnetic caloric effect. It just depends on the value. It can be 0.1 or 10K. And you can see a lot of different compounds, such as Heisler alloys, such as bulk gadolinium, some lanthanide family, manganese, gallium compounds, etc. This value on the scale, it's adiabatic changes of temperature. The maximal was found for iron or rubidium at about 20K and temperature 310. But for practical application, these materials, not all, of course, materials can be applied, because some how to say, some rules must be. First of all, it's Curie temperature. It must be near working temperature. In preferable at room temperature, of course. Large temperature differences in the vicinity of phase transition, no thermal or magnetic hysteresis, large cooling power, low specific heat and high thermal conductivity, non-toxic, some resistant to corrosion, mechanical properties, goods, etc. And why gadolinium? Gadolinium, it's a good candidate because it has big magnetic moment. It's over 70.6 magneton Bohr. Its material has phase transition to close to room temperature. And Vitaly Pecharsky already find gained magnetic caloric effect in compounds based on gadolinium. So it's open it's open way to application in these materials as magnetic caloric. Yep. But we find another way for using this gadolinium as thin film as a part of multilayered structure. Why? Because additional parameter controlling this effect can be found as a strain of the film on the substrate, mechanical stress, thickness limitation, etc. And we used these heterostructures that contain several layers, as you can see, MgO substrate, buffer wolfram layers, gadolinium thin film, and was on the top again wolfram for good mechanical properties on the top, and oxidation proof. We used several type of samples with different thickness of gadolinium layers. You can see that we have three type of samples with 100 nanometers and three type of samples with 300 nanometers, but with different orientation of substrate, MgO, I repeat. Why? Because this orientation has a different lattices parameter, and
Anna, we can't hear you.
Oh, I'm sorry?
Anna?
Can you hear me?
Yes, now we can.
Okay. Let's continue. Yes?
Yes.
Okay. So this is our sample, and first of all we used local analysis by energy dispersive X-ray analysis was done, and you can see the typical spectrum. All of the main elements were detected, and we used different accelerating voltage of electron beam for reaches each level of heterostructure, and uses the formula by Kanaya Kayama for extract the penetration depth and thickness of the layers, and this value was in a good agreement with estimations of thickness by deposition time. Okay, and second step, we analyzed bulk structure by X-ray diffraction, and you can see spectrum for our samples, and bottom it's a theoretical spectrum of gadolinium pattern. It was need for compare our results with some peak with position, reference position, and you can see that this for different samples this peak shifted, intensity reduced, but half full width at half maxima verified too, as you can see in this normalized picture. This according to the well-known formula, we calculate the internal stress, and it was maximal for a sample with thin gadolinium film, and higher value was observed for samples with orientation 111. For sample with orientation 110, amorphous film was observed, and it's impossible to calculate external stress. Okay, and third step, it was measured the magnetic properties of the sample, and you can see the magnetic attestation. First of all, we measured temperature dependence of magnetic moment. You can see this three regime. It's named FEC, ZFC and FEV. FEC, it's field cooling, ZFC zero field cooling, and field warming. It was needed to estimate magnetic hysteresis, and you can see that this line is completely the same. It means that no magnetic hysteresis wasn't observed at phase transition temperature. The value of this Curie temperature was found as deviation of magnetic moment, as it is minima. It's equal 295 K, and was more the same for all these samples. And around this temperature, we measured series of isothermal curve temperature dependence of magnetic moment. Each curve was measured at a fixed temperature in diapason in regime between 200 K and 350 K. And next we calculate magnetic entropy by Maxwell relation, where changes of SM, it's a magnetic entropy, can be described as an integral deviation magnetic moment temperature dependence on magnetic moment. So second step, we plot some error plot. It's the plot is based on Weiss molecular theory, assuming a proportionality between the intrinsic magnetic field of the ferromagnet and its magnetization, and generally based on Errett-Knox equation. And this parameter you can see gamma and beta. It's a critical parameters associated with magnetic susceptibility and saturation magnetization respectively. And you can see for the same samples or with the same orientation but different thickness of gadolinium, this shape of this error plot is different. It means the influence of strain and slightly non-oriented magnetic structure on the interface. Okay, and we plot temperature dependence of magnetic entropy for these samples, and you can see this dependencies of the for the samples at 5 Tesla. Maximal value was observed for sample with 1110 and thickness of gadolinium 300 nanometers, and lower one was for sample with orientation 100 and thin film 100 nanometers. Okay, and the maximal value of magnetic entropy increase with increasing of magnetic field, and reach the value about 8 joule per kilogram K in magnetic field at 5 Tesla. If we compare these dependencies for each sample, we can find very interesting effect that maximal value can be observed for sample with orientation 100. You can see this dark cycle. For example, for thin film, the value was about 5K. For samples with thickness of gadolinium 300 nanometers, it higher up to 7.6 joule per kilogram per Kelvin. So this graphs, these plots can show us how it can be, this effect, how it can be tuned by not just thickness, but with changes of crystallography orientation too. For example, for amorphous film, no any changes was observed for 2 samples with different thickness of gadolinium. Okay, but for practical application, not just the value of magnetic entropy, it's important. It's important relative cooling power, because it's a parameter which directly used in magnetic refrigerator. It can be calculated as according with this formula, the maximal value of entropy, you can see this point, and full width at half maximum, this value. So it means that RCP depends on the shape of this curve. And we compare these results for 2 parts of samples and find that for samples with orientation 111, the value or RCP factor is too close to value for bulk materials. So it means that you don't need to take bulk materials. You can use just thin film at 100 nanometers for reaches the value big, so it's high value. Okay, I'm going to conclusions. As I said, for amorphous state of gadolinium film with orientation 110, the layer thickness does not actually affect the maximum value of entropy. For another sample with orientation 100 and 11, the maximum value of magnetic entropy reach up to 7.6 joule per kilogram per Kelvin, and varies with the layer thickness. and relative cooling factor in the sample with orientation 111 reach the value typically for bulk materials. This effect opens a new possibility for controlling and optimizing the magnetic caloric effect. Okay, thank you very much. I'm finished, and that's all.
Dr. Oksana Kaplak, thank you for sharing your findings with us. Any questions from conference hall? Okay, our viewers, Maria Savyak has a question. Does a diabatic temperature change for non-magnetic material?
Anna?
Anna,
Oh,
do you hear the question?
no, please repeat.
Okay, our viewers sent the next question. Does a diabatic temperature change for non-magnetic material?
If I understand question about magnetic and non-magnetic materials, no?
The question is, does adiabatic temperature change for non-magnetic?
Because it's magnetic. No, it's impossible to view in non-magnetic materials because we used magnetocaloric entropy. As you can see, total entropy depends on the sum magnetic entropy, lattice entropy, and phonon entropy. In our case, we use just magnetic entropy. We have deal with magnetic subsystem, with spin system. And okay, magnetic caloric effect can absorb in magnetic materials.
Okay, thank you for your answer. Many thanks for your presentation. We will move for the next speaker.
Thank you for you. Okay, thank you.
Our last speaker is Vitaly Polovy, who is not only the PhD student, but also a programmer. Vitaly is from Lviv Polytechnic National University, and the subject of his report is the influence of Coulomb interaction on the frequency spectrum of surface plasmons in dielectric metal dielectric structures. Vitaly Polovy, please, you are welcome. Start your report now.
My study concerns investigation of the spectrum of surface plasmon polar electron waves in the heterostructure, mainly dielectric metal dielectric heterostructures. So a little bit of history of my research. Firstly, we studied how metal thickness influences the propagation of plasmon polar electron in such structure. Then we decided to do some quantum, took into consideration some quantum side effects, and we took into account electron neutrality condition and obtained some results. This result was good, but not okay. And after that, we decided to investigate how Coulomb correlation, e.g., interaction between electrons in a metal system, will influence propagation of surface plasmon polyreturn waves. So let's proceed to the problem formulation. So we have two dielectrics, between them sandwiched a thin metal film. It's a very thin film. Sometimes it's have just few monolayers. So we are interested in propagation of surface plasmon polyreturns in the interzone dielectric metal. So first dielectric and the metal. The propagation of these waves can commonly described by the system of Maxwell's equations. The first equation. And what is interesting, the interdependence between vector of electric flux and vector of strength of electric field is non-local. So we perceive the process propagating as non-stationary. And this means that we have spatial dispersion and frequency dispersion. And then we considered the wave in the TM mode. The vector of strength for both magnetic and electric field has this configuration, as you can see on the slide. And after applying Fourier transform on two coordinates, we have such wave equation in different domains. The equation in the areas of the electric is easily solvable and solution is well known. But the equations, differential equation in the area of the metal cannot be solved analytically, unfortunately. So so we took some detour to solve this problem. First of all, we considered the electric function, which is diagonal component of the dielectric tensor. And then we decided to take, as I said, to take some detour on the second equation and took a mean value over the wave function of electron in a metal. How we obtained this wave function? We considered a model of an infinite potential well and found this wave function of electron in a metal field. It's a well-known model and solution is also well-known. So we took this dielectric function for the metal and obtained a dispersion relation and well-known expressions for energy level and quantum numbers, e.g. bound states. The main thing is physically, when we have metal field, the width of potential well is quite bigger than, so the potential well is wider than a metal field. It's wider by the coefficient 2D, which can be obtained from the equation 9. So this is one thing. This is quantum size effect that can be explained by penetrating of electrons from metal into the dielectrics. So when we have this exponential tail, then the width of potential well is wider than the width of actual metal. Then we put this all together, calculated, solved dispersion relation for different widths of the metal, and obtained such a result. So red lines. Red surface is when we took into account just condition of the electron neutrality. The model of potential well, which was considered in this case, is a rectangle potential well of the finite depth, asymmetric potential well. And blue chart is our current model, which is when metal is considered as infinite potential well, but with the Coulomb correlations. So as we can see, the difference between two models is very significant. And this is also the same results, but for fixed wave vectors. So you can ask us why you think this difference on the previous slide is significant, why it should, is it true or is it false? So we compared to the experiment which was carried out for the same structure as we took consideration, silicium dioxide, organic silicium. So in this table, very visible, fine. The A is our model, B is our previous model without Coulomb correlation, and C is an experiment. As you can see that considering the Coulomb correlations allowed us to have better agreement with an experimental data. So our model works, and it is how we prove its reliability. So moving forward, here we solve dispersion relation for the width of metal from 10 to 120. Of 120, sorry, yes. And as you can see, the oscillation picture, the amplitude of the oscillation is decaying with the growth of the metal film width. This can be explained by the same picture when we investigated the chemical potential of such system. So the chemical potential with the quantum size effects of chemical potential also fading with the growth of the metal width. So this picture is confirmed by the behavior of the chemical potential. Also, you can ask us, what about if you consider potential level of finite depth? First, I should say that to build a good analytical model for this kind of potential well with taking into account the Coulomb correlation is very, very difficult. So we first decided to estimate the approximate effect of such model of a metal. And so we introduced some model coefficient, K, which is a Fermi wave vector for the system with Coulomb correlation divided by the Fermi wave vector for the system without Coulomb correlations. And we substituted this coefficient in the solution for the rectangle potential well when we take into account only condition of the electron neutrality. And we obtained such results. So first column is wave vector, the second column when we does not considering this coefficient, and the third column when we considering this coefficient. So as we can see, the difference between these two models, so with Coulomb coefficients in the finite depth and without Coulomb coefficients in the finite depth, is almost negligible. So we decided not to follow this path with this hard to obtain and hard to solve model. And this is how we proved that we will not obtain any good practical results from this model whatsoever. So what we got? We transited from the just taking into account the width of metal to quantum size effects, and we proved that considering the quantum size effects in such models is significant, and quantum size effects should be taken into account. And that's the list of references that I used to compile this presentation together. Thank you for your attention. That's all.
Dali Polovay, thank you for your very interesting report. Any questions? Okay, thanks again. And we look forward to your future insightful pieces of work. Thank you all for joining our session on nanoscale physics. Section nanoscale physics is closed.
So the next our speaker will be Professor Bogdan Luganets from Lviv Polytechnic National University with a report titled as Changes in the Physical Properties of the Layered Crystals Caused by Ultrasound Treatment.
Thank you. Let us consider changes in the physical properties of the layer crystals caused by ultrasound treatment. The first of all, we consider some objects as materials to create in high capacity electricity storage. Then we consider layer crystals as the nanoporous materials. Then change of the electronic spectrum of a layer crystals by external factors, for example, ultrasound or intercalation. We propose modeling of the layer crystals and obtain the results. We apply it to modeling, for example, quantum capacity and conclusions. There is presented three object layer crystals, supramolecules, rhodes objects, will has characteristic feature of them. It is a significant change in physical properties under the influence of external factors, intercalation, ultrasonic treatment, and so on. More detail, we consider layer crystals. Here is presented well-known layer crystal gallium selenide, but any layer crystal may be considered as a set of packets which connected but van der Waals forces. These packets зараз
вот эту штуку поставили место.
там указки там можна зробити зверху там. О, от воно.
Треба мишку.
Коментар чи?
Так, це я ввожу зараз, мишка зараз не працює.
Мишка не працює.
Ага.
Можна оцим
Ну давайте.
От якщо ви тут пальчиком будете водити, ось мишка не працює.
Я зрозумів. А там, значить, якщо ми там розглядали. Це значить,
коментар?
Так. І, значить, от зараз тут повинно бути. Ну, бо з ним. От воно є. А не працює.
Це прекрасно. Ладно, оцим почитала нам надо. А як вище поставити? Як повернутися?
Так.
Давай не.
A set of packets which connected between them weak van der Waals forces. It is very important. It defined anisotropic character of the layer crystals. The distance between neighbor packets, so-called van der Waals gap, is above a few angstrom. This region very often defines the physical properties of the layer crystals. In general, layer crystals may be considered as specific nanoporous materials in which role of porous are van der Waals gaps. Let us consider model of the layer crystals. We used the chronic potential, which presented on this figure. The R1 presence of van der Waals gap, and R of the 2 presence of packets. The width of van der Waals gap is A, and thickness of packets is B. Sum of A and B is a lattice parameters of the system. You see that it is a one-dimensional model, and this axis of this model directed along to normal to the packets. Wave function of stationary Schrödinger equation takes the form a product where the first term is a Bloch multiplier. Solution for Bloch function presented to this equations. It is we see that this equation is has not analytical solution but numerical solution. In this figure presented numerical relation of such equation. On the figure left presented presented right hand of the equation, and directed in this this means of -1 to -2 defined forbidden zone and allowed zone. Right, we have this. We consider allow and forbidden gaps. There is a problem. How to simulate ultrasonic treatment of layer crystals? It is very important experimental data. The experimental data shows that the electronic treatment of the layer crystal, the first of all, significantly increased its total thickness along the normal to the layers. In this file, the thickness of packets remains unchanged. Therefore, the expansion of crystal occurs due to expansion of van der Waals gap. Thus, in the zero approximation, the effect of ultrasonic radiation of layer crystal can be described by chronic PNE models by the change in it on the thickness of the potential valve. Quantum obtained results presented term of zone allow zone of layer crystal presented on the higher equations. We have that first term right is bottom of the J allowed the bond, and delta J describe of in serial connected capacities. Total capacities consist of two terms. So first of all, capacity electronics, which connected with electrostatic electrostatic behavior, and another terms, so-called quantum capacity. Quantum capacity is a result of velocity of change of charge on the change of chemical potential. In our case, CK presents as sum our all allowed mini bands and states in every of this in this bands. The presented dependence of quantum capacity at temperature 200 Kelvin at valve width 0.1, 0.2, 0.4, 0.6, 0.8. In other words, there is intensity of ultrasonic treatment. Shaded region air present a load zone. We see that growth of intensity of ultrasonic treatment post shift of energy and as well at higher ultrasonic treatments, these zones love to shift to lower energy, and this curves describe of quantum capacitance, and we say that their position coincide with position of low zone. A model of lower crystal ultrasonic radiation proposed. Based on the obtained electronic spectrum, the quantum capacity is calculated. We show that quantum capacities have discrete structure. It is a result of dimensional quantization of the layer crystals. These quantum changes are a result of electronic radiations. And dependence of quantum capacities agrees with the location of the low zone. The maximum coincide with the bottom of the zone. Thank you very much.
Thank you very much for important contribution to the work of conference. And please, if you have some questions in conference hall. There is one question from our chat, which came from Victor Kisluk. May the graphite be considered as a layered crystal in accordance with the definition? Thank you.
There is presented layer crystal, well known layer crystal galaxy. Here is packets which is connected with weak van der Waals forces packets.
Значить, graphite може бути maybe considered as a layered crystal.
I understand.
In accordance with definition.
Packets will be not only there is packets consist of two monolayers planes. For example, the up in and top and upper plane is selenium. Inside two plane consist of gallium. If you consider graphene, it is not,
yes.
in this case, this packet will be graphene.
Thank you a lot again for very important work and answer. So at the moment we have not any more questions. So,
Thank you.
Yes.
Thank you very much.
Good day. The topic of my presentation is hierarchical zeolites and as efficient catalysis for substituted for bromo to 3-dehydro-1H in the nodes dehydrations. Indents as a target products of indenols dehydrations are widely used as different ligands for catalysis for different polymerizations. For example, such indent is used, complex of such indent with zirconium is used for different organic polymerization. Typical methods for production of indent consist in dehydration of corresponding indenol. The dehydration of indenol is a very complicated process and leads on predominantly homogeneous strong acids. However, a high yield of indent is achieved, a high amount of byproducts. We have a lot of high amount of byproducts, so that the other problem is separation of byproducts and homogeneous catalysis from reaction mixture. So that our task is to develop an effective catalysis for dehydration of such indenol. As promising catalyst for this dehydration, we use hierarchical zeolites. What is hierarchical zeolites? Hierarchical zeolites are crystalline materials which combine zeolite microporosity with intercrystalline and intracrystalline mesoporosity. So that this material is characterized by higher concentration of available acid sites and could be used as catalyst for transformation of bulk molecules. Exists a lot of approaches exists for synthesis of hierarchical zeolites. One of that is consists in using special Gemini type surfactants as structure directing agent. Such Gemini type surfactants is illustrated on this slide. That's organic molecules which contain 2 or more ammonia atoms which link it with different alkyl fragments. These molecules also has hydrophobic tails, which which limit the crystal growth to 1 or 2 crystallographic dimensions. In our synthesis of hierarchical zeolites, we used such type of mini-type surfactants. Depending on the structure and amount of quaternary nitrogen atom, it is possible to obtain zeolites with different topology and different morphology. For example, with using of Gemini-type surfactants, which has 2 atoms of nitrogen, it is possible to obtain bare, mordanite, and MPI nanosheets, whereas using different 4 and 6 structure reaction again, which have 2 or 4 or 6 quaternary atom of nitrogen, it is possible to obtain nanosponge, nanorods, and other zeolite beta and zeolite mordanite. Using these Gemini-type surfactants allows to significantly increase the range or the range of zeolite crystal and significantly increase mesopore volume of obtained materials. For example, as we can see, compression nanosheet and nanosponge zeolite beta isotherms with typical microporous zeolite beta. Obtained material is characterized by a high amount of acid sites. Typical for used zeolites are loose and branched acid sites. To determine the concentration and ratio of acid and base acid sites in our zeolites, we used some specific technique such as potentiometric titration of such zeolites and using special molecular probes such as pyridine or 2,6 decharged butyl pyridine. As we can see, in our work, we used 3 different types of zeolites. For example, bore, gallium, and aluminum containing zeolites. These zeolites are distinguished by the strength of acid sites. For example, aluminum sites are the strongest site among other. The weakest sites, weakest branched and loose sites is characterized by boron-containing zeolites. Distinguishing concentration and type of introduction elements, we can vary the strength and concentration and vary catalytic activity of obtained zeolites. Boron, gallium, and aluminum containing zeolites are tested in a process of dehydration of alcohol in the node. And then the main byproduct of this process, including different zeolites, are product of transformation of indene, transformation of indene to dimer with starting indenol, or product of coupling of indene with solvent benzene that we can use. In case of all aluminum containing zeolites, we have obtained full conversion of indenol, but the yield of inden significantly decreases with increase of acid strengths. For example, for aluminum marganite, which has the strongest sites among other hierarchical aluminum containing zeolite, the yield of inden is approximately 30 or 60%. Whereas for aluminum beta, and especially for natrium containing some exchanges where some very strong sites exchanged to natrium, we have obtained the selectivity near 95% during target product with full conversion. So that we decided to compare this aluminum containing zeolite beta with gallium and boron containing zeolites, which has weaker acid sites in comparison with zeolite aluminum containing zeolite beta. We can see that in case of boron beta nanosheet and boron MTW nanorod, the activity by inden is very high, but insufficient concentration of acid sites by due insufficient concentration of acid sites leads to low conversion and of indenol and low yield to inden. In case of boron beta nanoparticles with quite big concentration of acid site, we give a good conversion. And this good conversion we have for Galli beta, Galli MTW, and Galli beta nanosheets but for Galli beta nanoparticle, which has a stronger site in comparison with other illustrated zeolites, the yield and of inden significantly decreases. Based on our data we build a dependence of based on data calculated on due potentiometric filtration. We built dependence between yield, conversion, and selectivity of by target product in this process of strengths of acid sites. As we can see, at high concentration, when zeolite have very strong acid sites, we have full conversion of indenol, but selectivity to inden is not very good. And we, when the centers are weak, we have good selectivity to inden, but the yield of indenol is and conversion of indenol is low. So that we determine the optimal pKa or strength of zeolites acid sites in which conversion and selectivities are optimal. Also, we tested our zeolites in dehydration of some derivatives of indenol, methyl and isopropyl. In case of methyl indenols, just aluminum containing or natrium aluminum containing, which is characterized by highest concentration and enough strength, dehydration is occurs, which we can we think that it's due some we can see that probably due some steric restrictions that could be. In case of isopropyl containing zeolites, all zeolites provide good activity and selectivity, but bore-containing and gallium-containing zeolites are less active due to insufficient concentration of the acid site. So that we developed effective catalysis for dehydration of 4-brom-2,3 dehydro-1 indenol dehydration, and we obtained the optimal range of pKs of zeolites to predict the catalytic, to obtain optimal yield of corresponding indenol. That's all. Thank you for attention.
Thank you very much. Please, who have questions about the report? Okay. There are some questions from our chat. Victor Kisluk asked, could you please describe in brief the electrochemical mechanism of the zeolite acidic behavior?
Electrochemical?
Electrochemical.
Every zeolite have zeolites have two types of acid sites. In this process, we have just acid bronzed. Them works only bronzed acid sites. So I don't know about electrochemical mechanism. This just acid mechanism transformation. So typical electrophilic typical element.
Thank you. Dear Michael, thank you for your report. Thank you for your participating in the conference, and good luck.
Thank you.
Our next speaker is PhD student Darius, maybe I'm wrong with the pronunciation now, Chomicki from Nicholas Copernicus University in Turin, Poland. The main direction of his scientific work lies in the plane of synthesis and physicochemical research of quinoline azo-dyes polymers.
Good afternoon. Thank you for the introduction. My name is Dariusz Chomicki. I'm a second-year PhD student on the Faculty of Physics of Nicolaus Copernicus University in Poland. And before I start, I would like to thank the organizers for giving me opportunity to speak today. So my talk will be focused on the influence of substituents on photoresponsive behavior of metacrylic polymers containing 8-hydroxyquinoline azo-dyes in side chain. So to give you a brief introduction into my field of studies, I would like to talk a little bit about the azobenzene. So azobenzene is a molecule composed of two phenyl rings linked by an azo bridge. And one of its interesting features is reversible trans-cis photoisomerization. we can see here in the left corner, we have trans-azobenzene, which is the stable form of this molecule. And after interaction with the light, the molecule can change its conformation and its bands. So as it bends, the dipole moment of the molecule change, but also the absorption spectra change. So as we can see in this graph, the trans-azobenzene have two bands of absorption bands. In the blue, we have the pi star absorption band, and in the red, we have n pi star absorption band. So in the transform, the pi star absorption band is intense, and the second one is really weak. And as the molecule changes its conformation to cis, the absorption band becomes weaker, and the n pi star band becomes stronger. So what we can do with this property? The interaction of the molecule with light causes the change in the molecule properties. So this is the nonlinear interaction. So we can use these molecules in the nonlinear optics. And one thing we can do with these molecules is to introduce intramolecular charge transfer. So we can, the common procedure is to introduce substituents in the para position of the phenyl rings. And as we introduce them, the absorption band becomes redshifted, and upon absorption, the electrons goes from the donors to the acceptors, and this causes the further increase in the dipole moment change. So the nonlinear response can be increased this way. Another interesting feature of these molecules is photoinduced orientation. When azobenzene molecules are illuminated with linearly polarized light, after they go through the cycle trans-cis-trans, the molecules tend to orient in a way, in a direction perpendicular to the light polarization direction. So we can use this property to orient the molecule. And this is called photoinduced orientation. And what is worth noting is that we can induce this orientation just by light. The other polling techniques require using of optical field and heating the samples. And we can, in case of azobenzene, we can photoinduce the orientation just with light and in the temperature below the glass transition temperature of the polymer. So we can use this property to photoinduce birefringence, and this can be used in the holography, tri-dimensional holography. And last phenomena I'm interested in is the photoinduced mass transport. So when the polymer doped with the azobenzene molecule is illuminated with the interference pattern of light, the material tends to go from the light regions into the bright regions. So, and the surface relief gratings is recorded this way. So we can use this in the surface, two-dimensional holography. So this presentation will be focused mainly in this last phenomena, this photoinduced mass transfer. So as I said, the common procedure is to modify the azobenzene just with substituents in the phenyl rings. But at some point, chemists found out that we can change the properties of the molecules with substituting the phenyl ring itself. So in case of my material, I have the metacrylic polymers with quinoline azodyes in the side chain. And as you can see, in this material, one of the phenyl rings is substituted with the quinoline. And I wanted to check how the substituents in the para position of the phenyl rings affect the properties of my materials. So I used 3 substituents, electron donating substituents. So the neutral sample in this R1 position, we have the hydrogen, which is neutral. And I used metal, metox, and dimethylamino substituents, which donating strength increased in this order as I mentioned them. So I prepared my samples with spin coating technique. First, I dissolved the polymer powders into in dichloroethane, and then I deposited it onto the substrate, spinned, and the thin layers were formed. And to check the quality of the thin film surface, I used atomic force microscopy measurements. So here we can see the as prepared sample of the molecule with the hydrogen. And the roughness parameters, the surface is pretty smooth. And to check how the interaction with light, if interaction with light changed the surface quality, I illuminated the sample with 365 nanometer light for 20 minutes and then performed AFM measurements again. And as we can see here, the surface, this roughness parameters changed a little bit, but the surface is pretty smooth. And in case of the other samples, the surface quality was much better. We can see the roughness parameters are smaller. And I've done this kind of study for all the samples. And as we can see, the interaction with light do not change very much. These roughness parameters in some cases go down, in some cases go a little bit up, but it's worth to keep in mind that these measurements were performed in the difference area of the sample. So this may be the reason why these roughness parameters change a little. Next, I wanted to check the spectroscopic properties of these molecules to know what light should I use in the experiments. And I used spectroscopic ellipsometry studies. So here in this graph, you can see extinction coefficient of these molecules and wavelength of extinction coefficient maximum shifts toward red with the increase of the electron donating strength of the substituents. So we can see this in this case of the neutral samples, the maximum was around 362. The metal substituent shifted it just a little bit, but this dimethylamino substituent, which is the pretty strong electron donor, shifted the spectrum pretty much. Next, we wanted to check the refractive index. So one thing we can see is the maximum of the refractive index changed the same way. It's shifted toward red. The stronger electron donor we used in the molecules, the more the spectrum is shifted. And the refractive index value in the non-absorbing region. First, when we substitute the hydrogen with a weak electron donor, the refractive index value goes a little bit down. With using a little bit stronger donor, it goes down more. But in the case of the strongest electron donor, the refractive index value was higher. So that was a little bit surprising. And the last thing I've done, I calculated optical energy gap. And this is in accordance with the extinction coefficient studies. The energy gap is smaller. The smaller it is, the stronger electron donor is substituted, the smaller is the energy band gap. Okay, so to check if my material interacts with light, I performed a photoionization studies. So I illuminated the samples with 365 nanometer light. And during the illumination, I checked how the absorption spectra change. So we can see in this graph that in case of the neutral sample, the pi star absorption band goes down and this n-pi star band goes up. So just like I was expecting, we have photoisomerization in my materials, which is great. And in case of the other materials, situation was the same, with exception of this material with dimethylamino substituent. I couldn't observe the photoisomerization. So there are two possibilities. One is that this material do not photoisomerize, or the thermal back reaction is so fast that I couldn't see the absorption spectra change. I will talk about this thermal back reaction in, a bit later. So one thing we can see on these graphs is that we have these isosbestic points, which indicate that the photoisomerization reaction is the only reaction occurring during sample isomerization. Okay, so kinetics of the isomerization process can be described using this simple graph. So at the beginning, we have the molecules in the trans state, and the absorption probability is described with absorption cross-section. And when the molecule is in excited trans state, it can, with some quantum yield, go to the cis state. And in the case of the molecules in the cis state, the situation is similar. We have some probability of the absorption described by the absorption cross-section of the cis state, some quantum yield of the cis trans photoisomerization, but we have additional process, which is a thermal back reaction from cis to trans. So the isomerization kinetics can be described with exponential, mono-exponential decay, with this isomerization rate described by this equation. So what I determined is that the stronger the electron donor is substituted in this position, the faster is the isomerization reaction. The isomerization rate becomes higher and higher. Okay, and last experiment I performed was the holographic grating inscription. So here we can see the optical setup. I used the helium-cadmium laser, which gives light with length of 442 nanometers. Here we have the beam splitter, 50-50 beam splitter. And after reflection from the mirror, the light beam goes through the polarizer and quarter wave plane and goes onto the sample. So we have these two beams with opposite circular polarization, which was previously found that this is the most optimal setup for surface relief grating inscription. I have probe laser. It was 690 nanometer light laser, and I measured the first order diffraction intensity. And from that, I determined the diffraction efficiency. So the results are depicted on this graph. We can see that in the case of the materials with metal and dimethylamino substituents, the diffraction efficiency grows much faster than in the case of other two materials. What is worth mentioning is that after performing the experiment for 30 minutes, we didn't see saturation. So there is a possibility to achieve even higher diffraction efficiency in these materials. And
you can hear us? We can't hear you, please. Yes, now we're here.
How long couldn't you hear me?
From the beginning of this slide, possibly.
Okay, So what I was saying is that this graph depicts the diffraction efficiency of the surface of the gratings inscribed in my materials. And what we can see is that in case of the materials with metal and dimethyl amino substituents, the diffraction efficiency grows higher than in the case of the other two materials. And what is worth mentioning is that after 30 minutes of exposure of experiment, I didn't reach the saturation.
One moment. Could you speak more loudly?
Loudly?
We cannot hear you.
Okay.
It's so.
So we can't see saturation in this graph. So that means that there is a possibility to achieve even higher diffraction efficiencies in my materials. And the higher diffraction efficiency was achieved in the material with this dimethyl amino substituent. So this means the successful inscription of the gratings means that in this material, this material do photoisomerize, but the thermal back reaction is fast. So in the previous study, that's why I couldn't see the isomerization. But successful grating inscription means that we have photoisomerization in this material. And to check this grating, I used, and what is worth mentioning is that I used 440 nanometer light to inscribe the grating, which is the most strongly accepted with this one material. And to check this grating, I use surface profiler, and I found that the surface relief grating was inscribed only in these two materials with metal and dimethyl amino substituent, but not in the other two. But still we have some, although weak, we have some diffraction efficiency. So what happened in case of these two materials is that surface relief grating wasn't inscribed, but instead we could observe the diffraction from the bulk grating, which was created by this birefringence induction. So we have birefringence grating in the bulk, and in the case of the other materials, we have also the surface relief grating. So the next thing I will perform in the future is to perform photo-induced birefringence experiments on my materials to check this behavior. And at the end, I would like to thank my collaborators. And if someone is interested in more detail in my study, you can find it in my recently published article. Thank you for your attention.
Thank you very much. Is there anybody willing to ask a questions to the speaker? I would like to remind you that you can ask questions in our chat. Dear Darius, thank you for your report and
thank you.
Dear Darius, thank you for your report and goodbye.
Goodbye.
Our next speaker is Dr. Yulia Gorbatenko, awarded a scholarship of the National Academy of Science of Ukraine, participated in scientific collaboration with the Polish Academy of Sciences, and she was a member of the Council of Young Science at Working Institute for Low Temperature Physics and Engineering. The main scientist direction of Dr. Yulia Gorbatenko are investigation of thermal properties and mechanism of heat transfer in molecular substances.
Как найти презентацию, короче?
Физика, химия.
Горбатенко, да?
Yeah, Yulia, are you ready to start your talk? Thank you. Good afternoon. My name is Yulia Gorbatenko. Our research group is engaged in the study of the thermal conductivity, and today I would like to tell about the features of the thermal conductivity of molecular crystals formed by flexible molecules. What do we mean under the flexible molecule? In this case, it means the flexibility, it means the small changes in geometric configuration of the molecule leading to qualitative changes in the properties. Following substances have been selected as the objects of the study. Then can be divided into three groups. First of this, it's benzophenone substances, it's benzophenone and 4-bromobenzophenone. Flexibility in these substances is caused by the rocking phenyl rings symmetrically to the ketone bond CO, and also by the rocking C-bromine bond in the 4-bromobenzophenone molecules. The second group is chloronitrobenzene derivatives. It's parachloronitrobenzene and pentachloronitrobenzene, abbreviated as para-CNB and penta-CNB. Flexibility of these molecules deal with rocking the nitro group relative to the phenyl ring. And this third group is freons, freon 112 and freon 113. These molecules have the flexibility, deal with conformational flexibility. The rotation of molecule occurs relative to the CC axis. It is known that for the dielectric orientational ordered molecular crystals, the thermal conductivity has a bell-shaped form with pronounced maximum. As example, on figure 1, temperature dependencies of the thermal conductivity for krypton is presented. To the left of the maximum, thermal conductivity is determined by the scattering phonons on different defects of crystal lattice, such as boundaries, dislocations, and impurities. To the right of the maximum of the kappa, the main mechanism of phonon scattering is phonon-phonon interactions, which are qualitatively described by the kappa inversely proportional to temperature. But more correctly, it is described as expression A divided T plus B, where the first term is due to the phonon scattering, and the second term B is a contribution of short-wave excitations, so-called diffusons. What about experimental technique? Thermal conductivity have been measured by the potentiometric steady-state heat flux method. And this method allows to make investigation in the wide temperature range. And experimental part. There are temperature dependencies of thermal conductivity for two polymorphic phases of 4-bromobenzophenone. Single crystal with triclinic structure, triangles, and monoclinic sample
which was polycrystal. A difference in these curves below 30 Kelvin is due to the fact that the preclinical sample was a monocrystal and monoclinic sample was the polycrystal. Both experimental curves described by the approximation A divided T plus B in wide temperature range. For triclinic sample, its expression describes range from 8 to 120 Kelvin. For monoclinic sample, it describes range from 30 Kelvin to 130 Kelvin. Above 120 and 130 Kelvin respectively, an anomalous growth of thermal conductivity is observed. It was suggested the observed growth of thermal conductivity may be associated with the influence of intramolecular vibration, in particular the C-bromine bond in phonon heat transport. In order to obtain the parameters A and B, which describes the phonon and diffusion contribution to thermal conductivity, experimental data for two polymorphs of for brombenzophenone or para-brombenzophenone were replotted in such coordinates. The dashed line shows the dependence A divided T plus B. The arrows indicate the deviation of experimental data in monoclinic brombenzophenone from expression A divided T plus B. Since in both polymorph for bromobenzophenone have different structures and different number of molecules per unit cell, it is possible to check the correlation between diffuse contribution to thermal conductivity B and with number molecules per unit cell. It can be seen on figure 4, where we presented diffuse contribution to thermal conductivity B versus number of molecules per unit cell Z for different molecular crystals. Both polymorphs are shown by the stars. Orange star corresponds to the clinic polymorph of bromobenzophenone, and green stars corresponds to monoclinic polymorphs of bromobenzophenone. It can be seen that diffuse contribution to thermal conductivity is inversely proportional to Z, but our experimental results differs from theoretical predictions. Here it marks by the dashed line. Next, since it has been found that anomalous growth of thermal conductivity in two polymorphs of 4-bromobenzophenone, we also have been investigated the thermal conductivity of benzophenone. It is shown on figure 5. Here for comparison, we plotted data for two samples of benzophenones and two polymorphs of 4-bromobenzophenones. It can be seen that qualitative the temperature dependencies of conductivity very similar. I want to repeat this slide. Next, we have done an analysis of
abnormal growth of thermal conductivity, which marked arrows on the previous slide. Early thermal conductivity growth was observed in quasicrystals, and it has been described by exponential dependence, which is Arrhenius equation. Arrhenius equation has two parameters, kappa 0 and E. In order to obtain the parameters kappa 0 and E from total thermal conductivity, kappa, it was subtracted term kappa 1, which marked the A divided T plus B, and the obtained values can be just a moment, has been replotted in coordinates logarithm kappa thermal activation from reciprocal temperature. It is shown on figure 7 for benzophenone substances. Also, just a moment.
Andrei.
Technical. So, for benzophenone substances, we obtained the next expression. In region of predominance of phonon-phonon process scattering, thermal conductivity can be presented as a sum of three contributions: phonons, A divided T plus diffusons, B, and thermal activation. The parameters kappa 0 and activation energy are given in the table. As I say, this thermal activation contribution is due to the influence of intramolecular modes. In benzophenone, it's flexibility molecule symmetrically to the ketone, and in the 4-bromobenzophenone, it's C-bromine bond. On the figure 8, presented the thermal conductivity for chloronitrobenzene derivatives. Para C and B was investigated in orientational ordered, blue circles, and orientational disordered phase, gray squares. The features in para C and B is due to fact that growth of thermal conductivity is observed and in orientational ordered and orientational disordered phases. And an analogous situation we can observe in orientational disordered penta CNB. And finally, we can see that thermal conductivity versus temperature for orientational disordered phases. One example, freon 112 and 113 demonstrates anomalous growth of thermal conductivity. Next, we also had done analysis of pre-exponential factor kappa 0 versus activation energy of molecules. On this figure 10, different symbols indicates investigated molecular crystals.
it can be seen that kappa 0 linearly depends from activation energy. Some relation was obtained for some quasi-crystals, which on this figure marked by stars. And now we can formulate conclusions. It was investigated the thermal conductivity of molecular crystals formed by flexible molecules in wide temperature range. It was shown that thermal conductivity features in the high temperature region are due to the influence of intramolecular vibration on phonon heat transport. The anomalous growth of thermal conductivity corresponds to thermal activation mechanism of heat transfer, which described by the Arrhenius equation. It was shown that thermal conductivity of investigated substances in region of predominance of phonon-phonon scattering processes can be represented as a sum of three terms: phonons, diffusons, and thermal activation contributions. It was found that thermal activation contribution to thermal conductivity in molecular crystals formed by flexible molecules linearly depends on the activation energy of molecules, and it takes place for some quasi-crystals. Thank you for your attention.
Yeah, Julia, thank you for your report, and please ask questions to speakers more actively, and because there are many interesting reports and so little questions. Thank you very much.
Thank you.
I'm going to take you through Jakub Matusiak. He's a PhD student at the Institute of Chemical Science, Maria Curie Skłodowska University in Lublin. His research interests concern stabilization of colloidal systems using polymers, surfactants, and their mixtures. He's also studying the efficiency of natural bioflocculants used in water purification and wastewater treatment. Yes, Poland, from Poland.
Mr. Jakub, can you hear us?
Yes, I can hear you. Can you hear me?
Yes, we can.
Okay.
Please demonstrate your screen for us.
Okay, let me here and okay, can you see my presentation?
Still not.
Let me check then. How about
yes,
now?
Now we can see it, only just full screen mode.
Okay.
Yes, we can see it.
Great. Okay, so can you see everything and can you hear me?
We can hear you quite good, and we see the full screen mode of your presentation, so wish you good luck.
Okay, thank you very much. So let's get started. My name is Jakub Matusiak and I represent the Institute of Chemical Sciences, Maria Curie Skłodowska University in Lublin, Poland. Thank you very much for this opportunity to present my research to the conference. It is quite unusual to talk to the laptop instead of the public, but I think I will manage it somehow. So today's presentation will be about the comparison of the adsorption and the electrokinetic properties of two colloidal systems, fucoidan titania and fucoidan alumina. As an introduction, I will tell you a few words about the polymer I have used in my research. So fucoidan is a natural anionic polysaccharide extracted mainly from brown seaweeds. Its structure is composed of a sulfated fucose backbone, but can also contain other quantities of other sugars such as xylose, uronic acid, and galactose. As you can see on this picture, the structure of this polymer is quite simple, but considering the fact that this is a natural compound, we can expect that depending on the species, season, harvest location, and the maturity of the plant, we can expect different composition of the polymer chain. For example, here are the fucoidans obtained from the Fucales family. As you can see, they are linear polymers. However, if we take a look at two other plant families, we can see that even branched structures are possible. Here you can see that uronic acid is present in the main polymer chain. So fucoidan is gaining its very interesting compound. Recently, it's used as a multifunctional material, mostly because of its antiviral activity, antioxidant activity, and, for example, anti-inflammatory activity, and so on. Moreover, the bioactivities of fucoidan support its use as a functional food for health beneficial effects, along with prevention and management of different diseases. So as you can see, this is a quite useful compound. So the aim of this study was to investigate the adsorption and electrokinetic properties of two colloidal systems, fucoidan alumina and fucoidan titania suspensions, in the presence of calcium chloride as a background electrolyte. To conduct this studies, we have used different methods. We have characterized the use substrates using, for example, DLS, SLS, SEM, XRF, or FTIR. We have quantified the adsorption of the polymer on the solid surface. We have measured the electrophoretic mobility, recalculated to the zeta potential. We have also studied the adsorption layer thickness using the viscometric measurements. And in the end, we have estimated the stability of our suspensions. So the first step in our research was the characterization of the used solid samples. We have used two adsorbents. It was gamma phase alumina and anatase form of titanium dioxide. As you can see, they were characterized by different specific surface area. The alumina was 171 square meters per gram, and the titania was 50 square meters per gram. We have also used the X-ray fluorescence spectroscopy to ensure that our samples are free of heavy metal contamination. And the analysis showed that both of the adsorbents contained over 99% of aluminum oxide and titanium oxide, respectively. We had information from the manufacturer of those oxides, because they were commercially available, that the primary particle size of the solid particles were 20 and 32 nanometer, respectively. However, we were aware of the fact that such particles aggregate in liquids, in solutions. Thus, we have measured average size distribution of the aggregates using the dynamic light scattering method. And we have obtained quite monomodal peaks for alumina and titania. It was 172 nanometers and 130 nanometers, respectively. On this slide, you can see the morphology of the used adsorbents. This is 1K magnification, 10K magnification, and 50K magnification. Here you can see that those particles are indeed nano-sized. However, they form bigger clusters of aggregates. We have also characterized our polymer. It was commercially available fucoidan from Fucus serratus. We have measured the molecular weight of this compound using the static light scattering method. And it was quite high. It was 1,730,000 Daltons. it was quite high value for fucoidans. However, even higher molecular weights were observed in the literature. Moreover, we have estimated the sulfate content using the barium sulfate precipitation method, and it was close to 6%. This, on the other hand, was quite low because usually the commercially available fucoidans contain around 20% of sulfate. However, this value was also spotted in the literature, so everything was fine. We have also carried out the FTIR analysis to check, to ensure that the sulfate groups are present in the polymer chain, and they indeed were present in our polymer. What was interesting, we have observed one stretching vibration of the dissociated carboxylic group, which was unfortunately covered by the hydroxylic group vibration. This vibration was coming from the carboxylic group, meaning that not only the sulfate was present in the chain, but also uronic acid could be found in the polymer chain. As far as the experimental results are concerned, we have studied the adsorption of fucoidan on the surface of two of our adsorbents. As you can see, the polymer adsorbs well on both of these solids. However, the adsorption was higher on the surface of titanium dioxide. In both cases, you can see that the adsorption increased in the presence of calcium chloride as a background electrolyte instead of sodium chloride. The reason for that was the formation of intermolecular complexes between the negatively charged polymer chain and divalent calcium ions. Moreover, we have studied the influence of pH on the adsorption of fucoidan on the surface of those adsorbents, and we have observed very little influence of pH on the adsorption. There were two explanations for that fact. The first one was that in the whole studied pH range, the surface of the alumina and titania were indeed positively charged due to the specific adsorption of calcium ions. I will show you more about it later. The second explanation could be the fact that the content of sulfate groups in the polymer chains was quite low, so we did not observe great influence of pH on the adsorption of this polymer. The next step was to study the influence of ionic strength, or as you could say, the calcium ion concentration on the adsorption of fucoidan on the alumina and titania. In red, you can see the adsorption of fucoidan on alumina. There is a slight decrease of the adsorption between the lowest ionic strength and the medium one. It could be explained with the fact that the adsorption of fucoidan on the alumina surface occurs mostly by electrostatic interactions. On the other hand, when you look on the adsorption of fucoidan on the titanium dioxide, you can see that the adsorption increased and then remained constant. So the increase could be coming from the fact that not only the electrostatic interactions are responsible for the adsorption, but also the non-electrostatic ones. And the second explanation could obviously be the fact that when more calcium ions are added to the system, more thicker adsorption layer is formed. Thus, we have managed to measure the adsorption layer thickness of fucoidan on the alumina and titania surface, depending on the ionic strength of the calcium chloride. And we have observed that with the increasing ionic strength, the adsorption layer thickness also increased. This could be explained by the fact that when the increasing ionic strength is observed, more developed structures are also observed in the adsorption layer. Not only the train structures, but also loops and tails are present, thus the layer is thicker. We have also studied the electrokinetic properties in terms of zeta potential. Zeta potential is quite useful tool that could be used to provide relevant information that could be used to describe the structure of the diffused part of electrical double layer, stability of the colloidal systems, aggregation of the particles, and also the toxicological evaluation of the nanoparticles. This is why we have studied this property. As you can see on figure 4, we have studied the influence of the type of electrolyte on the zeta potential of the alumina. In case of sodium chloride as a background electrolyte, we have observed isoelectric point of alumina in pH close to 9, meaning that the surface of the alumina was positively charged to pH 9 and negatively charged above pH 9. However, when we studied the electrokinetic potential in the presence of calcium chloride as a background electrolyte, we have observed complete charge reversal of the surface, and in the whole studied pH range, we observed that the zeta potential was positive. Moreover, no isoelectric point was observed due to the fact that calcium ions adsorb on the surface of the alumina. And then we have also studied the influence of fucoidan on the zeta potential of the alumina. As you can see, the situation is quite different when we added the polymer to the system. And now we observed that the charge reversed to the negative values due to the anionic nature of the polymer. However, it decreased with the increasing ionic strength, or the calcium ions concentration. There could be two explanations for that fact. The first one is obviously the presence of more and more calcium ions present in both the diffused and the compact part of the electrical double layer, but also the fact that the system is less and less stable with the increasing concentration of calcium ions. Zeta potential, as I said before, is a great tool that could be used to estimate the stability of colloidal systems, and the literature says that the values of zeta potential above plus minus 40 means that the system is stable. As you can see here, we have decreasing value of zeta potential with the increasing concentration of calcium ions. So we can expect the fact that the ionic strength, the higher the ionic strength, the less stable the system is. This was indeed true because we have observed it with our eyes. You can see that in the lowest ionic strength, we can see a turbid suspension of alumina, and when the highest highest ionic strength is applied, you can see clear liquid with sediment on the bottom of the vial. In case of the titanium dioxide, the situation was quite similar, with the difference that in the lowest ionic strength we have observed the isoelectric point. It shifted from 6 to around 7.5. The reason for that was obviously the specific adsorption of calcium ions on the titanium dioxide surface. And here you can also see that the suspensions were the most stable in the lowest ionic strength and the least stable in the highest ionic strength on the highest calcium ions concentration. But you could ask yourself, why do we measure such properties, the adsorption, the electrokinetic properties? The answer is to estimate stability of colloidal systems. This is a very important factor in producing new products, for example, for cosmetic and pharmaceutical industries. From our previous work, we have learned that fucoidan could be used as a stabilizer of those suspensions, which could find interesting application in different cosmetics. However, when we applied calcium chloride as a background electrolyte instead of sodium chloride, we observed the decrease of stability, and it's in such system the fucoidan acted as a flocculant rather than a stabilizer. Here you can see the changes of the TSI in time. The TSI is the Turbiscan Stability Index. It is a value measured on the base of the backscattering of the sample. And this TSI changes from 0 to 100. When sample is stable, it is 0. When it's unstable, it is closer to 100. So here you can see that in the lowest ionic strength, the sample was unstable. However, it was more unstable when more calcium ions were added to the suspension. The same situation was observed in the case of titanium dioxide. Here you can see that this suspension was more stable than alumina, but with the increase of ionic strength, we observed the decrease of stability, thus the higher TSI values were observed. So my take-home remarks for you is the fact that the description of the system stability is a very complex process that includes studying not only the adsorption but also the electrokinetic properties of studied systems, and the fact that fucoidan can act either as a stabilizer or a flocculant of the oxide suspensions, depending on the used electrolyte and its concentration. This fact is particularly important for different branches of the science and industry, because it could be used as a stabilizer of different cosmetic products, but it could also be used as a flocculant for the removal of nanoparticles from wastewaters. So I would like also to acknowledge that this research was funded by the National Science Center of Poland, and I would like to thank you very much for your kind attention. And if you are interested in our work, you can check our ResearchGate or the Google Scholar, or just contact me by email. Thank you very much.
Yeah, Jakub, thank you for your report. Thank you for participating in our conference, and good luck.
Thank you very much.
Let me introduce you. Tatiana Zheltanovskaya is a doctor of chemical science, professor, honor work of science and technology of Ukraine. She is the head of research group in the Department of Polymer Physics of the Institute of Macromolecular Chemistry of the NAS of Ukraine. Yeah, Tatiana, can you hear and see us clear?
Yes, I can.
Let's start. Please, let's start your report.
Please share your screen to us and turn on the video.
Do you see my lecture?
No.
Oh,
Open Zoom and start sharing screen.
Yes. Zoom. О, Господи. Sorry.
Okay, we could broadcast your presentation that you have sent to us, and you could you could give your lecture, and we will change the slides. Is that?
Do you see my lecture?
No, we see you at now. Have you? Please press in the Zoom. Press down on the Zoom. There is a green bottom down on the screen called Демонстрация экрана. Press.
I press.
Yeah, это я. No, you have pressed, yeah?
I pressed.
And selected the screen, yeah? We can see your presentation. Okay. Anyway, we could share your presentation, and you will give us a talk. Okay. Okay, you could open your presentation and give us a talk, and we will share your presentation.
Do you see my presentation?
No.
Oh, Господи.
Внизу экрана Zoom есть кнопка демонстрация экрана.
Я включаю, но она не включается.
Сейчас.
Демонстрация экрана. Включаю, не включается.
Хорошо, давайте мы будем транслировать вашу презентацию, а вы будете делать доклад, мы будем вас слышать.
Нет, ну я же должна вот эту презентацию показывать, свою.
Да, которую вы прислали, вы нам прислали презентацию.
Нет,
которую...
я лучше покажу свою. Я там кое-что исправила. Как же сделать связь?
О.
Так, демонстрация. Не могу ее открыть. Что-то заблокировано.
У нас открыта демонстрация экрана, разрешаю на всем.
Но это ваша, я же ее не вижу.
Я понимаю. Мы разрешили всем пользователям демонстрировать свой экран.
Но я-то свою презентацию не вижу здесь. Вы ее отключите, я включу свою.
У нас не включено ничего. Мы ждем от вас только.
Еще раз, демонстрация экрана. Но она не открывается. А, вот, открылась. Все. Do you see my presentation?
Yeah, yes, we could see your presentation. Please, give us a talk. You're welcome.
Can I begin?
Yes.
Thank you. Dear Chairman, dear colleagues, first of all, I would like to say many thanks to organizing committee for this conference, and also I would like to wish to everyone many health in this difficult time. So, the micelles of block copolymers are advanced materials of modern nanotechnologies. Therefore, their structure, synthesis processes and functional properties depending on their chemical nature, length, and interaction of blocks are widely studied. The main purpose of my presentation is to show the difference between micellization of block copolymers with weakly and strongly interacting blocks. Micellization of amphiphilic block copolymers in an aqueous medium is an example of self-assembly of block copolymers with non-interacting blocks. Here, the different types of micellar structures are shown, which are formed by amphiphilic diblock, triblock, and multi-block copolymers, where B is hydrophobic blocks and A and C are hydrophilic blocks of various nature. You can see a crew-cut and hairy type spherical micelles, a cylindrical and flower-like micelles, a vesicle with identical villi, a micelle with mixed karyona in which A and C blocks are thermodynamically compatible. Then a micelle with a divided karyona in which A and C blocks are thermodynamically incompatible. Also, you can see a vesicle with various villi and a core shell karyona micelle. The morphology of micelles and their relative size of hydrophobic core and hydrophilic karyona are determined by the position of hydrophobic block in the copolymer macromolecules, and also the strength of hydrophobic interactions in aqueous medium, and also by nature, total and relative length of hydrophobic and hydrophilic blocks. To consider the difference between micellization of block copolymers with weakly and strongly interacting blocks, it is necessary to recall firstly what intramolecular polycomplexes are. Intra-PCs are formed in an aqueous medium by block type copolymers with hydrophilic chemically complementary components. They are stabilized by cooperative non-covalent bonds such as salt or electrostatic, hydrogen, and dispersive. Intra-PCs with salt bonds are formed by block polyamphalites or zwitterionic block copolymers. Intra-PCs with hydrogen bonds are formed by block copolymers with protein donor and protein acceptor groups. Here, two first publications devoted to synthesis and intra-PC formation of diblock polyamphalites and diblock copolymers with hydrogen bonds system between the blocks are shown. The next slide demonstrates the first schematic representation of intra-PCs in diblock polyamphalites and the first a name, such as intra-macromolecular polycomplexes. It should be noted that our scientific team later introduced to scientific literature other terms, such as intramolecular polycomplexes. The block copolymers forming intraPCs are of a dualistic nature. On the one hand, they have many of the properties of intermolecular polycomplexes, but on the other hand, they retain many of the properties of conventional block copolymers, including amphiphilic ones. Due to these features, they can demonstrate different self-assembly types in an aqueous medium. Here, some self-assembly types for AB asymmetric diblock and triblock copolymers are presented. If the external contents such as pH, temperature, and the presence of other additives contribute to the stability of intraPCs, such type as self-assembly of intraPCs is realized. In this case, a special micellar structures with complex core and hydrophilic caryonia formed by surplus unbound segments of longer blocks appear. But if the bond system between the blocks breaks down, other types of self-assembly can be realized, such as self-assembly of only B block, of only A block, dependent on their relative solubility in aqueous medium in new external conditions. It is seen that depending on the structure of block copolymers and relative lengths of interacting blocks, essentially different micellar structure can be obtained. In one of our previous works, we proposed to describe such complex situation with intraPC forming block copolymers in an aqueous medium from the point of view coexistence of some competitive equilibriums. The system of such equilibriums presented in this slide was proposed for the case of AB diblock and triblock copolymers. One of block is polyacid, and between the blocks, the hydrogen bond system exists. In this work, we predicted the existence of special type of self-assembly of these block copolymers by intermolecular mechanism. In the following our work, we fully proved this prediction. Our scientific team studied micellization and drug carrier properties of double hydrophilic block copolymers forming intraPCs by hydrogen bonds. We studied DBCs and TBCs based on methoxypolyethylene oxide polyacrylamide, methoxypolyethylene oxide polyacrylic acid, and polyacrylic acid polyacrylamide. We studied also encapsulation release properties of model drugs by micellar nanocarriers and tested the developed micellar composition in vitro and in vivo. Let's consider one of our results. Firstly, micellization of asymmetric block copolymers based on MOPU and PAM blocks. Firstly, we obtain a series of diblock copolymers with this block with increasing lengths of MOPIO and PM blocks. In this series, the degree of asymmetry also increased. The parameter n is the ratio between the units of PM and MOPIO blocks. We determine the micellization thermodynamical parameters such as the critical micellization concentration and the Gibbs-free micellization agent, and found the increase in stability of micelles in this series of block copolymers. In aqueous solution, we found the hairy type polymolecular micelles and also small monomolecular micelles, which were in fact individual intrapices. Then we obtained a series of triblock copolymers, also with increasing length of PO and PM blocks and increasing degree of asymmetry. In aqueous solution, we observed also the formation of hairy type micelles, but in the case when the lengths of PM blocks were too high, we observed the appearance of very special micelles such as plate-like or cubic. Also, we destructed the system of hydrogen bonds between the block and observed the transition between hairy type micelles and two flower-like micelles, which contain polyacrylamide segments in their core. Then we studied micellization in asymmetric diblock and triblock copolymers based on MOPIO and PA acid blocks. As to DBC, we obtain a MOPIO block with the same length, but the length of PA acid block increased. The degree of asymmetry also increased in this series. These micelles were formed. This micelle formed also at pH less than 5. When the degree of asymmetry was relatively small, we observed the formation in aqueous medium crew-cut micelles, but when the degree of asymmetry was high, we observed the formation of hairy type micelles. Also, we found in this solution small monomolecular micelles, which were in fact individual intrapices. In a series of triblock copolymers, we proportionally increased the length of PO and PA acid blocks, and the degree of asymmetry was practically the same. In this case, we observed the formation of flower-like micelles, and their size with increasing the length of both block essentially increased. Let's consider micellization of asymmetric diblock and triblock copolymers based on PA acid and PM block. This is one of the most interesting cases. Due to the help of French colleagues from Institute of Paul Sabatier from Toulouse, France, We created two interesting series of diblock and triblock copolymers with the constant length of p-acid block and increasing length of PAM, non-ionic blocks. In this series, the degree of asymmetry also increased. Very interesting morphology we observed in aqueous medium. Side by side with almost spherical monomolecular and polymolecular micelles, we observed also an unusual needle-like structures. Analogous situation we observed in the case of triblock copolymers, but the effect was higher. Taking into account that the natural pH of these solutions, TBCs and DBCs, was relatively high, we achieved the conclusion that this situation is conditioned by simultaneous self-assembly of these block copolymers by intramolecular and intermolecular mechanisms. In this case, if it is right, the energy of self-assembly of these block copolymers by both mechanisms is approximately close. Then we asked ourselves what will happen in these micellar systems if we strengthen the system of hydrogen bonds between the blocks. To clarify this issue, we lowered the pH value up to 3.0. This slide demonstrates the situation with DBCs. The relative content of spherical polymolecular micelle grew, but the needle-like aggregates did not completely disappear. On the contrary, their size increased. An analogous situation we observed also in solutions of triblock copolymers at pH 3. The next slide presents the sizes of various morphological forms of micelle structures in solution of these diblock and triblock copolymers. It is seen the effect of increase of size of needle-like aggregates. Then we decided to confirm a similar effect in solution of other diblock and triblock copolymers containing more PO or PO and P-acid blocks. Early, we studied their self-assembly at a very low pH and found only almost spherical mono and polymolecular micelles. In the following experiments, we prepared these micelles at low pH and then increased this value to 4.0, 4.5, thus weakening the interaction between the blocks. As a result, we recorded the appearance of both spherical and needle-like micellar structures simultaneously. Thus, we proved our prediction that block copolymers forming intra-PC can self-assembly not only by intramolecular mechanism with formation of spherical micelles, but also by intermolecular mechanism with formation of needle-like structures. These structures
I'm sorry. Your time is almost up. please move to the end, and you got only 3 minutes left.
Yes, I can to finish.
Okay, thank you.
These are our muscle systems developed by us with drugs and silver nanoparticles. The most important conclusions are self-assembly of asymmetric block copolymers with hydrophilic chemically complementary blocks is one of the simplest way to create micellar nanocarriers with a complex core that have an increased binding capability in relation to toxic polysoluble drugs of various nature. They can effectively encapsulate drugs at C less than CMC due to their monomolecular micelles. In dilute aqueous solutions of these copolymers, there are 2 types of self-assembly, in contrast to their self-assembly of classical amphiphilic block copolymers with non-interacting blocks. The first type is the formation of intraPCs in individual copolymer macromolecules by cooperative non-covalent interactions, in particular hydrogen bonds, with the subsequent segregation of hydrophobic bound section of several intraPCs that resulted in the appearance of spherical polymolecular micelles at C higher than CMC. The second type of self-assembly is the formation of interPCs between chemically complementary blocks belonging to different macromolecules. It manifests itself at C higher than CMC in solution of block copolymers with a relatively weak system of non-covalent bonds and leads to the appearance of special needle-like intermolecular aggregates that can coexist with spherical polymolecular micelles. Co-authors of this presentation are Dr. Permякова, Dr. Kunitskaya, Professor Klipko, Dr. Klimchuk, and many thanks for cooperation to Dr. Maziras, Professor Destarakt from Laboratory of Heterochemistry of the Paul Sabatier University, France, to corresponding member of NES of Ukraine, Professor Stoyko from Institute of Cell Biology of NES of Ukraine, and Professors Maxim, Yakubchak, and Karpovsky from National University of Life and Environmental Sciences of Ukraine. Many thanks for your attention.
Professor, thank you for your report. And there is some questions from Victor Kisluk. What is the micelle stability as to possible aggregation? Is there a radial charge separation within the micelles?
This micelles is very stable. Their CMC has very high their CMC is very low. Due to this, they did not disrupt it at the dissolution.
Thank you very much for your report, and goodbye.
Goodbye.
Ladies and gentlemen, we are ready to proceed to our next report to be given by Dr. Anvi Panko. Dr. Anvi Panko is senior researcher of Ovcharenko Institute of Biocolloid Chemistry of NAS of Ukraine. The author's report concerns the problem of transformations of marine sediments under the influence of biocolloid processes and nanotechnology of their enrichment and application.
Hello, can you hear me?
Hi.
Yes. Hello once more. Today I want to present you some of generalized data concerning, as you already heard, the transformation of iron oxide aluminum silicate materials on the example of marine sediments under the influence of biocolloidal processes, and as well to present some aspects of the use of such knowledge. The data would be only generalized for better clarity, especially because it's a multidisciplinary work, and not to exceed time limits. So if there would be an interest of more complete data, we plan to publish it in this year's spring year monography after the conference. And of course, you can ask the questions at the end of the presentation. Well, to begin with, sorry. Yes. To begin with, it should be noted that marine sediment mostly consists of mineral turbidity part, which almost always include iron oxide, aluminum silicates, for example, clays, and an organic part, which includes biogeocyanosis of microorganisms and products of their metabolism. In the given electron microscopic images, we can see an example of such sediment in interaction with microorganisms. In this case, we see the rest of foraminifera and cyanobacteria, and including figure 2, and a hydrochloride as a product of the activity of sulfate-existing bacteria. But as you can see from the table of microbiological studies, there's a lot more a number of microorganisms, even the types of microorganisms in this element. And as long as in these examples the amount of organic phase and content of nanoparticles is not too much, but they have a significant impact on the properties of marine sediment, and not only on them, on these sediments. One of the obvious results of the action of biocolloid factors on iron oxide aluminum silicate materials is shown on figure 3. This experiment, unfortunately for well-known COVID reason, had not yet been fully completed, but you can still see a very interesting result. First and most obvious from the picture, that through several different stages of the process, as it can be seen on the picture of the final stage of the process, the initial polymineral and polydispersed material presented here by poor iron ore of biocolloid origin was divided onto three phases, layers: quartz, carbonate, clay, and iron oxide phases. This was achieved by non-specific bioflotation, autodispersion, and other biocolloid processes. At the same time, it should be noted that autodispersion processes are accelerating by orders of magnitude by the products of metabolism excreted by microorganisms, and it was already mentioned that they act as a surfactant substances which increase autodispersion itself. And as it can be seen from the figure 5 here, for a little bit another material in this case, pelagic sediment, but for the same process. That such processes have a very important impact on physicochemical here viscosity, chemical here concentrations of iron, and even mineralogical parameters. And as you can see, they correlate to bacteria content. Yeah. And on figure 6, you can also see the effect of nanoparticle presence. Left image with nanoparticles, right image without nanoparticles. That can be produced as a result of biocolloid autodispersion processes as well. Well, their effect on neurological behavior, which is also important for predicting the behavior and properties of sediments. The established experimental and theoretical data generalized in this work gave us the possibility to propose a model of the formation of pelitic sediments from dense rocks during biocolloid processes. And it also notes that under certain conditions, stress catastrophic phenomena are possible, conducted by gravitational movements of huge sediment masses. According to colloid chemical theory of stress and catastrophic phenomena on underwater slopes of seas and oceans. A model of such phenomena was also developed, which can be seen on figure 8. Phenomena on underwater slopes, which shows that due to changing of characteristics of accumulated sediment, it can and maybe some external forces. Such sediments can change their geological behavior and start to flow, causing stress phenomena, including earthquakes, and even earthquakes, which can be characteristic for the impact of tons of sediment in seismic unstable areas. For example, it is especially important for such called volcanic rings in the Pacific Ocean. Very fast. The conclusions are presented on a slide, but it should also be noted that the data and results of the work presented in this short but generalized report can be used in a broad profile, and especially for improving the bottom of technological patterns, for improvement of therapeutic compositions in balneology, enrichment and separation of core materials, and forecasting of catastrophic phenomena, and for much more other cases. And some things have already been implemented in a practice. For example, the technology of biocolloid protection of riverine storage pond of marine mineral water. Thanks to a set of nanotechnological solutions, the pond now holds up to 12 million cubic meters of water instead of previous 1-2 million cubic meters. And the last one, it should be noted that by the end of the year, we plan to complete the work on biocolloid nanotechnologies for enrichment of suspensions of poor iron ores and producing of almost pure iron oxide hydroxides with only admixtures of silicates and carbonates at the level of few persons, of just few persons. Well, it was short enough not to hold you long. Thank you for your attention. And if there are some questions, I will for them.
And they thank you for your report. Thank you for participating in the conference. Goodbye.
Goodbye.
Our next speaker is Yuri Pashkevich, the head of the Department of Dynamic Properties of Complex Systems, professor of solid-state physics in Donetsk Institute of Physics and Engineering, named after Alexander Galkin. The professor Yuri Pashkevich was awarded a number of special awards, namely State Prize of Ukraine in Science and Technology and Working Prize.
Dear Yuri, we couldn't hear you. Please turn on the sound on.
Сейчас. Okay. Do you see my screen?
No, we can see your screen. We only see the information that you have started your demonstration.
Okay.
Я понимаю, это наш экран. Could you restart the screen broadcasting?
Я должен выйти из Zoom.
Sorry?
Должен выйти из Zoom.
Нет, перезапустите демонстрацию экрана. Остановите демонстрацию экрана, после чего повторно ее включите.
Демонстрация экрана.
Он не прислал.
Today does not work.
Just a moment. We can see your presentation for now. We only see the information that you have started the broadcasting of the screen. We're waiting.
Maybe we wait a bit to start.
Just a moment.
It is written that our demonstration screen is приостановлено.
Не чую.
Написано, ваша демонстрация экрана приостановлена.
Смотрите, сверху там, где написано демонстрация экрана приостановлена, вы можете включить, то есть включите ее. Вот там, где нажмите на место, где демонстрация экрана приостановлена.
Ага, оце. Так, зараз щось з'явилося. А що ще з'явилося? Ви мене бачите?
Пока что не вижу. Не вижу демонстрации вашего экрана.
Продовжуй.
Хорошо, скажите, вы прислали нам презентацию свою?
Нет.
Нет, тогда...
Еще раз я попробую, давайте запустимся еще один раз.
Да, попробуйте еще раз запустить демонстрацию экрана.
Zoom. Почему она приостановлена?
Вот там, где она приостановлена, сверху выберите «Продолжите, трансляцию».
Нажимаю «Продолжить трансляцию».
Вот настройки просмотра рядом с кнопкой «Приостановлена демонстрация экрана».
Написано в комментарии «Дистанционное управление». Настройки просмотра, участники, так, а что ж такое? Ну, продолжим.
Сверху на экране, вот там, где рядом с приостановленной демонстрацией экрана. Его видно,
Так. Так. Так, вы меня видите?
Вас мы видим.
Так,
Презентацию вашу.
хорошо, уже победа. Так, теперь дальше что надо? Так, демонстрация экрана. Опять приостановлено.
Вот там демонстрация экрана, Анна, есть вот сверху есть настройки просмотра. Там есть, давайте я сделаю вот так. Я запрошу дистанционное управление Эни и это наши настройки.
Продолжить. У меня нет настроек просмотра ничего. У меня продолжить трансляцию,
Продолжить трансляцию, да. Нажмите «Продолжить трансляцию».
Утвердить.
Да. Так.
Так, ожидаем управления вашим экраном NFS.
Так, указываю. Ожидаем управления, да. Да, сейчас. Настройки просмотра, секундочку, теперь указывайте. Пока не вижу вашего.
Осуществляет управление вашим экраном.
Да, но... Показывать. Параллельно. Так, я не могу управлять тем, что вы остановили демонстрацию. Вы можете...
Я не останавливал демонстрацию. Я недавно проверял этот Zoom в другой конференции, все работало. Что тут, не знаю, происходит. Так, сейчас у меня полный весь экран вижу. NFS осуществляет управление вашим экраном.
Да.
Так, а где-то есть кнопка поделиться экраном здесь? Господи, экран. Там заметки докладчика, переключение.
Не дает. Мне не дает контролировать эту самую экран. Да, попробуйте переподключиться к Zoom-конференции еще раз, отключиться полностью и переподключиться.
Хорошо, сейчас я выйду полностью. Сейчас, спасибо.
Сейчас я...
Демонстрацию.
Алло, вы нас слышите?
Да, я вас слышу, да. А вы меня?
Да, я вас слышу. Ну что, теперь попробуйте, пожалуйста, включить... Да, мы вас, во-первых, не видим, во-вторых, попробуйте включить презентацию. И включить демонстрацию экрана.
Так. Опять написано, что ваша демонстрация приостановлена. Да что же это такое? Ну?
А вот там, где демонстрация приостановлена, продолжить демонстрацию экрана нажмите.
Сейчас. Продолжим. Ничего не происходит.
Хорошо.
Все время прошло.
Хорошо, давайте мы тогда попробуем вывести вас немного позже, пока что, чтобы...
Опа, сейчас вы
Опа,
запустили.
мы видим вас. Да, есть. Отлично.
Господи, да.
Хорошо, тогда, пожалуйста.
Let's start.
Я пробую, да.
Your code.
Так, запустили, но вы меня видите? Вы меня видите? Алло?
Мы вас видим, все хорошо, видим ваш экран. Пожалуйста, можете приступать к демонстрации презентации.
Он что-то не хочет мне расширяться сейчас, одну секунду. Или так уже буду делать, хорошо? Dear colleagues, I would like to present you some report about low temperature heat capacity of cobalt-containing layer double hydroxide, magnetic Schottky-like anomaly. This study is a part of a big project for study of layer double hydroxide, which is involved a few teams from Portugal, Ukraine, Belarus, and what is our main motivation for this study? The layer double hydroxide LDH are the well-known anion exchanger. Therefore, it is very important for applications, and one can affect on this exchangeability by magnetic field application if the LDH contain magnetic ions and therefore demonstrate magnetic properties. Therefore, we are much interested in these studies, and we use a few of cobalt-containing LDH compound. But now I just want to demonstrate you what are the layered double hydroxide. Layered double hydroxide is a so-called clays, which is consists of positively charged mixed metal hydroxide layers, which is shown here, and in between these layers, we can include some anions to compensate the additional positive charge of the layers. The nature of anions can be very different. It can contain inorganic molecular or even organic molecular. The possible to make the layer charged, we use the different content of metal plus and metal 3 valence state. The ratio of this metal state can be varied from 1 to 5, and the most favorable ratio is 3 or 3. Charge of the hydroxide layer performance dictates by this ratio of metal 2 and metal 3 valence. The most interesting for application ability of this compound connected with very low hydrogen bond energy. Because of these two layers connect mainly by hydrogen bond energy, so there is very low scale energy. Therefore, if you put this clays of the LDH compound in some water with different pH value, then some anions can be included in between the layers, and another one removed from the layers. So this LDH is anion exchanger can be used in catalysis and corrosion protection, drug delivery, and so on. And more structural details, which is important, is the structure which consists of octahedral layer and metal 3 and metal 2+ can be very different, and when one can use very simple very simple ratio of metal 2 metal 3, and which is defined by the anion content, which can be included in between these layers. Here we show these layers, and in between there is a few anions and some water molecule. Therefore, because of this ratio is most important, one can use very short description of this LDH compound, namely the number of metal 2, which is named by number n, and metal 3, and some anions. And next, most important building block of LDH is a octahedral cage, which consists of oxygen with some hydrogen above, so this hydroxyl group, and which has roughly average D3D local symmetry. And also important things, I just want to say that average crystal symmetry is a group which contains axis of the third Cole axis. FDH nanopowder samples can be prepared by conventional precipitation method, and you see here powder sample of cobalt, aluminum, and nitrogen nitrates, and you see here that this STM image demonstrates that if we change the ratio of cobalt to aluminum, then we have changed a bit the form and size of the nanoflakes. In general ratio, general law, which we can see here, that the aspect ratio decreases if we increase cobalt content. So cobalt 2 aluminum consists of nanoflakes, which is very well defined by the size. What about magnetic properties of cobalt-based LDH? Magnetic properties we should expect if we have some exchange interaction between cobalt ion, and this exchange really exists. And we show here some result of magnetization measurements of our cobalt-2 nitrates measured in magnetic field, zero field cooled technique and field cooled technique. You see here that around 5 Kelvin appears some peak, which can be explained as some kind of magnetic ordering. However, the measurement of the dynamic susceptibility demonstrates that there is some dependence on the frequency of this peak, which shifts under change of the frequency of the measurements, which is strongly point to spin glass behavior in this compound. If we start to measure low temperature heat capacity, we see that at zero external field, we see a very nice peak around 5 Kel, which is very nicely correlate with magnetization onset. And this anomaly, this is shown in the black curve. This anomaly will completely disappear in this scale, right, in this range, if we apply the field. It smoothly disappear if we increase the value of the field, but it is almost disappear if we apply 5 Tesla, approximately 5 Tesla. And here I should mention that the measurements were done by the powder sample. So we have not any preferable direction of the field and any preferable direction of our nanoflakes under these measurements. And how we can explain this behavior? This explanation can be very simply related to the energy level structure of cobalt-3+ ions. Indeed, if we consider cobalt ions and the energy scheme of this ion, this is cobalt-2+ or 3d7 Kramers ion, which at 3D configuration should have, after including spin orbital interactions, should contain 4 low energy Kramers doublets. So next we can proceed just to manipulate with internal magnetic field, which arise below 5 Kelvin, and then calculate the splitting of Kramers doublets due to internal exchange field, and then obtain the behavior of this Schottky-like behavior of this peak. And we modulate this internal field, which exactly repeat the behavior of the magnetization, and we use this 1.39 Tesla as maximum internal field at 0 temperature. And then we try to calculate what happens with this peak and what happens if we apply the magnetic field. This is a very simple idea, and we did this, but then we will see some strange behavior, experimental behavior, which is not was not accounted in our simple approach. There is some strange contribution to heat capacity at lowest T in black here in the black line, in the starting of black line, which completely disappears under increase of the exchange external magnetic field. So in the red line, you see that here some space. This is very strange behavior because of if we use our model, then we should not see any this contribution because of mostly all Kramers ions should contribute to this peak and nothing at the low temperature. Therefore, we should be consider the situation more carefully, and we go back to the structural features of the cobalt aluminum LDH. And in an ideal order implies some superlattice. This superlattice is shown here. You see here this new supercell, and you see that the only one kind of cobalt ion nearest neighbor in coordination exists in this case. But unfortunately, in the X-ray studies, there is no any superlattice break peaks, which never been observed in this compound. So it means that our ideal picture is not realized in the nature. So we should the aluminum ion should be distributed in this lattice in this octahedral layer in some random space. So this you see here this randomization, and after that we should stress that not only one possible coordination cobalt ion exists, but there are a few different coordinations. For instance, I show you here in this random picture of aluminum distribution two possible coordination of cobalt ion with its nearest neighbors, cobalt and aluminum. Here you see here some ideal path, which consists of 3 cobalt and 3 aluminum. But here you see only 2 aluminum in open circle and 4 cobalt ion. What does it mean from point of view more careful consideration? It means that we should include a few possible, not a few, but all possible cobalt ion coordination. And in some limited case, we should consider only statistical distribution of this possible coordination. And this is it.
I'm sorry for interruption. You got only 3 minutes left for presentation,
Okay.
and we have to move to the questions and move on.
Okay.
Thank you.
Okay. Then we will see that because of strong difference between ionic radii of aluminum and cobalt, at each coordination we will have very specific, a very individual but strong corrugation of this octahedral cage. And it leads immediately to the strong variety of energy level and G factor. Here I present you just 2 examples of this behavior. And after that we calculate, so we know this using Shannon radii, we estimate all distortion of in each case of cobalt environment, and we put all of this in our calculation, and we observe this kind of behavior for heat capacity. So we see here that that we include here all coordination of all coordination. We include here all possible orientation of magnetic field, a few numbers of this. We put here internal field which is directed along z-axis, and then we obtain this behavior. What we see here, we see that in theory that the contribution of magnetic degree of freedom spread into high temperature range and with weighted spectral, with widening of spectral weight. And if we use experimental value and for in this scale c divided by t square, then we see that instead this smooth behavior, we see some remnant of peaks of different field. Even at 5 Tesla, we see some remnant peak, which means that the magnetic degree of freedom contribute to this behavior. And also what is important, we see here what is the reason for appearance of this small contribution at 0 field, because of we have a few possible coordination which contribute with very small Kramer's doublet splitting. Therefore, they can contribute at very low temperature in 0 magnetic field. Now I come to my conclusion. The low temperature heat capacity of cobalt ion does not show lambda peak typical for the magnetic order. Instead, we observe Schottky-like anomaly, which is expected for spin-glass behavior. The action of magnetic field leads to the suppression of the Schottky-like anomaly, with shift and spreading in magnetic contribution into high temperature range. The LDH does not compound, namely cobalt-2 aluminum NO3, does not show expected long-range structural order. However, one can conclude about presence of large spot with short-range structural order. This is very important for the magnetic properties. And the structural disorder leads to the presence of cobalt coordination, which with wide variety of Kramer's doublet energy and highly anisotropic G factor. Now, I just want to stress that we deal with a lot of different anions. I show you here only anions with NO3, and also our acknowledgements. This we will see here. This is to the few project which were done, which now is going on. And thank you for attention. Okay.
Dear Professor, thank you for your report and see you at the next conference.
Okay, thank you.
Our next speaker is Dr. Evgen Polunkin. He is the head of the Department of Homogeneous Catalysis and Additives for Petroleum Products of Puhar Institute of Bioorganic Chemistry and Petrochemistry. The title of the report is Improving the Chemical Properties of Diesel Fuel Using a Micro-Additive of Carbon Spheroidal Nanoparticles. Okay.
Evgeny, can you hear me? Can you hear us?
Yes, yes, I listen.
Okay, thank you. Thank you. We're ready to listen to your report. Or please show us your screen, and you have 10 minutes for report and 5 minutes for question.
Yes, yes, yes.
Okay.
Good. One moment, please. Yes. Good evening, ladies and gentlemen. I want to say about improving the chemical properties of diesel fuel using micro-additives of carbon spheroidal nanoparticles. There are now that many different allotropic modification of carbon in their having nature. We study in first step, we study the different fluorines, examodified and clear fluorines, carbon 60, and his different derivatives. This very interesting compound that have very good properties, another antioxidant substances. We study of nitrogen containing fluorines, different hexaedral modified fluorines in model reaction of inhibition, oxygenation of benzyl alcohol. And we obtained very interesting result. We have obtained the constants of oxidation chain termination of benzyl alcohol in the presence fluorines and hexaedral derivatives. In this slide, you can see the constant of this compound in this reaction, in model reaction. And we found that different compound have beautiful properties, another antioxidant. And from the nitrogen hexaedral fluorines, we found that these fluorines have ability work another catalytic properties, catalytic substances, and this is the first we first who found this catalytic activity from carbon nanoparticles. After that, we see the symbiotic change of antioxidant and anti-wear properties of hexaedral fluorinated fluorines. This is very interesting that symbiotic properties of this compound give ability to do analogies between antioxidant properties, and properties anti-wear. And we first to fullerene, we found that this compound work most beautiful that industrial additives in bioethanol fuels, and we do the models of domain which nanoparticles build the domain spheroidalic construction from molecule of solvent around these nanoparticles, fullerene nanoparticles. After that, but fullerene is very have big price, and we want to found more substances which have low price. And these particles is the spheroidal multilayer nanoscale carbon clusters, or another name of carbon nanoonions. These carbon nanoonions we do self. In this slide you have ability to see ideal and real structure of carbon nanoonions and its agglomerate in the slide on the down slide. We do the equipment. On this slide, you have ability to see this equipment from plasma chemical synthesis of nano onions from gas raw materials. Synthesis, we do the synthesis. These products was we obtained nanomaterials by method of high frequency discharge pulse synthesis of tungsten electrode using hydrocarbon gases as raw materials. After that, we do the functionalization of these carbon nanoonions by different methods, by nitric acid, bromine, and chlorine. We do extraction of nanoonions for different analysis by atomic force microscope and spectroscopy measurement, Raman spectroscopy, and another method of investigation of these nanoparticles. Atomic force microscope photo you can ability to see now in this slide. The size of diameter, of these nanoparticles in range of 42, 32 nanometers. And when we change the frequency of this equipment, we obtained smaller nanoparticles is 15, 20 nanometers. We do the Raman spectroscopic investigation, and on this slide you can be to see halogenated nanoonions, Raman spectrum of these halogenated nanoonions, and infrared spectrum in range 1029. We have the line of carbon fluorine line. We do the investigation, salvated the dynamics radius of carbon nanospheres in solution by photon correlation spectroscopy. And we if in the case of self diameter of nanoparticles in 2 or 45 nanometers, Gauss distribution, maximum 22 nanometers. But in solvent, you have ability to see in different solvents, they have different diameter of this nano solvent nanospheres. This is a very interesting fact, and we do the model when these nanoparticles salutation in solvent in ethanol in this case have a big diameter, another 100, 500 nanometers. And we build the model, this hypothetic structure, which we give the name domain in polarizated space of which do the nanospheres, and molecule of solvent builds this domain. And we study the kinetic of oxidation, inhibition of oxidation benzyl alcohol in initiated oxidation in model reaction. And you can ability to see that in this slide that when grows the concentration of nanoparticles, speed of oxygenation of model solvent benzyl alcohol lower, and that slide said that this nanoparticles is a good inhibitor of oxidation of solvent when we give a more biggest concentration of these nanoparticles. In this slide, you have you see that effective constants of inhibition rate benzyl alcohol with carbon nanospheres, fluorines, and halogenate analogies. And effective constant by peroxyl radicals, inhibition by peroxyl radicals, two carbon nanoions, most biggest, most beautiful, that this constant to fluorine, and in down part of this slide, you see the industrial inhibitor of oxygenation in different factories products process. Sorry. And this fact said ability do this work most interesting, and we investigate the influence of carbon nanoclusters on the auto-oxidation of benzyl alcohol without initiator, and we obtain the same result. In this slide, in the table, the result of investigation gas liquid chromatographic of this solvent, and dependence of dynamic strength and electric capacity of ethanol solvent, concentration of carbon nanoparticles, carbon nanoions that have a maximum, have extremum. Sorry. We study influence of carbon multispheres, nanoclusters, bromide onions on anti-wear properties and scoring resistance of jet fuels. In this slide, you see that small quantity in all additives in industry, in chemical compounds, molecular compounds, another dialkyl phosphate of zincum, and another industrial additives in all factory they are given 0.3%. But our nanoparticles work in 100 smaller concentration, and this very interesting fact. After that, we study tribology in the stand equipment, measurement equipment, we do in National Aviation University in Kiev. This stand with is a different fast profilometer with laser scanning of surface. After that, after this model investigation, in this slide you see surface with gasoline A95, surface biofuel A85, and the same surface ethanol fuel with our additives. This in this slide you see that this surface smaller destroyed when we give in this solvent our additives. And in this there are no that head of combustion ethanol fuels on 20–30% smaller that hydrocarbon fuels. But when we give additives in model two-stroke engine, we see that very interesting fact that we see that consumption, this milliliter in 1 minute, is the same, and these nanoparticles give additives of head in this process of flammable in cylinder group in this engine. In this slide, the ecologies comparable with gas, carbon oxide, and carbon dioxide, and hydrogen carbon, which don't fire in the engine. And our additives excess gases exhaust gases on function of ethanol consist. We do comparable bench test with spark plug ignition of gasoline either A95 and gasoline modified with additives. And in this slide, you can ability to see that
I'm sorry.
economy. Sorry.
Dear Professor Blumkin, your time is almost up. Please.
Yes. This is finished.
Okay.
Yes.
Thank
According
you.
to the result obtained when adding micro quantity doses of synthesized nanomaterials to the fuel consumption decreased by 6–10%, and according to the effective efficiency increased compared to small indication when the engine was running in the some mode of fuel without additives. And in this slide, you have ability to see the indicator diagrams, which you see that pressure most biggest, and our additives, the analysis of the fuel combustion process in the engine by method of indicator expanded indicator diagrams show that the effect of the addition of synthesized nanoparticles on fuel efficiently in the engine due to change in the degree of conversion of combustion energy of fuel component into thermal energy. And this diagram for the indicator diagram. And sorry, I didn't read resume. You have ability to read in the display. Thank you. Алло. Алло.
Thank you very much for the report. And Viktor Kisluk want to ask you, do these additives have impact on the nitrogen oxide generation, which is a problem of the diesel combustion engines?
Yes, when we obtain the very interesting fact, the percent of carbon oxide and carbon carbons smaller, but in case of nitrogen oxide, the nitrogen oxide in different case of biggest or smaller. This is a very interesting fact. This fact comparable with temperature in the cylinder group.
Thank you for the answer, and see you at our next conference.
Thank you. Sorry that different.
The last speaker of this session will be Ms. Marina Drigaila, a bachelor student in the Faculty of the Physics at Karasin-Kharkiv National University. Also, Marina is a research student at the Institute of Single Crystals of the National Academy of Science of Ukraine. She was a scholarship holder from the Konrad Adenauer Foundation during the last academic year.
Вот.
Нет, выше.
Выше.
Мгм. Не видно будет.
Сейчас я включу, а у вас сейчас будет видно. Я... Пожалуйста.
So, good evening, dear colleagues. And today I would like to present my research, fundamental research of impact of presence of amino acids on calcium oxalate monohydrate, or I will shortly call it COM, crystallization processes in conditions imitating human organism. So, the COM crystals were obtained using hydrothermal synthesis in the presence of 3 different amino acids in 5 concentrations. These amino acids are phenylalanine, methionine, and lysine. The initial solution was consisted of sodium chloride that gave the ionic force of 0.15 moles, and acetic acid that gave the pH level of the solution 5.8. The temperature of the solution was 37 degrees. In addition, in this research, we used such types of equipment that you can see on the slide. Here are the diffractograms of the pure COM and COM with the adding of 3 different amino acids. As you can see, the peaks with the different amino acids match their reference peak that is the COM, the black one. And it means that the crystal structure of the COM is not broken. The same results we could see when describe the infrared spectrum. All of these peaks with AgNF amino acids match the reference one. Here are the crystallization curves for the COM. We considered only two concentrations of amino acids, the minimum one and the maximum one. Why? Because they show us the main difference in the induction time. And it is noticeable that the biggest and the sharpest rise of the crystallization graph is when methionine is added. And we made the conclusion that all of these amino acids are promoters of the crystallization of the COM. On this slide, pictures, photos from the scanning electron microscopy are shown. As you can see, with the increase of the amino acid concentration, the COM single crystals start to form conjunctions that can be assumed as COM renal calculi in vitro. The single crystals are about 5 micrometers in length and have ideal and non-ideal hexagonal form. Our main results are following. All amino acids are proved to be promoters, and increasing of concentrations of amino acids reduces the induction time significantly. Thanks for your attention. Your questions are welcome.
Thank you very much. Please, who have questions about the report? No questions? Dear Marina, thank you for your report. Thank you for participating in the conference, and see you at the next conference.
Thank you.
Thank you very much. Dear participants, the section Physicochemical Nanoparticle Science is closed. Now will be the next section with title, one moment, with the title Nanostructure Surface and Nanobiotechnology for Healthcare will be open.
Good afternoon for all who has joined us for nanostructured surface and nanobiotechnology for healthcare sections. We decided to unite two sections in one for convenience of our participants. Let us start with a talk entitled conductance tips in point contact and their reflection spectra, which will be present Professor Mikhail Belogolovsky from the Khalkin Donetsk Institute for Physics and Engineering, NAS of Ukraine. So, Professor already with us. You are able to listen us?
Can you hear us?
Yeah.
Do you ask me?
Okay, so Yes, yes, yes.
Yeah, yes, I'm hearing you. Yeah.
Yes, we already in connection. So please, you should start your presentation. And I just would like to all participants remind our reglement that it's something like 10 minutes for talk and 5 minutes we should left for questions. Please, we have at the moment to need follow this rule. So we should start.
Yes. Do you see my screen or not?
No, unfortunately, we can see your screen. Please, in the Zoom, select the bottom screen sharing. It's a green bottom down on the screen in the Zoom.
One moment. Yes, I thought that it was selected by me. One moment. No, one moment. One moment. To enter the conference, yes?
Sorry?
I see. Войти в конференцию, yes?
No. You don't have войти, enter to the conference. Не нужно войти в конференцию, вам нужна демонстрация экрана.
Yes, I saw it.
Вы
Most probably, наверное, мне надо повторить заход в Zoom, да? Я все это делал.
Да, отключите сначала, остановите свою демонстрацию, а потом включите повторно.
Now we have. So now we have a couple of minutes, and I would like to a little bit introduce our professor Mikhail Belogolovsky, and he is the head of the Joint Laboratory for the Dynamics of Electronic Processes in Hybrid Structures, created by the Institute of Metal Physics, National Academy of Science of Ukraine, and Donetsk National University, which is now in Vinnytsia. He is a vice president of the Ukrainian Physics Society, responsible in particular for helping physicists displaced from Eastern Ukraine and Crimea. Since the 1990s, he has been actively cooperating with colleagues from Germany, France, and USA, and other countries. This work which he will be present is a result of his joint activities with Slovak partners.
Have not you seen?
Okay, thank you. We can see a screen. Please enter your presentation because we can see only your browser. Yeah.
Yes, clear. So it was necessary. One moment.
Okay, start the slideshow and you're free to start.
Have you seen, yes?
Yeah.
Me and you seen the screen, yes?
Yeah, we can see your screen. Thank you.
Okay. So thank you very much for the presentation. It's really a joint work with Slovak colleagues. And what I want to tell is about some anomalies, some strange features in point contact and tunneling spectra of superconductors. The idea of these two spectroscopic tools for studying superconductors is very simple. So you have two metallic electrodes, and without voltage bias, there is no current across such a heterostructure, since the chemical potentials are equivalent both sides of the junction. If I apply voltage bias, in this case, free states appear from one or another side of the junction, and there is a current. If both metals are non-superconducting normal, there is nothing interesting and simple. We have an ohmic behavior. So the current is proportional to the voltage, the conductance is constant, and nothing else. So if I replace at least one of two metals with a superconductor, in this case, in the spectrum, energy spectrum of a superconductor, there is the energy gap, and up to some voltage, there will be no current, and after that, the current emerges. So it is the method how to directly measure without even any fitting procedure to measure the energy gap of superconductor, and how to know the influence of external factors only. So between the two metals, I should have a high resistance interspace. Usually it is created by two different tools. The first one is a point contact. So there is a normal tip in touch of a superconductor. The second possibility is a tunneling junction, when we put a nano thick insulating layer between two metallic electrodes, films. In principle, to calculate, to find theoretically what will be the current voltage characteristic is sufficiently simple, but we should take into account one very important feature. Imagine an electron with the energy less than the energy gap arrives to an interface between normal and superconducting films. If the energy is less than the gap, it is forbidden for it to enter into the superconductor. And what it can do, it takes a partner. A partner, it is another electron with an opposite spin and opposite momentum. They form a Cooper pair and enter together into the superconductor. What does the second electron leave after it? The hole. So it is the special processes which occurs only at the interface between normal and superconducting films, and is known as Andreev reflection. So the electron is scattered back as a whole. If to take it into account, we can after that calculate the differential conductance, so the derivative of the current over the voltage. Here you can see it is known the typical characteristics. So if we have an ideal point contact, so an ideal contact between two metallic films, in this case we have such a dotted curve, a black curve. So it is the differential conductance normalized to its value in their normal state. So there is a flat region up to the gap, and after that it goes to unity since it is normalized. And in the inverse case, when we put an insulating layer between two films, in this case we get the density of states of a superconductor. It is a green curve. So there are peaks just at the gap values. What I said that it's a way how directly find from experiment the gap values in a superconductor. And all was okay when we were dealing with trivial ordinary superconductors. But when research is transferred to transition metal superconducting compounds, some problems have appeared. The problem is that the measured characteristic is not very similar to the theoretical one. And especially there are some features which often have been observed in such curves. So some features that cannot be explained with this well-known theory. And our task of this work was to explain maybe the most popular such unusual feature. It is the conductance dips. Now I want to show experimental results obtained 20 years ago by other colleagues, where these features were discovered for the first time. So in the center, there is a tunneling conductance, so it is a tunnel junction where the authors expected to obtain to see the green curve. But instead of this, they observed peaks. But after this peak, there was a gap, and after this gap, there was a small peak named hump. So people usually dubbed this structure as peak deep hump structure. What does it mean and where there is the energy gap? Now about point contacts. Imagine that we have an ideal direct contact between normal and superconductor. What happens in this case? Here there is again a figure taken from the paper which was published about 20 years ago, where the authors changed the combinations of the two normal metallic films, normal metal and superconductor, and observed such really a flat region, as I told. So they expected to see the black curve. Really there was a flat region, but after that suddenly there was a dip. And what is the origin of this dip? Now our explanations, what we try to say about the origin of these anomalies. For example, we have I start with a tunneling junction. So we have a three-layered structure which consists of normal metal, an insulator, and a superconductor. Our hypothesis is that we are dealing not with 3 layers, but with four layers. So we suppose that the superconductor has a nanostructured surface. And in this surface, in the nanometer wide, this surface sheath, the superconductivity is suppressed, maybe totally, maybe partly. So here in the theoretical model, we have a normal counter electrode and very thin insulating layer, and the electrons may quantum mechanically transfer it. And this normal or superconducting layer with the suppressed gap and the superconductor. What happens in this case? As I told, imagine that the electron is arriving at the NS interface between the two metallic layers. In this case, it is scattered back as a hole. This hole is scattered from the insulating layer, and again, it is now transferred by Andreev-like retroreflection into electron, and the electron goes back. So we have such a round trip of an electron. During this trip, it survives the transferring into a whole state. And as we know from the elementary quantum mechanics, that the phase acquired during such a round trip should be equal to twice pi multiplied by integer. And this condition defines the bound state in this degraded surface layer.
I'm sorry
So
for
after that we can...
Professor, you have just 3 minutes left, and we have to go into the question.
So I should accelerate, you want to say, yes?
Yes, exactly.
So the same hypothesis we used for interpretation of NS point contact. So the presence of a surface layer with suppressed superconductivity. And here you can see experimental curves of our Slovak colleagues, which we can explain with this explanation. And the last part of my talk was that during this explanation, we had 3 assumptions: the degraded layer, the direct contact between a normal tip and the superconductor, and semi-transparent interface between the degraded and the main superconducting bulk. So our idea was to fabricate such a system artificially and to see if conductance dips appear in such characteristics or not. So it was done by Slovaks. So we had such a 5 layered structure where platinum was a counter electrode. Here it is an interlayer with very small resistance, aluminum and niobium nitride, where superconductor with a small gap and with a strong gap, and they were divided artificially with a very weak paramagnetic layer. And here, this figure, you can see that rarely we observe such deep regularity. So we hope that we understand now the origin of the conductance deeps in these junctions. What is important from the spectroscopic viewpoint is that now we understand that the real gap value is not the peak in the tunneling characteristic, or not the boundary or the flat regions in point contacts, but just dips define the real position of the gap values in the superconductor studied. So it's my conclusion, and if you have questions, thank you for the attention. I will be glad to answer them.
Thank you a lot for a very important contribution to work of conference. And please, if you have some question, please ask. Please. Yes, yes, exactly.
Thank you for your talk. Could you please tell us which formalism did you use for calculating the reflection probability of electrons or holes or other or quasi-particles from the interfaces between different regions of your structures?
Yes, so the formalism, traditional scattering formalism, where we have transmission and reflection coefficients, and we are summarizing the probability amplitude for the whole structure. And what is new in this situation is that we should take into account this Andreev retroreflection when the electron is transferred into hole, the hole is transferred into the electron. So it is traditional standard scattering theory, only modified with this specific feature which appears at the boundary between normal and superconducting layers.
Thank you.
Thank you a lot again. So we are going to the next speaker, and next speaker will be Professor Andriy Horyachko from the Institute of Physics of the NASA of Ukraine, and also he has a second affiliation. It's the National Taras Shevchenko University of Kyiv, and his report entitled as self-assembled rare as nanostripe arrays in the Selenium-112 system. I would like to add a couple of words about Professor Andriy Horyachko. He's an expert in the field of scanning probe microscopy, electron spectroscopy, diffraction, and other surface analysis techniques. He teaches various advanced courses at the National Taras Shevchenko University of Kyiv, such as surface science, modern microscopy, integrated electronics, oscillation and waves, nanophysics and nanotechnology, and etc.
Can I start?
Yes, so please.
Good afternoon. So you see the title of my talk is about self-assembled rare earth nanostripe arrays in the cerium molybdenum 112 system. Page down. So first about the motivation, rare earth elements, in particular cerium nanostructures, are of great importance for nanotechnology, nano-optoelectronics, catalysis, medical applications, etc. Practically useful, functionally tailored nanostructures usually have to be placed on some metallic substrate. And the molybdenum-112 is such a very interesting substrate on which self-assembled long-range ordered nanostructures of alkali earths, and rare earth elements can be formed due to intricate interplay of anisotropic surface properties, elastic effects, and long-range interactions mediated by substrates electrons. Here on this slide, can I see the pointer, by the way? Yes, please. Okay. So here on this slide, you see just one example of such work where I think gadolinium is forming such linear chain nanostructures on top of molybdenum-112 substrate, but generally there are a lot of works in this area already performed by other scientific groups. And so this is right here in the at the bottom of the slide. You can see this molybdenum-112 substrate. It is an isotropic substrate, consisting of ridges and troughs, and with two different interatomic spacing in the plane of the molybdenum-112. Here, 0.445 nanometer, 0.273 nanometers. And how do we investigate this substrate? We use theoretical density functional theory calculations, and in order to simulate the surface properties, we form such a fictitious three-dimensionally periodical solid, where here in the bottom part you have some crystalline structure of molybdenum and any cerium adsorbed atoms which may be there, and followed by a rather thick enough so-called vacuum gap or vacuum region, and entirely they form a three-dimensional unit cell that repeats itself in three orthogonal directions, x, y, z. And then the density functional theory, as you know, allows us to calculate the total energy of many electrons moving in the field of many atomic nuclei. And by this, we can extract various properties like the adsorption energy by means of finding the energy of the systems containing cerium adsorbate atoms or without them, according to this formula, and so on, and many other properties. Here you see the details of our density functional theory calculations. Then also I would like to introduce a couple of useful definitions. First of all, the definition of coverage is the ratio between the areal concentrations of the topmost molybdenum atoms in the topmost atomic layer of this sample and areal concentrations of the cerium atoms. And also the definitions of surface superstructure, L times N, means that if the adsorbed atoms are placed with the lateral periodicity L or M times larger than this interatomic spacing of the molybdenum substrate itself, then we call this an L times M or L by M superstructure. And so we start really with the linear chains like this, with the coverage of just 1/6. We can have linear chains or the zigzag chains, and then the adsorption energy shows us, these are the energies per atom, per a single adsorbed cerium atom, shows us which energy is energetically favored and therefore should be realized in a real experiment. Then as the coverage increases at 1/3, we have two nearby linear chains, and they can also be linear with varying distances between neighboring cerium atoms. Here we see some kind of a tendency for the formation of cerium surface dimers, or they can be zigzag chains. And in this case, the adsorption energy tells us that the zigzag chains are more favorable, and therefore we should expect to see them in experiment. The same thing goes when we add the third linear or zigzag chain to the previous two ones. Now, at the coverage 1/2, we have the uniform film over the entire surface. And in that case, we have found two equilibrium structures, one with a primitive 2x1 superstructure unit cell, another with a centered 2x2 supercell. And the absorption energy shows us exactly that the C2x2 structure should be realized by nature in the experiment. Now we go further, higher with coverage 2/3. Again, here the tendency to form a surface cerium dimers shows up, so the neighboring cerium atoms become closer. And then the so-called zigzag arrangement of these dimers is preferred, like you see here in the right part of the slide, with a superstructure 3x2, 3x2. Well, this structure is actually preferred. Finally, we have only reached up to a coverage theta = 1, and in this case, we have already non-primitive 2x1 superstructure unit cell. Here you see it in comparison with the previously shown P2x1 superstructure for theta = 0.5, and also you can see the side views of our slabs, which were actually used in our calculations, thus simulating the surface of this adsorbate substrate system. Now I want to show the intermediate conclusions from our numerical calculations. So we can say that the stable periodic linear chains running in this direction formed out of cerium add atoms are stable at low coverages. Then there is a strong attraction between the chains when coverage increases. Two or more adjacent linear cerium chains rearrange into zigzag change, resulting locally in the C2x2, should result locally in a C2x2 superstructure formed by cerium atoms. And therefore, at the niche, if we would compare it with the experiment done by means of thin film growth, then we should say that the initial stages of submolar cerium film growth on the molybdenum 112 substrate should proceed through the formation of islands of the C2x2 cerium at atoms phase. Then at theta = 0.5, there should be a uniform film with a C2x2 superstructure. It is energetically the most favorable, and in particular, if compared with the P2x1 arrangement. Then at theta = 2/3, there is a clear tendency of cerium dimers formation, the later being arranged into a P3x2 superstructures. And finally, at coverage equal unity, there is a uniform film of a P2x1 superstructure, which is energetically the most favorable state. And also these conclusions, as you see over here, must be experimentally verified. So we use the low energy electron diffractions, thus utilizing the wave nature of the electrons, which were incident on the sample. And then as soon as they behave like waves, they diffract on the crystalline grating formed by atoms of the substrate and the adsorbates, and then we can see what is the symmetry and the periodicity. We can deduce the symmetry and periodicity of the sample from the diffraction picture that we observe on this fluorescent screen. So there you can see the diffraction from the pure molybdenum 112 substrate. Here there are the principal first order diffraction spots. Then if we grow the film, actually as a coverage 0.63, we see these additional diffraction spots, diffractional maxima, which appear, and they correspond to the P2x1 odd layer. So there is a doubling of periodicity only in one direction. Further, we don't see any other structures during this experiment. If we add more cerium, like here for reaching up to theta = 1.5, at 300 K substrate temperature, we only get an amorphous layer because there is no coherent diffraction whatsoever, and the diffraction image is dark. So from there, we can say that surprisingly, we detect the P2x1 add layer structure, which is energetically less favorable than the C2x2. And the later was never observed, although it was predicted by the density functional theory theoretical calculations. Then we tried to anneal our samples at 1400 K. This is done because at higher temperatures, surface atoms can have higher mobility. They can move around and actually try to find energetically more favorable positions on the substrate. We still didn't see any C2x2 arrangement as predicted by theory. Instead, we have seen a number of other structures depicted here by means of lead image. And apart from the already named P2x1 structures, we have also seen so-called P2x1 plus P n by 1, meaning there are diffraction spots very close to each other that corresponds to a very long, already mesoscopic periodicity in real space. Then this periodicity becomes even larger because the spots here, the splitting becomes smaller and smaller. And also at higher than 0.5 coverages, we have observed a C8x4 superstructure and C1.4 times 2 superstructures. Now, if we get to this splitting S, this split components designated by the letter S, which are at a distance delta from the principal first order diffraction spot of the molybdenum 112 substrate, then we can actually calculate the number of surface substrate units as the surface prelude zone size divided by this split in delta. And then we get the number of units of the molybdenum 112 substrate corresponding to the observed long range periodicity in real space. And as delta goes to 0, while coverage approaches 0.5, this long range periodicity is divergent, as you see here. This is the domain size, lattice units corresponding to this green curve. So this is already a very interesting observation, but then we should also try to answer the question, why is the P2x1 structure observed instead of the C2x2? We don't have a definitive answer yet. We don't have any conclusive proof. However, by citing this work, we can say that a similar system was observed where strontium was absorbed on molybdenum 112, and it turns out that the oxygen impurity can indeed stabilize the preferred C2x2 structure, which is also the case here in case of the atomically pure system, in favor of this C2x2. P2x1 superstructure can be stabilized should the oxygen be present in a rather small concentration on the surface. It turned out that by means of Auger electron spectroscopy, we have indeed found the oxygen impurity, or it can be considered as the oxygen doping. The oxygen atoms in these atomic models are designated by small red balls. And so we have just a qualitative, speculative and tentative suggestion that these oxygen atoms in such positions, should they be present, they stabilize this P2x1 superstructure in favor of this C2x2, which should have been present in case of an atomically pure system. In our experiments, we had from 1 to 25% of oxygen impurity in our serum odd layers. And so we believe that it is these impurities that leads to a P2x1 superstructure formation. And the most important thing that actually it may be simultaneously responsible for the establishment of this long-range mesoscopic structure, the model of which, proposed model of which is shown here in the image C. So we basically have the nanostripes arranged periodically with the periodicity in real space equal L, and that is this number of substrate units N from the previous slides, times 0.273. And in between these serum ascorbate nanostripes, there are regions of uncovered molybdenum 112 substrate. Then also for for the higher order structures like C8x4 at higher coverages and C1.4 times 2. Again, they appear at coverages 0.64 and 0.7. So this is, in fact, in case you remember, is the coverage range where the cerium dimer phase with a 3 times 2 reconstruction should appear in case of the atomically pure system. But again, as soon as we have the oxygen impurity, we believe that structures with the following arrangement of cerium atoms should be present as the ones which would correspond the lead diffraction image. And again, I would stress that the oxygen atoms are not shown in these models, although they are definitely present in our experiments. And actually now I can already pronounce the conclusions of our work. This is already the conclusions from experimental observations. So the first one, only the P2x1 superstructure is observed after cerium deposition on molybdenum substrate at room temperature. Then we have a whole number of different superstructures. They are listed over here. They are observed after annealing in the temperature region from 1200 to 1500 K in the coverage range from 0 to 0.75. Then the disagreement between density functional theory predictions and experimentally observed surface structures are believed to be caused by oxygen impurity from 1 to 25%, which was always present in our cerium odd layers, according to Auger electron spectroscopy measure. Then the Pn×1 superstructure is a self-assembled one-dimensional mesostructure with a period of more than 24 substrate units, substrate atomic units, appearing at cerium coverage from 0.1 to 0.45, and it is essentially an array of parallel stripes with a lateral periodicity starting from 6.5 nanometers in real space, and consisting of highly defective P2x1 cerium at atoms phase, separated by the stripes of pure molybdenum 112 substrate. And the driving force of the mesoscopic self-assembly, which leads to the structure, is believed to be an instability of the surface with the mosaic surface stress tensor towards formation of elastic stress domains plus electrostatic interaction between the areas with a different electron work function. These are the areas with and without cerium. And of course, further investigations are required to reconcile theory and experiment, both atomically pure cerium molybdenum 112 and cerium molybdenum 112 with some precise control of oxygen content. So the investigations of such systems, both experiments and theoretical, are of course necessary to figure out and to understand why these structures are formed in a way as they have been observed. Thank you very much for your attention.
Thank you very much for interesting talk. And are there some questions? Thank you again for our speaker.
Thank you.
We have to go on to next speaker. It will be a young scientist from the also Institute of Physics. His main scientific interests are liquid crystals physics, especially optics, photo alignment, and defects in liquid crystals. Also liquid crystals optic devices. His PhD student, Pavlo Golub, maybe you already know his as a member of our organizing committee. And the report titled as Topological Defects, Movement Control in Liquid Crystal Cells.
Oh, good morning, ladies and gentlemen. And so my name is Pavlo Golub. As my colleague presented me here, thank you for your time. And now I will speak about the movement control, all of the topological defects. Usually the topological defect is controlled by changing some internal parameter of the liquid crystals, like changing chirality, or when you change some properties on the surface. So when we started work with the liquid crystals, crystals topological defects, we found that if you use some chiral dopant to control all that depends on irradiation or temperature, it's we get problems with actually temperature, because when it gets hotter or colder, the chirality changes, and the defect starts move unexpectedly. So we started to think, what can we do to leave ourselves without all this defect. And so we started to think, what if we control all the defect movement by the changing of the surface alignment? And so we build the liquid crystal cells which consists of two surfaces. One was linear circular rubbed by rubbing roll, and another was oriented by photo alignment method, as a linearly. Yeah, actually, I need to say some words about photo alignment. What is it? It actually photo alignment is the method when we when you give to the surface make surface some oriented in some direction, like it could happen and just because of, for example, all changes surface like transistomerization or bulk mediated for line, when the liquid crystals molecule are absorbed to the surface in some direction. And so in our experiments, we have used the cell geometry. When on the one surface, we have used the linear rubbing in the planar cell, and then axial rubbing between in these glasses. There were other liquid crystal called 5CB. And for the aligning surface was PVC and low oil, which we oriented by the polarized UV light. Right? When we filled the surface with liquid crystal, we could see such a defect, as you could see on these pictures. It's a linear defect, but unfortunately we got at it a little bit distorted. That's because the some imperfections in the surface rubbing. It may be that. So when we filled the surface as the linear defect were formed, and this is that defect we wanted to move over, actually rotate. So we started to irradiate this cell with a UV lamp on which wavelength was between 260 and 330 nanometers, just from 10 minutes to 2.5 hours, as to find the dependence of the reorientation intensity on the dose of the irradiation. After the irradiation, we could see that the defects changed its direction. Actually, you could see on this picture that the defect effect turns on approximately at least 30, almost 30 degrees. That was happened after the irradiation by UV lamp for 2.5 hours. we make some experiments when we irradiated the liquid crystal cell with the UV lamp, and here you could see the dose of dependence on the angle of the reorientation of the liquid defect in the liquid crystals, still on the dose of which irradiated surface. As you can see, or see on dose 75 millijoules per meter squared, it's quite at high reorientation, up to 25 degrees. If we will irradiate it for a long time, I think it would be turned on for more than 25 degrees. So, what for can we use these experimental results? As, for example, we could precisely control the movement of the defect by the dose of the irradiation and move precisely particles in this which were captured in this defect. Also, so we could use it for dosimetry because the defect movement depends on both of the angle of the so we could see the angle of the defect rotation and see and to precisely measure the dose of the radiation that fall on the photosensitive surface. So it would be used for example, for personal dosimetry for safe sunburns or etc. So something and some another dosimeter, liquid crystal dosimeter. So thank you for your attention, and please questions.
Thank you for your contribution, and please questions. Are there some questions? No. So thank you also for saying time. And the next will be next presenter will be Dr. Andrei Neteba from Faculty of Radiophysics, Electronics and Computer System of the Taras Shevchenko National University of Kyiv. His research interests are connected with biological objects study in medicine by physical introscopic methods. He is co-chair of the organizing committees of 2 international conferences on applied physics. He has been teaching theoretical physics and physical modeling courses at the Kyiv University for about 20 years. Please, Andrei.
Good afternoon, dear colleagues. My name is Andrei. I am from Taras Shevchenko National University of Kyiv, Faculty of Radiophysics, Electronics and Computer Systems. Our scientific group works on the Department of Mathematical and Theoretical Radiophysics and Department of Medical Radiophysics. The fields of our scientific research is in the fields of magnetic resonance imaging, ultrasound imaging. Our scientific results and experimental measurements we have carried out in cooperation with scientists of Institute of Neurosurgery, Academy of Medical Science of Ukraine. Magnetic resonance tomographic device you can see is consists of different parts. The physical principles for obtaining of nuclear magnetic resonance imaging is on the using by special coding physical phenomena of nuclear magnetic resonance. Magnetic resonance imaging may be several types. Among them, imaging weighted by spin density, spine-spine relaxation time, or spine lattice relaxation time. You can see different type of these images in this picture. But for obtaining this imaging, we have different physical factors that influence on the quality, on the informativeness, and of the obtained free induction decay signals.
I'm sorry, your presentation we cannot follow because also all your video with
on the video. Yeah, I'm sorry. I'm sorry.
Your presentations sharing your screen. Yes,
1 minute.
Yes, yes.
You can see?
Not yet. You have to press sharing screen.
1 minute, please. You can see my presentation?
Yes, yes, yes. Now we got it. Yes.
Thank you very much.
Maybe you should to start with first slide and just couple of words and with each slide in order to we follow all your line.
Okay, 1 minute. You can see magnetic resonance imaging device for obtaining magnetic resonance imaging. Magnetic resonance imaging may be several types. Among the imaging weighted by spine density, spine-spine, or spine lattice relaxation time. For obtaining this imaging, we can see free induction decay signals and special of this imaging and this signal in different character of dependence from noise, from inhomogeneities, etc. You can see several images, among them magnetic resonance imaging weighted by spine density, weighted by spine lattice relaxation time, and weighted by spine-spine relaxation time for human brain and for slice on one point of special structure. For obtaining magnetic resonance imaging, we can obtain free induction decay signal in general form can be represented by expression. This expression includes spine density, T1 spine lattice relaxation time, and spine-spine relaxation time. Type of magnetic resonance imaging, among them weighted by spine density or relaxation time, depends on the time of spine echo, TA and TE. For obtaining images, array of signals is recorded in gradient K space, and in these signals can be written as where and depends on gyromagnetic ratio of hydrogen, value magnetic of field gradients, and pulse sequences. For obtaining magnetic resonance imaging, we can use spatial coding of physical phenomena magnetic resonance. And for this purpose, we use transverse gradient magnetic fields. But thanks to local structure, these transverse gradient magnetic fields have an inhomogeneity and gradient instability. For K space, we can obtain this instability of value. We introduce addition correction. We offer to introduce to make correction after recordings of signals, and this in structure of the signals noise components we offer to describe as Gauss-like probability distribution law. For example, the parameter of this probability distribution we can see on this picture, and in our work we offer to make a decision for compensation this noise parts in the structure of free induction decay signal with obtaining magnetic resonance imaging with better quality. For obtaining this investigation, we realized full model experiments. For real magnetic resonance data, we calculate free induction decay signals with dimensions by 146. And for this array of signal, we calculate part of noise component. reconstructed weighted by spine density magnetic resonance images for different parts of a noise component, and you can see on the next images. And you can see for different meaning of these parameters, diagnostic quality of magnetic resonance imaging is different. We offer to realize method for compensation noise part of in the structure in the signal. For obtaining magnetic resonance imaging is which may be used for using in the diagnostic medicine. We estimate, for noise estimation, it is possible to use technique of non-parametric statistical that gives to an advantage about parametric estimation. There is a restrictive assumption of function form. And we assume that standard normal distribution, we have this sample in the structure of signal. You can see in the equation. And after that, we construct of estimation of noise part for these images in accordance to this equation. We use construct some mathematical procedure of estimation and some kernel function. And after that, the structure of this noise distribution you can see in the next images for different parameters of probability distribution. And for example, this estimation, we can obtain different images for different parameters of this probability. And statistical estimation of noise component, it is low to obtain magnetic resonance imaging with part compensation of noise part. And signal expression can be described as equation. Physical phenomena of noise pattern in the structure and all signal may be caused by inhomogeneity of magnetic resonance experiment, because magnetic resonance experiment is based on the using by transverse gradient magnetic systems, and in the each point of cast space we can different deviation from central part. The implementation methods in work to compensate for this instability is to apply filters to the complex signal model's value, because it corresponds to the informative part of the imaging in cast space. And after that, we can obtain magnetic resonance imaging with compensation as a high level of quality. You can see on these images. A method of statistical estimation of the noise component for the conduction of instability of transverse gradient system of magnetic field is proposed. The evaluation of statistical parameters for noise component is carried out, and method of compensation of component instability of gradient of magnetic fields is implemented. The obtained results are have a great interest for the development of our resolution technique of magnetic resonance imaging now, and for creation of modern equipment, for example, local and portable magnetic resonance tomographical devices, and for development new direction in practice medicine, for example, high resolution magnetic resonance imaging. Thank you very much for attention.
Thank you a lot for your talk, and please, oh, there is one question. please.
So, hello, thank you for an interesting talk. I have two questions. Which chemical elements are participating, or the nuclei or electrons of which chemical elements are participating in the formation of this image? So, who gives the signal, and what is the resolution in real space? This is millimeters or micrometers of the images, in the images that you have shown us in your presentation.
Thank you very much. Obtaining magnetic resonance imaging is based on the process free induction decay signal, which obtained for spatial distribution of hydrogen. Because biological object, biological tissue consists hydrogen, and distribution of hydrogen in biological tissue is one of the informative distribution. But different type of images, for example, weighted by the distribution spine density or spine lattice, spine relaxation time, is based on the different physical characteristics of distribution. Spine density is concentration in the point of the space, but based on the relaxation times, depends on the local structure. Because magnetic fields of local structure have influence and depends on frequency of nuclear magnetic resonance frequency depends of the local structure of the local structure. But if you on your questions, what is the size of elements? For example, in practice, in traditional magnetic resonance imaging, element for obtaining and analyze is named as voxel. Voxel size of voxel is maybe 1 parts of the millimeters, because this signal is complex free induction decay signal from all structure. But high resolution magnetic resonance imaging have a resolution with more small by 2 or 100 or 1000 later.
In the micrometer range.
Micrometer, because size of elements is size of voxel, but free induction decay signal is formed from the elements in the volume of voxel. And mathematical equation and inhomogeneity of magnetic fields and the instability of magnetic fields is free induction decay signal and frequency depends of these parameters, not for element of voxels, but for small elements. It's a complex sum of signal.
Yeah. Okay. Thank you very much.
And after that, the level of this is dependencies on the proton level.
Okay, thank you.
Thank you very much for interesting scientific discussion, and also again for your perfect report. I hope we continue also freer a little bit later, maybe by chat, our chat in internet, and we have to go through it. And yes, thank you. The next our speaker will be Dr. Irina Ryzha. She is engaged in mathematical modeling of carbon monoxide oxidation processes of inhomogeneous catalytic surfaces. She was awarded the Yaroslav Pistrihach Prize for Young Scientists in Mathematical Modeling. Currently, she is engaged in a joint Ukrainian-Austrian R&D project, retrospective analysis of Austria's and Ukraine's greenhouse gas emission inventories. So please, Irina. Я не знаю, коли може називатися. Мінус. Просто да. Greetings to everyone. First of all, I would like to thank the organizing committee for the opportunity to participate in the conference. Our paper is about fine structure of oscillatory reaction of carbon monoxide oxidation on the metal catalyst surface. The purpose of this paper is to construct and study mathematical model for reaction diffusion processes of carbon monoxide oxidation on the platinum catalyst surface, and to establish regularities of the influence of surface structure and diffusion effects on the flow of these processes. In order to do this, we'll first consider the reaction mechanism, the peculiarities of the reaction mechanism, then construct a mathematical model, describe it, and conduct some numerical analysis, and finally make some conclusions. Obviously, it is impossible to build a mathematical model of some process without understanding its mechanism. It is believed that carbon monoxide oxidation on the platinum catalyst surface proceeds via the Langmuir-Chadwick mechanism, according to which the reactant species have to adsorb on the catalyst surface before the reaction takes place. The temporal changes of carbon monoxide surface coverage on the surface of platinum catalyst is modeled by the following equation, number 1. This equation describes the changes of carbon monoxide surface coverage due to molecular carbon monoxide adsorption, reaction with adsorbed oxygen, desorption of carbon monoxide molecules from the surface, and diffusion of carbon monoxide molecule along the surface in two directions, OX and OY. The temporal changes of oxygen surface coverage is described by the following equation, number 2. It describes the change of the surface coverage due to adsorption of oxygen atoms, surface reaction, and diffusion of oxygen atoms along the surface. The desorption of oxygen atoms is neglected because it is pretty impossible to occur in the range of temperatures at which experiments are conducted. The nanostructure reconstruction of the catalyst surface plays a very important role in the catalytic carbon monoxide reaction. Especially the adsorbat-induced structural reconstruction on platinum-110 is observed, and the fraction of the catalyst surface in the non-reconstructed 1x1 structure is the change of this fraction of the catalyst surface is modeled by the following equation, number 3, where W describes the probability of the catalyst surface to be in the non-reconstructed structure. F is the model function, and there are also the diffusion terms in these equations, because since W is the probability of the catalyst surface to be in the non-reconstructed structure, so this equation has to have the structure of equation Fokker-Planck-Kolmogorov. So there are two terms with diffusion coefficients in two directions, OX and OY.
Some further changes in the catalytic surface may occur in platinum-110 during carbon monoxide oxidations, namely the formation of new crystal planes, so-called faceting. The degree of catalyst surface faceting Z is modeled by equation number 4. It describes the change in this degree due to surface reaction between adsorbed carbon monoxide molecules and oxygen atoms, and also the catalyst temperature, which when raised slows down the faceting formation. It also should be mentioned that such structural changes of the catalyst surface influence its adsorption properties, especially with respect to oxygen. So the oxygen sticking coefficient is written as the linear combination. And it also should be mentioned that the rate coefficients used in those 4 equations are determined by the Arrhenius equation, so they are temperature dependent. The results of numerical analysis will be presented on the next few slides. First, we considered the case when the diffusion coefficient for W is neglected, and we obtained, we can see that mixed mode oscillations appear in the system. Such a fine structure when the oscillations of high and low amplitude are observed is due to the fact that because of the faceting and the surface reconstruction, some new sites, active sites appear on the surface, and also the oxygen sticking coefficient is increased on the faceted surface. It also should be mentioned that we can see that for different diffusion parameters of oxygen, the oscillatory behavior doesn't change. So the oxygen can be modeled as a mobile atoms on the catalyst surface. Obviously, this can be explained by the fact that the oxygen diffusion coefficient is still rather 1/100 of the same coefficient of carbon monoxide. So the oxygen atom will rather react with carbon monoxide atoms situated near to it than diffuse to the other 3 sides. The next slide presents the results of numerical analysis when the diffusion coefficient for W are not equal to 0. Unfortunately, there are no experimental data for the value of this parameter, so we considered 2 cases for slow and fast diffusion of W. In the case of 1/10 of diffusion of carbon monoxide, we see that the oscillations do not have a pronounced character. And for the fast diffusion of W, we see that there are no oscillations at all, and the system is in the state of high reactivity. So how can this be explained? Due to W diffusion, the surface reconstruction loses its the surface reconstructs faster to the structure, which is more which is better for oxygen atoms to absorb on it. So the more oxygen will absorb on the catalyst surface, then this oxygen will react with carbon monoxide that has already absorbed there, and so the system will be in the state of high reactivity. So some conclusions. The 2-dimensional mathematical model for carbon monoxide oxidation on the platinum catalyst surface has been developed according to the Langmuir-Shelwood mechanism. This model takes into account the influence of diffusion effects and the nanostructured construction of platinum-110 surface. So the structural changes of the platinum-110 surface during the reaction have a significant influence on the character of oscillatory mode and may cause as mixed mode oscillations and the state of high reactivity as well. Thank you for your attention. Any questions are welcome. А в чате там
Ні, нема зараз на дану презентацію нема. Thank you very much for excellent report. Thank you. Yes, we should go on.
Hello.
The next speaker will be Rostislav Lisyuk. He was awarded with Fulbright Scholarship Grant and carried research in North Dakota State University in the field of colloidal quantum dots and spectral converts for solar cells. Also, he got the Dresden Excellence Junior Scholarship and moved to Germany, keeping cooperation with Maastricht Institute for Applied Problems of Mechanics and Mathematics and Lvivska Polytechnica. In Germany, Rostislav worked later on the EU-granted project, two-dimensional Synetra, about colloidal two-dimensional nanomaterials at Hamburg University. After completion of the project, the group moved to the University of Rostock, and Rostislav joined the Nanostructures and Nanomaterials group, where he is currently working on colloidal nanomaterials and their properties. So now is Dr. Rostislav Lisyuk will present a report entitled as Colloidal Two-Dimensional Nanomaterials Shape and Dimensionally Control Opens in Region Properties.
Good afternoon, Lviv. Good afternoon, Kiev. Good afternoon, all the cities. Can you hear me?
Yes, yes, we hear you. Yeah.
It's a great pleasure to contribute to such a nice conference. At that time, unfortunately, many of us cannot be present in person in Lviv. So I will quickly go through the outline of my talk. I will give a little bit introduction of what is a shape control and dimensionality control, what is the difference and the peculiarities in this. Then I will shrink the topic only to one project about lead sulfide as a template colloidal nanomaterial. The lead sulfide is very popular material, but I will show you how the surface properties may fundamentally change the properties of this common known semiconductor. I will start from the question whether the shape can considerably influence the properties of physical objects. Is it correct? So probably we will answer yes, the shape can somehow alter the properties and help us, but can the shape switch the properties of physical objects or create new properties? Only the shape. And the answer to this philosophical question is yes, in particular in the nano world. But for that, I will just refresh something from the field of colloidal nanostructures. So I'm sure every one of you heard and maybe has some experience with colloidal quantum materials like quantum dots or nanocrystals, and there are plenty of nanomaterials in this field. So you can see some displays were even fabricated with the help of these quantum dots after 30 years of development. But a lot of projects are still in laboratories. Let's go to lead sulfide, very popular simple material, and you can see how the colloidal synthesis and exactly to say the conditions in the synthesis, the ligands can alter the shape of this material with the cubic crystal structure. So you can see you can have octapods or star shapes or near spheres and so on. So there are plenty of possibilities to change the shape. But the new level is to change the dimensionality of the material, because with dimensionality you can have additional properties. Here you can see different dimensionalities like bulk has no dimensionality. You can see the nanosheets or nanoplatelets, which are kind of soluble quantum wells. So quantum wells are known from the solid state physics and thin films. And so you can get also by colloidal synthesis these structures in solution. You can see the nanorods and quantum dots. Of course, there are plenty of approaches to explain the properties. The main thing is that you can quantize the energy of electrons in such a structures, and you can tune the spectral properties a lot and other properties. So what is interesting that the quantum dots were famous since more than 30 years, or maybe 30 years, let's say 30 years, but relatively recently, the dimensionality control came to the field, and nanoplatelets of cadmium selenide were synthesized by French group of Dubertret and Etruria and other South Korea group. And later, it was done also with lead sulfide. And this opened the very large 2D nanochemistry field. And in this field, we are working now. So what is the difference in the spectral features, for example, of such structures? If you see in the left, the cad selenide quantum dots have quantized absorption transitions, but you see the broadening of the lines. Whereas in the nanoplatelets or nanosheets, mostly nanoplatelets, these lines are very nicely resolved in Sold transitions of heavy hole, light hole, and split off orbitals. So, and you can see this at room temperature. That means that you see excitons in both cases, of course, but in this case, you see the very nice exciton absorption at room temperature, but it's not possible by for example, gallium arsenide, which is studied always by cryogenic temperatures. So that means you can very precisely tune the spectral features, and the very nice property of nanoplatelets is that they are atomically precise systems, so, or atomically homogeneous systems. So if you synthesize your product, you have normally nanosheets or nanoplatelets with a homogeneous thickness, and this thickness can be increased only by one monolayer and the next monolayer and the next monolayer. So that means you can selectively choose the spectral position. You can track your thickness by the spectral position. So what is nice by the large nanosheets is the nice thing is that you can contact them individually. You can study the properties in the individual way. So you can, by lithography, by electron beam lithography, you can study individual structures. And this is what our group does mainly. So this is an example of a very recent project of zinc sulfide nanoplatelets, and you see this excitonic absorption at room temperature, which is very so it's kind of approximating the giant oscillator strength effect, so which you cannot observe by quantum dots because they have the signal broadening due to size dispersion. Yeah, they suffer always on size dispersion, and this system are atomically precise. So you see pronounced excitonic absorption. So just few words summarizing. I will try to summarize how you can how you can realize the dimensionality control. So in colloidal synthesis, you can influence the surface energy of different crystal facets, yeah, by surface selective ligands. So this is the main instrument how we can direct the growth or do something with our crystal and make another shape or dimension. Also, we can provide conditions for a templating effect. So we get the confined growth in the surfactant mesophase. So we get some, we put some ligands which self-assemble and align in specific way, in such a way that they create a template, lamellar effect, and in this templates the synthesis is done, and you get the 2D nanostructures. And also you can have self-organization effects, such as oriented attachment. And normally, or very often, you have combination of several effects. So this is something to show about this templating effect. For example, you have your precursor, and you have your ligand self-assembled in such a templates, and then inside you synthesize your material and you get 2D nanomaterial. Or you can do it the same by oriented attachment. First nucleate your nuclei, let them a little bit grow, and then let them attach in a specific way by the help of these ligands, and then get to 2D nanostructure. So this is an example of zinc sulfide. You can track this process, this templating effect or templating structure, by the small angle X-ray scattering, and you see this periodic pattern which say out that there are distinct periods between these lamellar structures, and inside you can calculate how your ligands align and so on. So you can nicely track this during the synthesis. And now I go to the lead sulfide, and lead sulfide is a cubic material, so it has octahedral symmetry. So it's very symmetric material. So how you can get actually the 2D nanomaterial from this cubic, very high symmetry material, but it is possible if you not only have some standard ligands like acetate, carboxylates, and for example, like oleic acid or oleate, but you also co-dope or you have co-ligands like halides. Halides are very famous co-ligands which can do with the nanostructures almost crazy things. So we can get, for example, very nice, very thin, several nanometer thin nanostructures of lead sulfide. And if you put more of this halides, you can get nanostripes. And then you can contact them individually and study their properties. So it was found that, for example, they are very nice semiconductor structures. They have better properties as a film of nanocrystals because they have no intergrain transitions. And if you study them, you see that they show you field effect, photoconductivity, and so on. So they behave very nicely, but always as semiconductors. And in one synthesis where our student was checking a lot of parameters, went through the parameters. In one synthesis, we synthesized such interesting zigzags nanostructures. And what was special about the zigzag nanostructure, when we contacted them individually, we saw the very bad semiconducting behavior. That means they showed no photo effect, no field effect. But what was special that they had very large current. So yeah, two magnitudes larger than the semiconducting than the straight ones. The straight ones were semiconducting, and zigzag ones were kind of metallic, we would say, at that time. And it was nothing special. So if you have bad properties, you don't care about this. But actually, it was interesting why they have such properties. And we started to check something about the structures. And yeah, so semiconducting and metallic properties. So why there is a metallic behavior? The first idea was maybe there is a metallic shell around the wire, and we did a lot of ADX and mapping experiments. So we never see some shell, some lead shell around the, yeah, that could be only lead shell, of course, around our nanostructures. So then we thought maybe we have some doping of our nanowires. And the third idea, a third hypothesis was that we have something like exposed 111 facet. 111 facet is something special because 111 facet is a polar facet. It can consist only of sulfur or of lead. And we assumed maybe we have the 111 facet. Then we started to check the crystallography of our nanostructures. And we found that, in fact, this ridiculous structure of zigzags can be explained if you add such octahedrons, which we also observed as a side product in the synthesis in such a way that they build the zigzag with only 111 facets. But how can 111 facet on the lead sulfide bring you metallic properties? But the following experiments showed something very weird. If we check the temperature dependence of the conductivity of our nanostructures, we saw that straight stripes, which are semiconducting, with temperature, they show typical semiconducting behavior. So the conductivity goes down. And in the zigzag wires, as the conductivity goes up. What was more surprising, that at the temperature of 7.57 Kelvin, we saw the jump of conductivity. And this jump of conductivity could be interpreted as maybe it jumped to superconductivity because maybe we have some lead on the surface, especially this temperature, because this temperature is this inherent temperature for lead, where lead turns into superconductivity state. I'm sorry, I'm out of time. Should I take more 5 minutes, or should I conclude? I'm sorry.
Yes, couple of minutes you can use, couple of minutes.
Okay, I will use a couple of minutes. So we started to think how it can be like that we get this result based on these three hypotheses. But the first hypothesis was excluded. We don't have the metallic shell. So we also checked the XPS, of course, to check whether we have something like massive lead and so on. And yeah, this is some graphics which explains how the stripes and wires are built in such a way that the flat stripes or flat stripes, they don't expose 111 facet, and the zigzags, they always expose the 111 facets. The difference in the synthesis was that we put more ligands inside. So we stabilize more the 111 facet by oleic acid with co-ligand chloride. And I showed you this graphics, but I wanted also to show you, we wanted to check whether they really have this volumetric three-dimensional structure. And this is tomography video, which shows you the stripe, the straight nano stripes, and they are really straight. They don't have any volumetric structures inside. And then we checked the zigzag structures, and we saw indeed they have this volumetric 111 structure. Yeah, I wanted also to show you, but I will skip it. I will go directly to the main conclusion. So how to explain this? And we started to think maybe we can simulate this, and we took some DFT simulations. So we built crystals or nanocrystals with a vacuum inside, so it's some confined system, and exposed the surface with 111 and 100 surface. And then we see that if then on the right side you see the band structure, and then we see in the 100 termination you have always the band gap. It's very typical behavior for lead sulfide. Of course, the band gap is larger because it's confined. And if you have 111 termination, you have no band gap, and you have really the wave functions that have orbitals which lie inside the band gap, and you should have metallic behavior. And if we visualize these states, this state corresponds to this visualized state, we see that in opposite to the localized state inside the crystal, this state is delocalized on the surface, and that should be the reason for this metallic-like transport. We also found some literature, very nice paper about the similar simulation, and they show in fact same result. So that give us some idea about how it works. So I will maybe skip the XPS results, but we can go back. If you have some questions, I will go to directly to conclusions, and I will not read the conclusions, but I will just conclude that the electrical properties of lead sulfide nanowires, zigzag nanowires, were tuned from semiconducting to metal ones, and supposedly to superconducting by faceting the crystal, so only changing the shape of the crystal. So changing the shape may give you new fundamental properties. So in that place, I will thank you. I will just give you one more overview about materials that we produce or we synthesize. Maybe you have some interests that are, for example, copper sulfide, copper indium, disulfide, zinc sulfide, tin sulfide, tin telluride, perovskites, everything in 2D. And on that place, I would like to thank you and sorry for my delay with time. If you have any questions.
Yes, thank you a lot for a very interesting and important presentation. And please ask somebody some questions. In chat, there is no also question. So if somebody we obtain, we share with you, obviously. And thank you again for your contribution.
Thank you very much.
So the next speaker I would like to invite, it will be PhD student Oksana Kalinikova. She is from Bogomolets Institute of Physiology, NASA of Ukraine, and title of her report, The Influence of Gold Nanocomposites Treatment on Male Reproductive Function. Good evening, Sana.
Hello, everyone. Are you here and see me?
Yes, we see you. And please just go into the full screen mode.
Yes.
Stay with us.
I see my presentation?
Yes. Okay. Nice. And you should start. Yes.
Okay. The topic of my report is the influence of gold nanocomposites treatment on male reproductive function. Nowadays, the use of nanotechnology in order to create new high-performance biomedical nanocomposites proves to be one of the most relevant research topics. Due to the structural features and manageability of the intramolecular structure, branched polymer systems are considered to be interesting object of basic research, as well as promising functional materials of the new generation. Recently, it was shown that polymers with a dextran core and graphic polyacrylamide chains, dextran polyacrylamide, DPA, are effective in photodynamic chemotherapy, which gives confidence in the prospect of drug nanosynthesis. However, further research is needed to turn the concept of nanotechnology into practical application. Thus, animal studies are becoming more relevant to determine the effect of the treatment of such drug nanosystem, DPA polymer matrices, on male reproductive function in particular. So the aim of study is to evaluate the effect of a 5-time treatment of polymers with a dextran core and grafted polyacrylamide chains, DPA and DPAP, as well as gold nanoparticles in the composition of such polymer matrices on the male reproductive function in mice. Experiments were carried out with the use of adult male albino mice. The investigation polymer matrices were synthesized at the Department of Chemistry of Macromolecular Compounds of Taras Shevchenko National University of Kyiv. Doses of test compound are given, and gold nanoparticles have a spherical shape. To assess the viability of sperm, a dye test of trypan blue was performed. The number of sperm million per milliliter was counted using Goriev's chamber, and its morphology was analyzed. Evaluation of the ratio of cells of different generation of spermatogenic epithelium, spermatogonia, spermatocytes, spermatid, Sertoli cells, and the apoptotic ethnocrotic diff of testicular cells and cells of the epididymis was estimated by morphological characteristic using the method of dual color fluorescent dinucleus acid, HEOX, and propydium iodide. We have two polymer matrices. The first is unloaded starlight polymer matrices DPA, consists of dextran nucleus and rafted polyacrylamide chains. The second is charged starlight polymer matrices DPA-PE, consists of the dextran core and grafted partially hydrolyzed polyacrylamide chains. Alkaline hydrolysis modifies some of amide groups of the hydroxyl, which also causes the negative charges of the macromolecule. The size of the nanoparticles of gold loaded in GPA was 2 to 5 and 16 to 20 nanometer, and in DPA-PE 4 to 11 and 16 to 20 nanometer. Our result, the next is treatment with gold nanoparticles in the polymer matrices does not change the concentration of sperm, but increase the number of abnormal sperm, both total and primary anomalies. Compared with such values in control group and compared with such values in the group DPA-PE, and compares with such values in group gold DPA. Under the condition of treatment with gold nanoparticles in the polymer matrices, the number % of testicular spermatogenic cells, spermatocyte and spermatids significantly decreased in group gold PA-PE compared with group control and compared with group DPA-PE. Under condition of treatment with gold nanoparticles in the polymer matrices, the number of primary spermatocysts with morphological signs of apoptosis and necrosis under this condition change. The number of living cells is decreased. The number of apoptotic and necrotic cells is increased in group gold DPI-PE. Compare with group control, compare with group GPA-PE. In the next estimate, we saw that similar data, because in the number of epidermis cells, spermatozoa gives us a more significant effect, particularly living cells decrease and apoptotic and necrotic cells increase. Under the conditions of treatment with gold nanoparticles in the polymer matrices, in the group gold DPA-PE, we saw the increase embryonic mortality and particularly pre-implantation mortality increase and post-implantation mortality increase. Compare with control group and group DPA and group gold DPA. And last picture, in this condition, we also obtain similarity data. In group gold DPA-PE, we have increases number of live newborns, pups. And our conclusions. For the first time, it has been shown that 5-time treatment of with GPA and GPA-PE and gold GPA did not affect reproductive function in male mice. But disorder of the mice reproductive function occurs under condition of 5-time treatment with gold DPA-PE and significant change in the values were established in pre and post-implantation mortality on embryos, the number of live newborn pups, sperm and abnormal sperm 4%, spermatocytes primary and spermatids percent, living apoptotic and necrotic cells in the testic, spermatocytes primary and epidermis spermatozoa. And further studies called IM at determination the by description, accumulation, retention, removal of such copolymers, DPA and DPAPE. And particular attention could be paid to the interaction of the copolymers, nanoparticles, with the cells of immune system. For example, to determine citron non-specific immune responses and the delivery on engineering particles and drugs to target organs, tissue, or cells. Thank you for attention.
Thank you a lot for interesting talk. And please, are there some questions in conference hall? Just let me to check if somebody to write. Okay, maybe later we obtain something for you too, and we share with you questions if you will have. Thank you again.
Thank you very much.
Yes, yes, have a good and nice evening. Okay, thank you.
Bye.
Bye. And also, before we closing our sessions, I have I would like to give a chance to make a presentation in the second time. Dr. Ruslan Sergeyenko from Physico-Technological Institute of Metals and Alloys of the National Academy of Science of Ukraine, which entitled as Zirconium-based amorphous and nanostructured ribbon. Please share with us your screen.
Так, I share my screen.
Yes.
Can you see my presentation?
Yes, yes, we can see,
Yeah.
and just yes.
Okay, can I show like that? Because I afraid if I put full screen. Okay, okay.
Yes, perfect. You see.
Okay.
Good luck for your presentation, and we should start.
So I want to represent my subject, zirconium-based amorphous and amorphous nanocrystalline rods and ribbons. So this work was done in the Physico-Technological Institute of Metals and Alloys, National Academy of Science, and our Department of Physics and Chemistry of Alloys. So actually amorphous materials, if we say about metallic compounds, so they are called also metallic glasses, have been actively studied since 19th of last century. So in different countries, for example, first of all in Japan, this is under leadership of Inoue at Tohoku University, and also in the USA, Russia, and in our institute also we are provided such kind of investigation for production of amorphous materials. So I would like to say a few words about advantages of amorphous metallic materials, metallic glasses in comparison with traditional crystalline alloys. So this is actually metallic glasses have higher resistance to destruction, higher hardness, and higher corrosion resistance because of special structure, because of no long range order structure, not ordered atomic structure, no grain boundaries. For this reason, amorphous alloys of metallic glasses have
higher strength, higher corrosion resistance. So a few words about some benefits and about benefits. I say already a few words like higher hardness, higher strength, and corrosion resistance. But shortcoming of these materials, actually quite low plasticity at room temperature, and during for preparation of this material, we need some good vacuum equipment and also lower modulus of elasticity compared to crystalline material. So to increase some mechanical properties, for example, strength and plasticity, we tried to prepare such kind material like amorphous nanocrystalline. So we can imagine structural. This is structural model. So this is model consists of amorphous matrix, and inside this amorphous matrix distributed nanocrystals. And nanocrystals should actually nanocrystals should increase like plastic properties of metallic glasses. So main goal of an objective and goals of our work was prepare amorphous nanocrystalline materials, and object of study was zirconium-based amorphous alloys. So the system is zirconium, copper, nickel, aluminum. So we actually we studied what we studied. We studied thermophysical properties and also some mechanical properties. So these pictures show enthalpy, how enthalpy change when liquid substance is cooling down, and if heat amorphous material, so how amorphous material go to solid, go to crystalline in crystalline sense. Actually, if during cooling, if liquid substance, so melt can go to crystalline state at the temperature of crystallization. If at low cooling condition, low rate cooling condition, but if we make some special cooling condition like fast, very fast start very fast cooling, so liquid substance can go to directly solid, but go to not in crystallized state, go to amorphous state. So, and also amorphous, any amorphous structures, metallic materials, metallic glasses, they have like they have a special interval. So this is the delta T interval, call it superplasticity interval or interval for super cooled liquid. Actually, our idea was to heat up material higher at temperature higher than glass transition temperature, and keep at this and keep in this interval temperature interval this material, and during holding this material in this at this temperature in amorphous matrix should appear nanocrystals. So this is our equipment which we use for preparation of amorphous alloys. This for preparation of ribbons we use like casting on the copper wheel, and for preparation of rods we use vacuum suction equipment in the copper mold. This is equipment for investigation. Actually, we use differential scanning calorimetry to analyze thermophysical properties like glass transition temperature and crystallization temperature, also heat crystallization. So this investigation is connected to we investigate crystallization at zirconium-based alloy at different heating rates. So as you can see, if you heat up material at different heating rates, so also change position, also change, you can see like shift of temperatures, glass transition temperatures and crystallization temperatures. So this is dependence of temperature. For example, from this picture, temperatures of crystallization temperature and glass transition temperature from heating rate. So as you can see, this is like logarithmic dependence. And at higher heating rate, also temperature shift to shift up, increase. So this is actually we put thermophysical characteristics of amorphous rod and ribbons in the table. So this is characteristic for transition, for glass transition temperature and crystallization temperature at different heating rates. And also we calculate energy of activation energy using Kissinger method. And also using differential scanning calorimetry, is it possible to not calculate, just directly calculate from the DSC curve heat crystallization. And this is another like experiment. It was also different DSC differential scanning calorimetry experiment, but we heat up material up to special temperature, for example, 390, 40 degrees C, 420, and keep some time during this temperature. So in such kind we can analyze and we can calculate like volume if we analyze this curve. So we can calculate volume of a fraction of crystallized material using classical equation like Kolmogorov, Johnson, Mail-Avrami equation. And as I said, we calculated heat crystallization using just area under the DSC curve. And area also change. For example, if we keep sample at different temperatures and a different type, also change some thermophysical parameters and change heat crystallization. And we just calculate heat crystallization from easy equation, compare with initial amorphous sample. So this is thermophysical parameters at different heat annealed samples. So we prepare samples in amorphous state, and this was heated up 300 degrees C, 370 degrees C, 2 hours, and rest materials at higher temperature. And you see also change glass transition temperature, crystallization temperature, and most important, we can calculate from this the DSC curve a fraction of amorphous and crystalline phase in our material. So this is actually developed our heat treatment conditions for zirconium-based alloy. So we use on the basis of this DSC investigation. So we find some regime for treatment of zirconium-based alloy. And now I would like to show structure and some physical properties. So from this slide, you can see some different rods and ribbons at heat treated at different temperatures and at different holding times. And you can see some inclusion of a pair in the amorphous tape, in the amorphous rods and ribbon. But this inclusion is we cannot analyze from these pictures because the same images have low resolution. And actually, this is so we try to use also a transparent electron microscopy to investigate more precisely structure. But here also some investigation of X-ray diffraction analysis for our samples, and you can see our samples remain almost amorphous up to 400 degrees C. But we can say our materials remain like amorphous even at when we treat at this temperature. Some changes is happen. Just we can look by high resolution microscopy. And of course, at higher temperature, we can recognize some peaks. And these peaks came from intermetallic compounds, zirconium to nickel. So this is transparent electron microscopy images, and transparent electron microscopy investigations show that heat-treated ribbon at 420 degrees C show some particle, nano-sized particle. It's zirconium to copper, but zirconium to nickel, we found they have larger size. And finally, some properties. I show properties and next conclusion. So if we heat up at higher temperature, go up temperature and also holding time. So it's exactly, for example, hardness of material increase and increase from by 2 to 12% about. And also actually for plastic properties, it's difficult to say because maybe a little bit material become a little bit more plastic, but unfortunately plasticity of metallic glasses is it's like a hard question because amorphous glasses, metallic glasses, it's quite brittle material, and we can compare plastic properties only with like amorphous initial amorphous material. But if we compare with usual crystalline materials, usual commercial crystalline materials, so no plasticity is much lower for metallic glasses. So finally, conclusions. So for obtaining of amorphous nanocrystalline structure in zirconium-based alloys, so we conducted heat treatment of our samples, rods and ribbons in the special region. It's between glass transition temperature and crystallization temperature, and also developed some regimes like holding time, temperature, and investigate some thermophysical properties and some mechanical properties. So presentation is finished. Thank you very much. If you have some question, please ask me.
Dear participants of conference, thank you a lot for your attention. Now our conference is coming to the end, and let me to provide you small statistic. During these 2 days, we have conference in combined format. It was our first experience in such a way to organize the conference. Due to the COVID, we decided to provide and to help our conference in format online and offline. And now we received the experience, and I think in the future we will use some moment for other conference too. During this year conference, we have 46 oral presentations, and among of them we have 70 presentation which was from a plenary session. We have participants from different countries of the world, and this year due to COVID we provide opportunity for scientists to use such a platform as Virtual Nano. And now we will stop our conference, but all who was registered on Virtual Nano have opportunity to appoint the meeting and to cooperate with scientists from different countries of the world. And it will be possible during the next 2 days too, because Virtual Nano will be continue to work during next 2. So you have opportunity to continue to appoint the meeting on Virtual Nano too. Also, everyone who have poster session, we provided opportunity to post it on our website. So I invite everyone to go to the website and to look on the posters. There are approximately 200 posters is posted on this website. Also, we provided such opportunity as our Facebook page of nanotechnology and nanomaterials conference. There you can find a lot of posters which is located in different sections. We invite you to discuss these posters. You can communicate with the different corresponding authors. You can see that contacts of this corresponding authors is posted in posters. So please contact it, please discuss your future cooperation. And this year, as you can see, we have broadcasting of 2-hour days of conference on our channel, YouTube channel. It will be, this video will be kept, so everyone can to open the link. This link is disseminated to all our participants, and to look again on interesting topics, on interesting lecture. If you wanted to cooperate with some concrete scientist, please contact with him, because the main our suggestion and goal of this conference is provided opportunity for scientists from different countries of the world to cooperate. Thank you for your attention, and I hope that the next year we will have opportunity to meet again with you, and maybe COVID will be stopped and we will have opportunity to have face-to-face meeting. So goodbye.